Good morning and welcome. The communication landscape is always evolving, and AI and machine learning are turbocharging this evolution. Networks are advancing from 5G to 6G and beyond, while the field of AI and machine learning progress at an incredible pace. This gives rise to the captivating question: how can we ensure the seamless integration of AI and machine learning into our future networks? Today's workshop will shed light on the several exciting aspects of this integration. We are building on sustainable, substantial bodies of prior work. We started with the ITU focus group on machine learning for 5G and future networks, making an influential contribution to ITU standardization work. We followed with the ITU AI ML in 5G challenge, our discovery series of expert webinars and special machine learning editions of the ITU journal on future and evolving technologies. Key concepts have also been further examined by our focus group on autonomous networks. I'm glad to highlight that we have achieved encouraging results, consistently expanding ITU's machine learning community. The ITU standard Y.3172 provides an architecture framework for machine learning in 5G and future networks. These standards have been very well received based on the outcome of our machine learning focus group. This standard laid the groundwork for machine learning pipelines and related work within ITU and other bodies. The ITU AI ML in 5G challenge built on this foundation. The challenge is an open competition for some students and professionals to collaborate on practical problem statements and open datasets. The challenge has attracted participants from over 100 countries, and they benefit from mentoring and the webinars, mentoring on the webinars that have received tens of thousands of views. In partnership with the challenge, the Build-a-thon initiative run by a focus group on autonomous networks have produced a range of product of concepts. This work has engaged more than 100 participants, including from developing countries. However, the AI and machine learning landscape is changing rapidly. We are now in the era of generative AI, large language models with hundreds of billions of parameters and cloud-native networks. In this transformation, we believe that our open collaborative ecosystem encompassing industry and academia offers a unique opportunity to analyze emerging requirements and take action to meet them. We are joined today by a diverse group of experts to discuss what our next step should be as we look toward 6G and beyond. We will gain insight on the latest research directions in AI and machine learning for networks, AI native 6G, practical architecture enablers, and potential integrations. And we will ask what are the key requirements of applications, ambitions for 6G and future networks. and what are the machine learning mechanisms and integrations needed in networks underlays to address these requirements. I express my gratitude to the experts joining us today to share their knowledge and experiences. I also thank our many participants attending in person and online. I will follow your discussions with great interest, and I wish you a most successful and productive workshop. Thank you.
Thank you very much, Onoe-san, for the opening remarks. So right now, we can set the stage, and maybe Vishnu, you can start with icebreaker and introductions.
All right. Bonjour, colleagues. Bienvenue à Genève. Thank you so much for coming. I think we, as Onoe-san just now mentioned, we have been working on this workshop for quite some time. I've been, in touch, in fact, bugging most of you, I think. So welcome, everybody. Today, we have a packed session. We have 4 sessions going today. Let's take a look. Okay, so we have 4 sessions today. In between, you will have time to grab something as well. No worries there. We have some changes in the agenda. I will go through them as Thomas will bring it up. I will go through that as well. Thomas, you want to do the first?
We do the first slide or the slides?
Yeah.
I thought we can do just quick introductions.
Okay. We don't have time. We can go through the slides and discuss.
Okay, seems time is not on our side, so let's just quickly go through the introductory slides. And this will set the tone or the stage for the sessions that we are having today. And probably first, let's go through the background of the activities that we have been doing over the years. So since 2018, I think most of the work for the machine learning communication network started with the focus group in focus group machine learning for 5G. And this focus group published some relevant work that has been cited, that's been used within ITU and also in other SDOs. And the work that was the beginning was on the use case, on use cases for machine learning in 5G. And then this was proceeded by Y.3172, which was the architecture framework for machine learning in future networks. And this is one of the, I would say, most downloaded and cited machine learning recommendation in study group 13 and one of our relevant work. And of course, there are other works that also derived from this, for example, data handling, saving framework, marketplace that was produced. So the focus group finished this work in 2020. And fortunately enough, in 2020, we started the ITU AI Machine and 5G Challenge, which has been running since 2020 up to now. And we are really privileged to have several collaborators that has worked with us over the years, still working with us. I see many people in the room that are presenting today that has been collaborating with us. These are some of the people that has contributed tremendously to the success of the challenge, working with us for the past 3 years. We have Barcelona Neural Network here. They have had the Graph Neural Network Challenge, and the 4th iteration was just launched 2 days ago. Happy to see the results from there. And we have our collaborators from Huawei who have posted 2 problem statements for this year. We have Arizona State University, Professor Ahmed, ZTE, Fraunhofer, and several others. So it's really nice to see everyone coming up in this workshop to join us and also collaborating with us over the past few years in the challenge. And it's not only the challenge, but also the outcomes of the competitions have been published. We have had 2 special issues published and 1 special issue is in the pipeline. So the idea is that the solutions from the challenge can be put out publicly as open source. So the code, we have the GitHub repository where the code is placed and anyone can access the code, the repos, the slides that are associated with the work that is derived from the competitions. And also this supports to the pre-standardization work that is ongoing in ITU related to machine learning communication networks. So we have this feedback loop where we have work in the challenge or the competitions that we host, and some of the solutions contribute to open source, some contributes to pre-standards activities in ITU, and some contributes to research, furthering the research directions in different research institutes and industry. And yeah, let me not take much of your time. I would give the floor to my colleague Vishnu to continue with the presentation.
Thanks so much. So this picture may be familiar to most of you. This is our work in focus group autonomous networks. We started with work on publishing of use cases. We studied 40 odd use cases, and then we published this architecture framework for autonomous networks. And in addition, this not only paperwork, we also did proof of concept work. There's Build-a-thon proof of concept. This proof of concept has seen 100+ participants since 2020. So we have been running it for 3 years now, and this is the 3rd year that we will be running. This is the framework. I don't go into details. Paul is here. He will go through a lot of details from the focus group work. Next slide, please. Thank you. So you will see a bunch of colleagues today. We have been doing this ML5G webinars hosted over last from 2020 onwards. We have 100+ webinars already hosted, and they have been viewed all over the world. These colleagues, whoever is circled, are here. Thank you for coming. You will have the privilege of listening to them again. Next slide. These are some of the lessons learned for your benefit. We have derived this out of these talks which I just now talked to you about. The first one is that AI/ML is changing quite a bit. I mean, it is not what it used to be 5 years back when we did machine learning 5G. It is quite a bit evolved now. Now we have ChatGPT. Now we have large language models and billions of parameters, as Ono-san mentioned in his talk. There is Copilot, there is GitHub Copilot, and code generation and document generation and whatnot. We ourselves actually tried with our own ITU's own Copilot. In fact, it is being used in Build-a-thon right now for generating use cases and assisted generation of use cases by students and participants. The 6G is coming. I don't have to talk too much about it. You all know semantic communications. Today we will hear from Abhishek, as well as there are network digital twins. We will hear from the experts here. Albert is here. The open data and ecosystems have evolved. 5G challenge we have been running, and that's quite important. We heard and we will hear from Shilin today, chief scientist in China Mobile. She will talk about the importance of that. Autonomy and AI/ML is important. Focus group autonomous networks has been working on it, and building a community is the most important aspect. We have Professor James from Nigeria. He will talk about this particular aspect. So collaborations is the name of the game, and the question is, what do we do next? So this we will answer. Try some answers today. Next slide, Thomas. This workshop did not happen yesterday. we have been studying the advances in AI/ML for quite some time now. 2020 onwards, as 2019 onwards, we have been studying the gaps and integrations of machine learning, 5G, 6G, and so on. We have been studying use cases, requirements, sandbox. Fatih is here. He will talk about Mina sandbox and its concepts. So we have been studying that. ORAN and architecture options have been studied. AI native features we have studied, and there are several webinars which we hosted on these topics. So on the right side, we have the sessions. Session 1 will focus on AI machine learning advances to bring you the latest topics from AI machine learning, building on the collaborations from focus group machine learning 5G onwards. Session 2 will look at network advances, focusing a little bit more on AI/ML challenges and discovery series. And session 3 will look at platforms, building on collaborations from autonomy, focus group, and so on. Session 4, we will look at, finally, what do we do next and what are the integrations possible? Next slide, Thomas. So let me quickly go over each sessions a little bit, scratching the surface. So session 1 is called generative AI. Is all that you need or not? So 2017 we discussed with Slamir. Slamir is the chair of focus group machine learning 5G. When we discussed with him our topics, I think some of you already know. We were talking about linear regression. We were talking about ARIMA models, what not. The main problem at that time was whether data is available at all or not. That was the problem at that time. And now you see there is the landscape has changed completely, because now we have generative AI. Now we have large language models, application aware scenarios, and machine learning operations. Salih is here. You will hear from him a lot more. And the question is, what do we make out of it? So Sam is unfortunately not able to make today. He's supposed to talk about unleashing potential of machine learning and AI in 6G. We have Abhishek in place of him, so he works with Slamir. He will talk about semantic networks and the topics under that. So we will discuss with Abhishek on that. Wemong from ZTE, he's the chairman of governing board of LFAI and data. He will talk about open source opportunities in AI-enabled 6G. Salih is here. He will talk about machine learning operations. So this is our session 1. There may be a slight change in the order. Wemong will go first, and then finally we'll close with Abhishek in this session. Next slide, please. In session 2, we have AI native open networks of the future. You know, in 2017, when we discussed this, in 2017, when we looked at this, there was this concept of how to apply machine learning models into networks. But now the networks AI models ate up the network, so to speak, because you have network functions and services and applications implemented inside models. So that's what is happening now, right? So to study this kind of an evolution scenario, we have Albert. Albert will talk about how to build a network digital twin. He's our great colleague from Barcelona Neural Networks. He's also a host for Graph Neural Networks Challenge for 3 years now. Enning is here. Enning from Nokia Standards, chief architect of AI machine learning Nokia. He'll talk about native network intelligence in 5G advanced and 6G perspective. Enning has given considerable, I think 2 or 3 talks, if I remember right. Excellent perspectives. You should listen very carefully. Professor Tom is here. Professor Tom will talk about trustworthy AI applications to 5G networks in collaboration with our colleagues from Wabe. He will talk about this analysis. It's very interesting optimization algorithms that he will talk about. Please don't miss the chance. Tim is here. Tim will talk about deep learning in physical layer, as well as his pointers and guidance for what to do next. We should carefully listen to Tim. Next slide, please. In session 3, after lunch, so we have session 3. We will talk about platforms for 6G. You know, in 2017, again, in 2017, we looked at mainly core, edge, and radio aspects. This is what we looked at in machine learning 5G. Machine learning 5G analyzed use cases around these 3 concepts. But now what we see is that you have a cloud, and in the cloud, it is subsumed that there are knowledge, there are experiments, and it is deployed in the cloud. The knowledge is generated, experiments are done, and it is deployed in the cloud. So I think it is quite interesting scenario. And we have this quote from Qualcomm, which says that continual improvements through self-learning is the key. And this was also quoted in Ono-san's hosted webinar with our colleague from Deutsche Telekom and Oran Alliance, Alex Chua. It's very interesting perspective. In this session, we have Ahmed, Professor Ahmed from Arizona, and he will talk about multimodal sensing and to digital twin assisted communications. He is also hosting a very interesting challenge. If you are not familiar, you should look at AI machine learning challenge from Ahmed. It is a very interesting challenge. Shilin will join us remotely. She will talk about architectures and platforms enabling AI in 6G. Jose is here. Jose will talk about forging networks of tomorrow, leveraging deep learning for mobile network planning and operations. Really interesting talk. I was going through his slides yesterday. Very interesting. Paul is the backbone behind focus group autonomous networks architecture. He will tell you a lot more details about autonomy in networks, and that's why telco must stop solving problems. Then who will solve problems? That's up to Paul. We'll listen to him. Next slide, please. The last session. So the last session is the one which is most interesting. So in 2017 and in networks, what we saw is that we found that, you know, engineers reported problems, they fixed it and tested, and they were those solutions were tested and deployed. But in future, what we would see is that problems are discovered proactively, and there are ML models which are found and trained to solve those problems, and they are tested and deployed in the network. So this is what we are seeing, which is coming. And again, I'm quoting Alex Chua. You can see there, ChatGPT generated software programs for network automation is the key, which is coming. These are not my words. You can listen to the webinar. Ono-san hosted the webinar for us with Alex Chua. In this session, we have Fatih from DU. He will talk about future of standards in AI machine learning. Frank is here. Frank from Nokia Bell Labs. He will talk about AI machine learning in Wi-Fi. Karim is here. Karim will talk about driving telco innovation and business growth. I think this is a very interesting talk as well, talking about cloud native and AI. Professor James and our colleague Fidel, they are both here. They are from universities in Nigeria. We are great collaborators for a long time now. They will talk about what is developing nations perspective for leapfrogging to next generation. This is a very interesting talk of building upon the collaborations that we had. Next slide, please. Okay, so what would be the future steps? Let's listen to these experts and let's see what they have to say. There is a concluding session. Bilal is here, so we will have a concluding sessions, picking up the pearls from these talks from these experts, and Bilal will give us those pearls at the end of the day. Don't miss that. We will derive the next steps from what you tell us. Okay, so thank you so much, and let's get to the first talk. Can I invite Vemon, please?
Okay. Good morning, everyone. And now, how grateful I feel to have the opportunity to be here to talk about the open source opportunities in AI-enabled 6G network. And first piece allowed me take a few moments to express the appreciation to ITUT to give us the activity to talk about AI and the 6G network. And the second, I would like to express my high respect to Dr. Reinhardt for his great contribution in AI and 5G over the years. And today I will talk about the open source opportunities in AI and the 6G network. Today we have finished some AI in 5G network research, and this figure is the typical framework of the autonomous network. On the right, we find AI platform, and the AI platform provides data training, model marketplace, and the reasoning platform for the network. And the AI engine can be deployed in the cloud. It is the centralized deployment, and it can be also deployed in single domain, and such as wireless, transport, and car network. And it is also it also can be deployed in the terminal. For example, the cloud and the network integration and the last mile of the network. And then that is AI for 5G network. But we have many useful output, not only from focus group machine learning 5G, focus group autonomous network, but also the contribution from other standard organizations. And how about the AI technologies for AI for the 6G network? And this figure is cited from ITUR completed vision recommendation for IMT 2030. And we certainly find the AI in this figure. And it is called integrated AI and communication. And what does it mean? I think in AI in 5G or machine learning in 5G network, we usually use AI as a tool to applied as a tool to facilitate the network to achieve autonomous management and operation. And in 6G network, I think we should move the AI capability into the network itself. So the network will provide the capability for AI model training, inference, and etc. So the AI in 5G network, we call it AI-based system. And in AI in 6G network, it is named AI native system. And what is AI native system? I give the term of AI native. AI native is the term used to describe technology that is designed and developed with AI capabilities in mind from the outset. This means that AI is integrated into the core of the technology, and it is not simply added as an afterthought. So AI native technology is often more efficient and effective at performing tasks that require AI, such as natural languages, processing, and computer vision. And this paragraph is not written by me. And do you know where is it from? It is from ChatGPT. So I think ChatGPT is very useful for us to highlight our thought today. So I use ChatGPT to tell me what is AI native. And I think this is very accurate for the definition. So the next I would like to give some steps for the AI, the network transforming to the AI native network. As we know, the AI in 5G is AI for 5G, and in 6G, the 6G network provided the capabilities of AI training inference. So it is called 6G for AI. So let's have a look from the bottom. 6G network for AI, 6G network should provide the excellent network capabilities for AI, such as low latency, massive connections, and etc. And then the network should provide the knowledge graph for AI. And the knowledge graph is not only for telecommunication knowledge graph, but also the generic knowledge graph and the other industry knowledge graph for AI. And these are the basis of for AI training and other things. And then the step 3 is the network should provide a computing force or computing power for AI. And the 6G network will become a new infrastructure for computing force. So this computing force is the very key issue for AI training. So 6G network should have this capability. And the step 4 is it's about the large model. 6G network should be deployed with the large model. It is not a language large model, but the telecom industry large model should be deployed in 6G network for the autonomous operation and optimization. And then the step 5, we will achieve AI native network. So AI native work will include in computing force data, a knowledge graph, and the AI workflow orchestration and management, and support these the services capability of building AI application in network infrastructure. So the next I would talk about the AI open source. I say AI is born for open source, but why I give this answer to you? As you know, we now have many excellent open source projects around the world, such as Android, MySQL, and OpenStack, etc. And the feature, the common feature of this project is that the number of the developers of this project is very big. So if a project will be successful, it should have a huge amount of developers and a wide application in every industries. So this figure is cited from a survey of China Open Source Development Blue Book 2023. So in this figure, we find about 45% of the developers are interested in AI technology. And 34% of the percentage of the developers are interested in programming language and etc. So the number of developers in AI is a very big number. So that is the ceiling of the development of AI open source project. So a big name from Apache Foundation said community over code. That means the community, the ecosystem, the community can build an ecosystem, and the community is is more significant than the code. So I believe that AI is born for open source. That is why. So in this slide, I would like to list the two trends for AI open source. There are so many trends in AI open source projects, but I just list two of them. And the trend one is from AI framework to AI tools. We have many, there are many AI frameworks, excellent AI works in the world, such as the PyTorch, TensorFlow, PaddlePaddle, MindSpore, and etc. So I think that is enough for us to get the AI framework today. What we lack is AI tools. I think AI tools is helpful for enterprise or society or the country to achieve the digital transformation. And I think the AI tools is needed in the future. More and more AI tools are needed in the future. So this is the trend one, and trend two is open source code to open source model. And AI is not only open source code. There are three aspects in AI open source. Open source code is one of them. The other two aspects is data and computing force. If a person get the open source code or open source model code, that is meaningless for people. So we also need open source data and open source computing force. So I think the second trend of the AI open source is from open source code for the framework or the tools to open source model. You know, the famous open source model platform Hugging Face is become very popular today, and we have many open source model on that platform. And the open source model looks very excellent, but it still has many challenges for open source large model. Let's look from the bottom. And the first challenge is, what are open contents? I just mentioned open source model is not only code, but also the computing power and the data. So for 99% of people, the source code of GPT-4 is meaningless because they don't have the data, the training data, big data, and they don't have the if they don't have the computing force, they can do nothing. So this is the first question and the challenge. And the second is, what are the business model? How company earn money from open source large model? So I think the large model can be considered as the artificial intelligence applications. So the platform we know operation system and OpenStack cloud computing can build a big ecosystem, and the company can earn much more money from these ecosystems. But what are the business model for open large model? So that is the second challenge. And I think this determines the motivation for company to share their large model. And the third is, what are the licenses? Because because the model is not only the open source, but also the data and the computing force, computing power, and the current license. I think they are not compatible for open source model, because that is just for the open source code. So what are the license for the future? We open the large model should apply. So today I find that many organizations has done some researches on the open source model license, and let's look forward to that new thing. And this slide, please allow me to take a few minutes to introduce what is RFAI and the data. And fortunately, I was elected as the chairperson of Linux Foundation and the data in last month. And what is RFAI and the data? RFAI and the Data Foundation is a project of Linux Foundation. And it supports open source innovation in AI, machine learning, deep learning, and data open source project. And the RFAI and the Data Foundation was created to support numerous technical projects within this important space. And the figure is the landscape abstracted by RFAI and the data. In this figure, we find more than 330 projects in this figure, and more than 2 million GitHub stars. And we have more than 40,000 developers around the world, and the funding organizations exceed more than 180. And the line of code, we have 5 million line of code, and every week we generate 1 million line of code. And the contributing organizations is more than 1,000. So, but these projects are not belong to RFAI and data. RFAI and data now has about 60 projects, and the membership, we have 46 members today. So LLM, the large language model committees in RFAI and data. We initiated LLM committee last month in RFAI and data, and we solicit for the project of data sets, model architecture, pre-processing code, training code, evaluation metric and benchmark, model weights and parameters, supporting libraries and tools and document. And our mission is that the core LLM elements to contribute to the open source AI community's collective knowledge to foster collaboration and accelerate progress. So any person and any company are welcome to participate in LLM community in RFAI and data. And then I would like to talk about the 6G large model. And there are many opportunities for 6G large model in the future. So today, the large model is mainly for natural language. But in the future, I think the trend is industry large model will be more and more significant in our in the future. And we, from the generic large model, for example, the language large model and the telecom data mining, and in telecom industry, and the telecom knowledge graph, all of them will build a telecom industry large model. So AIGC plus MMKG. MMKG means multimodal knowledge graph. It will accelerate the innovation of network intelligence. I think that this is the beginning of our research on this field. So welcome to have welcome to have more and more discussion on this topic. And at last, I would like to give a proposal. Since the AI technologies has changed over the years, and we moved to the large model era. So there are many differences between the AI before and the AI today. So I would like to propose the ITU, the people at ITU to discuss the potential research for the requirements, architecture, use cases on AI native 6G network. I think, and the telecom large model, I think this is a very important, significant topic we should talk about. And together with open source community, I think open source grows rapidly, especially in AI field. So it is very important to connect together with open source communities to talk about the AI in 6G or 6G for AI. We are working together. I think that is a very good solution for the next work. That's it. Thank you. And that's it. Thank you.
Thank you so much, Wemong. I have a lot of questions for Wemong, but let's just hold those questions. Sally is waiting. We have a discussion session at the end of the presentations. Wait for half an hour, and we will have the discussion sessions. Hold your questions. Thank you, Wemong. And we had quite a bit of discussions with Wemong during Machine Learning 5G, and we look forward to your guidance for the 6G. Thank you for talking about native AI, 6G, and the proposals. It's very interesting proposal that Wemong had. Thank you, Wemong. Can I request Sally, please?
Hello, everybody. Thank you, Wemong, for your presentation. I think that's a very important topic, especially like when you presented AI native, it made me think about the security that we used like for software previously. It used to be like you design your software and then you integrate your security aspects afterwards. Then security-based software design has become a paradigm. And similarly, I think from AI-based networks to AI native networks is very important. Hello, everybody. It's great pleasure to be here among professionals who are well-versed in machine learning and its applications in telecommunication networks. My name is Salih Ergüt. I am serving as the lead of data science, R&D, and strategy at Oradata. Before I move on, let me actually talk about the structure of my talk. I will be providing a brief update or a summary of Oradata, what we do, and then introduce some of the concepts in MLOps and their applications, how they are relevant for the telecommunication networks. Then I will be talking about some challenges in deploying ML models into production and how we can leverage MLOps for the telecommunication networks. I'd like to discuss some insights for operators, especially when planning for the move towards MLOps, and I will be concluding my talk. A brief summary about Oradata. We are a technology consulting company. working with our clients from multiple industries in assisting them into their digital transformation journeys. These industries include telecommunications, finance, e-commerce, manufacturing, oil and gas, and other industries. We are Google Cloud Premier Partner, the largest in Turkey, and we have a great presence in the Middle East. We are also we have partnership with other vendors in terms of data, machine learning, and big data solutions. We are around 120 employees, most of whom are technical people, data engineering, cloud engineers, data science, DevOps, and software engineers. In terms of the telecommunication networks, I'd like to also mention that we have been working with multiple operators in terms of implementing AI solutions. And recently, we are going to be implementing like more than 20 use cases in different areas for an operator in Middle East. I will not be able to disclose names yet. In network operations to finance, customer experience, and marketing and sales areas, use cases. I mean, we are seeing that cloud is picking up a lot in the Middle East. The cloud transformations are actually speeding up, especially with the introduction of data centers in the region, which allows organizations which are regulated in terms of their data to be able to use these cloud services when they have data centers within their boundaries. Having said that, before actually talking about MLOps, as you all know, the machine learning is very important in the telecommunication networks, and we see a lot of use cases ranging from network optimization to resource allocation. And improving customer experience and service quality, especially in the era of 5G and as we look forward to 6G, we see that the network is increasing, the network complexity is increasing tremendously, which needs intelligent systems to manage and optimize these networks. Telecommunication networks have their own set of challenges, ranging from requirements for low latency, high reliability, and lack of standardization in terms of implementing ML solutions. I mean, especially taking the concepts from the DevOps teams, MLOps has a great potential for implementing this or assisting this machine learning models into production, especially in the telecommunication networks. So let's discuss some of the challenges. Implementing machine learning models in telecommunication networks do not come without its challenges. To start with the low latency processing, as you all know, the telecom networks are inherently sensitive to time in terms of providing decisions. And when you are considering use cases such as real-time traffic routing or network slicing or real-time fraud detection, this type of low latency processing and providing decisions in the stringent time requirements becomes very essential. And also telecom networks are, they have a distributed architecture, and this, like from base stations to edge networks to data centers, gateways and routers, etc. So it is important to be able to manage this scattered ML models in this distributed architecture. And it's important to be able to scale based on your increasing traffic in this network. Most of the operators' network is comprised of a diverse set of hardware and software modules. And without having any standardization between these components, it's hard to implement certain use cases. And at some of the operators, we see that they are working in siloed structures where collaboration can be limited, and the data is owned by certain departments, so it is hard to provide a collaboration environment where different departments can work together, from IT to network, or even different departments within these organizations. So having said that, maybe we can introduce what we define by MLOps. MLOps is a multidisciplinary approach in bridging the gap between the model deployment, model development, and deployment in production environment. It actually combines the best practices from the machine learning and DevOps organizations. As you are all familiar with, DevOps organizations automate, collaborate, promotes automation, collaboration, and integration between software and operation teams. Similarly, MLOps frameworks automates the end-to-end ML lifecycle and promotes collaboration between different teams, from data scientists to operation teams to network engineers. So to address challenges in deploying and maintaining ML models, it's important to streamline workflows and increase the reliability and the performance of machine learning models in production. Especially when we are talking about telecommunication networks, which is already complex and it has a distributed structure. It's important to implement MLOps to help in this type of settings and to address the requirements or needs for low latency, high reliability, and scalability in these environments. What are the main functionalities of MLOps? This is not like different departments actually, or different solutions have different implementations for MLOps. But when you are actually looking into general overview, you can see that one of the important key aspects is data versioning and management. So you are actually working with different sets of data and different timestamps, and you would like to be able to version them. And especially when you are doing model development and experimentation, you should be able to track both data or your experiment and your artifacts from this experimentation. Similar to DevOps, version control tools and collaboration tools are important for the MLOps frameworks. You need to be able to train your model in an automated fashion. Basically, you need to be able to select different models, and you need to be able to do hyperparameter tuning, and preferably in a distributed architecture, so that you can try multiple things in short amount of time and better use your resources. Model packaging and deployments are important aspects. Basically, you need to include all the dependencies. So like different type of frameworks are used for machine learning implementations, and it is important to be able to package them so that you are not dependent. You can just run it in anywhere in your network. Model monitoring and logging is very important. So you need to be able to provide the accuracy or other metrics, performance metrics. You need to be able to monitor changes in your data distributions or the concept drift, maybe the input-output dependency has changed. And it is important to be able to do load balancing and to be able to handle and scale large traffic. Continuous integration and deployment is an integral part of these frameworks, where you should be able to iteratively make improvements to your models, and especially when they are going down. And finally, the model explainability and fairness is very important, especially for the regulated industries, such as telecom or finance type of industries. So most of the frameworks support tools for handling this type of functionalities. And maybe I should also mention the feature stores for the data versioning part. As I mentioned earlier, different organizations within the same company may have different definition of certain features. So it is important to have a common understanding across the company when you are working on different machine learning models. We are working with different vendors, Google being one of the largest ones that we are working in terms of implementation of MLOps in their environment. And we are also developing our own platform, especially for those who do not want to move to cloud, especially due to regulations, and would like to implement on-prem. So we are working on an open source solution, which has been actually implemented in some of our customers. Talking about MLOps, I think we cannot proceed without mentioning the MLFO. Vishnu, one of the major contributors of this platform. This was an architectural concept proposed by the focus group on machine learning for future networks, including 5G. And at that time, it actually intended to standardize and streamline the ML developments in telecommunication networks. The main requirements that it was trying to address were from model management to data management, the pipelining concepts, and it had closed loop systems. Like intent and policy management is, I think, one of the pioneer aspects, especially at that time it was much harder, but now we have these large language models. I think intent is like identification is more manageable now. And it had some limitations in terms of like its interactions with some network functions. And it was specifically for the telecommunication network. It addressed the needs of the telecommunication network. So this is one of its strengths. And also we can maybe consider some limitations when you are talking about machine learning systems. Now you are seeing more and more generalized systems that can address multiple industries. So using MLOps in the telecommunication networks provides certain benefits for telecommunication networks. First, it improves its model quality. Basically, you have a lot of testing, monitoring integrated into these frameworks. You can try multiple models and etc. So you guarantee the model quality and you make changes if needed. With it is templates, streamlined or workflows, implementing ML solutions and bringing them to markets in very quick time is very possible. And as I mentioned earlier, like the siloed environments in telecommunication networks can be overcome by the increased collaboration environment in terms of like versioning of data, versioning of models, monitoring them. It can bring multiple teams together, and it can standardize the interfaces through best practices and approaches from different standards, including like the DevOps or MLOps own best practices. So when we are actually going through 5G, I mean, as you know, 5G is provides high bandwidth with low latency, and it provides a large amount of devices in the network. Some of the main use cases, such as like network slicing, provides virtual networks for over the same physical infrastructure, and managing and optimizing resources for these virtual interfaces has to be in real time. And the ML models needs to be able to implement this in real time, predict their predictions. Some use cases such as autonomous driving or like remote surgery type of use cases requires very low latency and high reliability, and implementing your models on the edge helps you with the low latency requirements, and having like a lot of continuous monitoring of your models also helps with the reliability of these use cases. As we are moving towards 6G, we are seeing like the need for more data is going to be increasing a lot, and the network complexity is going to be increasing a lot as well. So as we are moving towards 6G, it is important to have like this type of practices when we are implementing our models in the network, and especially when we want to design AI native networks. So let me actually skip this slide. I mean, as I mentioned, 6G. I'd like to talk about the generative AI technologies, especially in the context of MLOps. Like, especially using very large language models, we can optimize, we can choose the optimal pipelines or models or algorithms and hyperparameter tuning using these algorithms, which has some, I mean, promises over there. Especially when you are dealing with data, sometimes you may not share data, so it is good to have a synthetically generated data to share with different parties, especially due to privacy and etc. Or sometimes in cases where you may have like the data imbalance, you have certain sets very low, so you can generate new data, synthetic data to I mean, skip that type of problems, address that type of problems. Explainability and fairness, as I mentioned earlier, there are different frameworks that can handle explainability of ML models, but these are usually in the form of providing certain weights or providing certain features as being important in the decisions. Providing a natural language in terms of explainability of models will actually increase the overseeing of these models and implementation of these models. As I mentioned earlier, we are in development of our own internal MLOps framework, and this is one of the additions that we are working on, the first and the third one, integrating LLMs into this framework. And especially when you are considering large amount of logs created from the telco operators, it is, I mean, models can learn from this type of logs a lot, and then we can incorporate that into our models. And especially you can try out different scenarios, which is probably hard to see in real-time deployment. You can have synthetic data here as well to do testing and validation of your network for edge cases. So when telecom operators adapt MLOps frameworks, it's important to first assess what they have, how they model, how they deploy their models, and how they monitor it. And by first assessing this, they can see where they are lagging behind and where they need some automation, and they can actually set some clear objectives when implementing this type of solutions or frameworks. One of the key aspects of MLOps, as I mentioned, is the collaboration between teams. And with well-designed workflows, you can bring like business teams, data scientists, ML engineers, network engineers on board, and then they can work towards your goals that you identified first. There are many ways of implementing MLOps frameworks. You can use certain open source components. You can use some cloud actually providers. You need to decide on the technology that you want to use. Sometimes not the features of the framework, but being able to not do vendor lock is important for some operators. So as I mentioned, our platform, we are targeting those customers who do not want to move to cloud. And some of our customers who are already in cloud also prefers our platform because they don't want to have a vendor lock with the platform. If they move from one cloud provider to another, they should be able to move everything. And we need to be able to set the continuously monitoring these models, performances, and have the closed loop, feedback loop, so that when we see some degradation in performance, we should be able to provide iterate in terms of our models, do corrections when they are required. So to conclude my talk, like I mentioned about what MLOps is and how it can help the telecommunication industry, especially when we are moving towards 6G. I think it's important to embrace the MLOps, help in terms of handling network specific challenges. And I think that MLOps frameworks will be able to help the requirements, operator requirements in terms of latency, distributed architectures, standardization, reliability, and etc. So it is, I can say that the MLOps is going to be part of future networks, telecommunication networks, in achieving this type of goals. Thank you.
All right, thank you, Sally. It is difficult. It's extremely difficult to be a startup, but he's here. So yeah, thank you so much for coming. I want to ask Sally about his journey from Tuxel to the startup. I want to ask him about LLM ops. I want to ask him about the cloud aspects that he mentioned. But please hold on to your questions. Please hold on to your questions. We have Abhishek, he's waiting. And after his talk, we have a session for discussions. So please have your guns all loaded, and we are all set. So Abhishek will talk about smart interfaces and AI native approach for control and integration. This talk is in discussion with Slavomir. Slavomir unfortunately is not able to make it, so we will have this talk in discussion with Slavomir.
So hello everyone. So originally, as Vishnu said, Slavomir was supposed to be here to give you a broad overview of what we are doing. Unfortunately, he's not here, so I will, instead of giving a broad overview, I will focus on one aspect of our work, which is smart interfaces. But I will just give you a brief idea of what is Fraunhofer. So Fraunhofer Society is a collection of 70+ institutes in Germany, We focus on applied research. So I'm from Fraunhofer Heinrich Hertz Institute, which is based in Berlin. We focus on mostly with telecom, but now also in AI. We are from the wireless networking department. I am a researcher there. We currently are working on multiple 6G projects. So you can see one of the project 6G RIG, which is one of the major 6G hubs funded by the German government. We are focusing in this 6G RIG project, we are focusing on various aspects of future networks. So reflecting surfaces, AI-enabled air interfaces, more, let's say, more radio level things, but also we focus on more higher level, higher level technologies. So we just to give a broad overview of what kind of things we work on in this project, we are working on semantic communications, where there is some work on a variable sampling to achieve a freshness of information. Then we are also focusing on how to send or rather how to communicate, semantically communicate data. So for example, if you have an image of a black cat, then how do you send it without actually sending the image? You just send the concept, for example. And then we are also looking into how to manage split neural networks in 6G networks, etc. But for this, because I don't work on all those things, Slavomir would have told you better, but I only work on this. So I will focus on this smart interfaces. Yeah. So if you look at the network interfaces today, they are basically channel of communication between network entities. So you can divide them up in control plane, management plane, and the user plane. So for example, E2 in ORAN, or it's a kind of a control plane interface, you can say. Then you have O1, and then for management, and then you can say N3, which is like a user plane interface. So this is only the high level classification, but if you go deeper down, you see that actually you can divide them even further. So these planes could be divided into, let's say, structure plane, what you call data structure plane, which is S plane, and the information plane, which is the I plane. So the data structure plane is, this consists of the data structures for control and management messages. So for example, in case of control messages, this could be the syntax or the structure of the RPCs which are sent to control something. Or in case of management messages, this could be YANG models or the E2SM models or MIB models, which are defined by 3GPP, through which you can manage your network devices. And traditionally, this structure plane is defined by or standardized by SDOs and vendors. Then you have the I plane, which is so this is basically, if you have like a data model, then you also need to assign some values to the individual keys of this data model. So this values is what we call the I plane. So for example, if you have a key in the data model which says 5G QoS identifier, then you need to assign a value to this, which is 3 in this case. So this would be the I plane, the information plane, which actually gives the value to this data model. And this I plane, these values are values are generated typically by a decision-making algorithm, like for example, an XAMPP. These are not, of course, I mean, these are dynamic, so you need to generate it according to your requirements. Now, ideally, these two planes are supposed to be aligned. I mean, they are supposed to have symbiotic relationship. So you define a data structure and then you use it in your network and all is good. But in reality, there is a problem. So this data models might define some keys and variables, which some vendors might not be interested in exposing, or they might not even exist in some specific cases, like let's say non-terrestrial networks. So, and similarly, you can have I-plane applications. So for example, you have an XApp which needs to send a particular value, but that variable does not exist in the data model. So I mean, or such model is completely impossible to use. So what you can do is you can do customized data structures, but then you have problems of compatibility, adoption, standardization, etc. And the reason why this is happening, at least one of the reasons, is that the iPlanes are getting intelligent. So you have AI-enabled XApps, AI-enabled RApps, and yeah, and but if you look at the data structure planes, they are in this, I don't know, like 10, 20 years ago, how they were. I mean, they are like very rigid. They are defined on paper, and then that's it. They cannot be like variable or dynamic. So we need to make this data structure plane intelligent. So how do we do that? Then is basically we need to make intelligent production and consumption of this data structures. So here you have a simple example. You have a controller and you have a network element. So to make it more real, you can imagine this is a near RT rig from ORAN, and you have a CEO or a DU as a network element, and it's sending a control message to do some operation. So ideally, you would use a data structure defined in E2SM models or something, or O1 models. But if you want to have intelligent S plane, data structure plane, then what you need to do is to generate application specific data structure, and then assign this values using your application and then send it over. But then this creates the same problem as I said in the previous slide. This is like customized data structure, and it's non-standard, and the network element will probably not understand it. So what you also need to have is intelligent data structure consumption. So the green part. So once you get this message, the network element needs to do semantic message parsing. So what I mean by that is it doesn't just match the incoming message against a predefined data structure. It actually understands the message. So how the large language models actually understand what you say in your prompt, and it's not like a pre-coded or a rule-based approach. And once this message is passed, then you need to do also code generation, which also needs to be AI enabled, of course. So how do you produce data structures? I mean, this kind of customized data structures. So one way of doing is using this large language models, because data structures typically use natural language, and language models are good at this basically. So what you can do is you can say, I want to create a data structure or a data model for creating a new slice. And this telecom tuned language model should be able to generate a data structure for your specific prompt from the application. And then on the consumption side, when the receiver receives this message, it as I said before, it should not just decode. So right now what happens is, when you have an incoming message, it has certain stored structures in its memory. It does kind of mapping or matching between those, and if it recognizes that this is the message of this structure, then you have to do this. So this is all rule based. This is hard coded. You can't really do anything right now. But now we need to do a more intelligent parsing of the message. So the receiver needs to understand the meaning of the message. So this is where the semantics come in, which means that it needs to semantically understand the message, like how I would say something to you and you would understand, not because you already know what I'm going to say, but because you know the English language, and that's how you understand. So once it understands this message, it has to also generate corresponding code, because today you have code which is already there on the device, which is hard coded. But in this case, because this is a new message, you also need to generate code which can actually implement the things or the operations which are being specified in this new message. Which again, this is where the large language model would come in and generate a piece of code which would perform this operation. Yeah. So what can we use this for? So there are several use cases. We can have multi-vendor deployments. Right now, we know there is a problem with integration of multiple vendors in ORAN. So what you can do is you can deploy different DUs, for example, which might not be strictly complying with E2, and you can have like a third-party rig and like a XF from a fourth party maybe. Because the interfaces don't need to be strictly matching to the standards. By the way, this will have impact on standardization, of course. So right now, what standardization does is it defines data models or control structures on paper. But I think in future, the job of standardization bodies would be to define high-level concepts, like, for example, what is slicing, but not define the exact parameters of how to create a new slice. I mean, that could be done using this kind of systems. Then you could have something like interface on demand. So if you look at again ORAN, you have this north to south interfaces, but you don't really have east to west interfaces. So for example, if you want to have a cell-free network, you have multiple DUs and you need to coordinate between these DUs for enabling cell-free networks. Such interface currently does not exist. I mean, what you could do is you go to ORAN Alliance, put in your time, effort, and maybe one day you will get such interface. But I think 6G networks are much more dynamic, and we need to have something which we can create on the fly. So I think this is something which is pretty possible with this kind of an AI native large language model based approach. So yeah, I mean, future 6G RAN may not need this kind of predefined interfaces which we have, which complicate things even more, right? There might be some disadvantages of this as well. But these interfaces can be created on demand according to the requirements. So, and I think already covered the role of SDOs. So what we are investigating is we are trying to do, we're trying to explore what kind of large language models could be used. So you have the proprietary LLMs, of course, like GPT, but then you also have open source LLMs, which are more interesting for research, of course, like StarCoder, Vicuna, WizardCoder, etc. And we plan to use this with gRPC based interfaces to actually try to do some minimal control or management operation where the interface is not defined, and with this we like do this on the fly. Yeah, so that's it from my side. Thank you.
Thank you, Abhishek. You know, I want to ask Abhishek about what he told about SDOs, the role of SDOs. I mean, he has very quietly put us all out of the picture, actually. So I think that's quite interesting. And I want to ask Wemong about what he told, because if you look at one cloud implementation, cloud native implementation of what Abhishek just now explained with open source, then what's the role of a lot of people? I'm not very sure about it. So I think it's an interesting future. It's a question that we should discuss. Now at this point, I would like to open up for discussion. I have a long list of questions, but that's not important. What is important is that we should probably ask these guys about what you heard today, and maybe prepare for the next stages, that the proposals that what they had as well. We have maybe 25 minutes or so. After this, we want to make sure that you are all fed and watered for the next session. So we have a coffee and coffee break and so on. So that is important. So we should probably take 25 minutes now and fire away. I think if you have questions, please, this is the time. It's very difficult. Yes, Cesar, please.
Yes, thank you very much. Good morning, everyone. I'm Lee from Qualcomm, Switzerland. Very interesting discussions. I have a very fundamental questions, actually. So AI native network sounds very nice, but I believe this all network elements have something associated with AI functions or features in all the corner of these network elements. Possibly AI between the different AI features, they may organize logically overlay AI networks. If not the case, one of important aiming for use of this AI like network optimization, resource reservation, it might be very difficult. But many of you already talk about 6G. When I see of this ITOR recommendation, it's announced a couple of weeks ago, 6G latency, or this sensitivity is quite high, like 0.1 millisecond until not more than 1 millisecond. Even the mobility is 500 kilometers or 1,000 kilometers per hour. So sounds very nice, but how this AI will take into account of this all requirement from bottom layer networks, bottom physical or logical networks, how this collaborate to meet of this, to support of that, especially taking into account AI is by nature open source, and also something the last speaker say about interface maybe not defined, but on demand requested. Such nice features, how you guys work together. What is the role of this? How to reach of this common goal over SDOs or any activities? If you share this, it would be great. Thank you very much.
Thank you, Cesar. Sally, would you like to take that, please?
And maybe I can actually talk about the MLOps part, and then maybe open source parts can be different. I think that is very important. Currently we are in the process of defining the frameworks for MLOps, like maturity levels, like from level 0 to level 1, to different organizations define it differently. Like the latency requirements, it will actually require to have this edge networks to be implemented, and you need to, especially thinking about your ML models, you need to be able to coordinate them and run them in a distributed architecture on the edge, so that you can actually meet this stringent delay requirements, and you need to have this feedback mechanism to monitor your model. So it will be very important. How implementation is quite challenging question. So it will definitely needs to be considered. The current focus is mainly on the current challenges, but for 6G, I think we need to work more closely in terms of achieving those requirements.
Raymond, would you like to add something?
I think ITU should be a platform for the standard organizations and open source communities to collaborate with each other. And for the question about the latency of the 6G network, I think this is a typical use case. Our problem we should address in the future. We can discuss furthermore about this question in the future. Thank you.
I think what I understand, Jessup, is that there are offline and online use cases. Real time and non-real-time use cases. So real-time use cases, in my opinion, there are optimized models which can maybe do it, maybe in XApp, like Abhishek explained, and there are, Shilling will explain in the afternoon. I think there are use cases like that which are handled by smaller models and optimized models in XApp real time. Currently, if I understand right, it is less than 1 millisecond that we are looking at. 6G, I don't know, but we can probably study that as part of the next studies that we can do. About there is training that model training that we could potentially look at, and generation of interfaces, as Abhishek explained, and the generation of code and the network functions and other artifacts which we can look at. That is offline. So there is no real-time constraint there. I know that the Sally is working on potentially commercial use cases. So I think I would value what he's saying. And also I think we have other speakers. I think Professor Tom and Shijong are here. They have real time, real use cases which are applied as well. So definitely there are applications, but I think we have to have further studies in this area. Abhishek, you want to add something, please?
Yeah, so for a moment, if we keep AI aside, I mean, just to focus on this typical metrics of latency and bandwidth. I mean, if we look at this kind of let's say some specific campus networks, so we have this non-public networks, which is like industrial 5G or private 5G or whatever they call it. I mean, some of them have very different requirements. So some of them might be more interested in the freshness of information, or what is called age of information. So basically, how fresh is the piece of information which you are getting, which is different from latency. So historically, we are always focused on lower latency, higher bandwidth, etc. But future networks, I mean, some of the future networks may not actually have this requirement. I mean, they may not have, in the sense they would require some low latency stuff, but they will have some other requirements which we might want to focus on as well.
I think the question is that we have to distinguish Chesap's question into what are the network requirements and what are the model requirements. I believe that's important. Professor James has been waiting very patiently. Yeah, Professor James.
I think you can hear me now. Thank you. My name is Professor James Sagajo from the Federal University of Technology, Mina, in Nigeria. Very wonderful discussions from contributions from the presenters. And actually, there's this area you delved on. I like so much. And I want you to probably shed light on it. To the first speaker and probably the second too, he did talk about that. When you talked about the LLM models, in the case of the first speaker, he talked about LLM DevOps and stuff like that, bringing the concept of DevOps in LLM. So I wanted to, because I believe the marriage is going to be wonderful if it's realized well. So we could just shed more light on that, so we could probably carry on from there. Thank you.
Thank you. I think that's a very important topic. I mean, we are talking about DevOps, DataOps, MLOps, and as Vishnu pointed out at the end of my talk, now LLMOps is being considered. Like the ChatGPT has made a great impact on how we are considering this type of models, but it also has its downsides. Like you all might have heard about Samsung's, like the data source code being revealed, etc. So like we are amazed with it now when you are considering the enterprise implementations, you are more interested in having your own data sets being used, not being leaked, and it's contained within your cloud environment if you are using it. So there are, especially like the cloud vendors are working towards that. I mean, since we are working closely with Google, I can maybe comment on their implementations. They have a Gen AI suite where you can implement this type of large language models. I mean, multi-models like text, image, or audio in your own settings, and you can ensure that it is easily implemented. It can integrate with multiple applications, so it can be pipeline similar to MLOps, and you can easily integrate into different applications like web-based applications or internal applications like network monitoring applications. So this is becoming very hot, and I think that is what it will be able to implement or bring the LLMs into the enterprise settings. And this type of frameworks allow you to use multiple large language models. And I think that's one of the important aspects is you don't always need the most complicated large language model if you're just doing some classification of certain intents, which is very limited in terms of categories. So you can go with small ones, and then you can just do this type of changes between different models. And they allow this type of like migrations as well.
Thank you so much. There is a bunch of questions online. Let's take a look at those questions online. There is Uttara, thank you for joining. She's asking if XApps are associated with iPlane, what will R apps be associated with?
Yeah, XApp is just an example. Okay, so all of these decision-making apps, doesn't matter where they are. It can be in ORAN or Wi-Fi or a satellite network. Any app which makes a decision and sets a value to certain variable, it's basically in this information plane. So I was just giving an example, and I can also address this another question. Okay, so the same person also has asked, how do you propose handling intense memory requirements for LLM? So I think this is a huge, this is something we should really think about. Right now, it's just, we know how much GPU it takes to kind of run something like GPT or even open source models. But I think in future, this will come down. I see this definitely happening because you cannot really keep doing what they're doing right now. But yeah, this is something we need to think, where will these models reside? If we have a network, then where is this compute where the models would actually do these things? Maybe one day we will have small enough models to fit on your own device, but who knows? But right now, yeah, it's something to explore.
Thank you so much. That's a great question. Maybe Bemong, you want to answer this question from Uttara about cloud native. There is a process to achieve cloud native, yes, but how do you approach enabling AI native?
Where is the question?
At the end.
I just find the question, the last one. Okay. I think AI native network should be integrated AI capabilities. For example, the computing force and the knowledge graph. The knowledge graph not only for telecom knowledge graph, but also the generic knowledge graph and the other industry knowledge graph. So I think the how to achieve the AI native, I think we should redesign the AI network, AI elements to ensure they have the ability to provide the computing force, computing power, and the huge amount of data for AI training. And we don't need the external AI platform or AI engine or AI AI framework to do the AI training inference. We just to do this work or these tasks in network itself. So I think this is I would like to propose to achieve this goal in 6G network. And then the AI native network, I would like to introduce the large language model into the 6G network. For example, the top is the level of our network is intent-based network. So what is intent-based network? The intent means I can use the natural language, sound, a graph, picture to tell the network what I want to do to the network. So the LLM, the large language model, can do the thing and can do the recognize what are you intended to do to do the network. So I think introduce LLM into the network is another aspect of AI native network. Okay, thank you.
Thank you so much, Memo. Maybe Abhishek, you can maybe answer the Akshay's question, please.
Okay, I was going to put it in chat, but anyway. So yeah, I mean, this is a so we are not talking about decision making using MLAI for decision making here. So there are two different applications. So you can use AI for making decisions, which would be translated into certain sets of values, which would be sent to the device. And then you can actually use AI to create the structures of data which would be used to send these decisions. So we are not focusing. So right now, you already, as I said, this iPlane is already very intelligent. I mean, you have AI-based XApps online. You can use them. So we are not focusing on that part. We are focusing on how to use that to actually create the data structures.
Thank you. Are there considerations made on how to handle several communications rounds? Privacy and federated split learning. I think this is Frank's favorite topic. So this is about federated and split learning. Frank, maybe you can. Do you want to? Are there network overheads? That's what Blessed is asking, whether there are overheads in privacy strategies like federated and split learning.
Well, I think this is more for Wei Meng, as he mentioned these distributed architectures, and this includes federated learning and split learning, things like that. But yeah, I mean, I see federated learning as also a useful tool for fostering this collaboration, as also Sally Ergood was mentioning before. But I don't know to which extent this can be kind of the solution for solving these problems in terms of collaboration among competition or competing entities, like for sharing data models in this case. But yeah, for sure, a very interesting topic to be studied, also in conjunction with other technologies, which may be, for instance, distributed ledger technologies or other things that help to build this trust among participating entities. Sure.
Thank you. Yeah, Henning.
Yeah, I just wanted to add in 3GP SA2, there's already active standardization in the federated learning environment. Of course, the focus there is like Frank also said, more in the group creation, client selection. So really the management of the FL groups rather than the actual model exchange, basically. Yeah, but this of course will then continue also in release 19 and also towards 6G. Yeah.
Could you say that again, Wenning? Management of what groups?
Yeah, the FL group, basically group setup,
Ah.
right? I mean, first to establish federated learning, you need to create a group, right? And then all of this, what clients to select and so on. And, everything you need across the group, say, to manage the life cycle, let's say, of the group, right? And what they do is actually now they have defined what they call an interoperability token, which points then to an agreed model within the group. Yeah, but that model is not standardized actually.
Interesting. Thank you so much for that pointer. There was some question. Yeah. So what about network digital twins? How do you see the role? I think we can hold on to that question. Maybe for the next session, we have speakers. Albert is here, so we can maybe hold on to that question for the next session. Thank you. Anything else from the yeah, Paul, please.
Thank you so much. So touching on what you were saying, Abhishek, about this idea of on-demand interfaces and things, like, are we getting a little ahead of ourselves in that it's fine, gRPC can create the technical ability to have two different things communicate, that's great. But if we have on-demand interfaces, how do we specify what's actually going on? Like what's the process behind the generation of the demand to communicate with something else? Like, are we decoupling like the meaning of what we're trying to achieve here by having that capability to generate the on-demand interface?
So the demand of what kind of data model or structure you want would come from your application. So it depends on this is application specific. So if your application needs a specific variable to be set, or a specific set of operations which require certain variables to be set, then that would be included in this data model. So it's very customized to your application.
So it just to repeat to make sure I understand. So the idea is that you write your code, you write your application doing whatever it's doing, and then somehow it would decide or define or suggest that it needs to communicate with something else. And this approach would then facilitate that communication without the application having to worry about how to do that. Is that right?
Yeah, roughly, but we can discuss more offline.
Okay, thanks.
I'm going to talk about how to build a network digital twin. And my presentation, it takes actually a little bit longer than 15 minutes. So I will skip some slides, but you have the slides online and you can check, and then we can also discuss if you wish. So the first thing I would like to talk is what is a network digital twin. I believe that many people already know here, so I will go very quickly. It's kind of a digital replica of your network, right? And it can be used for optimization and analysis. I will discuss this a little bit later. So my presentation is how we can actually build it, how we can actually have one real world network digital twin. And the first thing I would like to discuss is the inputs and outputs. So the network digital twins is an overhyped term right now, and it is being used across many different fields. For instance, in healthcare, they are trying to do a digital twin of the body or of a particular organ. For the industry 4.0, and of course also in computer networks. And whenever you have a term which is so overhyped, typically what happens is that it is defined in many different ways. So it's hard to have one single definition. And at the same time, and in some cases, it has kind of an ambiguous definition. So it's a little bit unclear what a digital twin is, a network digital twin. So in what we have done is to try to at least define one network digital twin. I'm not claiming that the one I'm defining is the best one and the only one. I believe that there are many different approaches which are also equally valid. But at least this is ours, and this is concrete and specific. So the first thing we need to define the network digital twin is try to define what are the inputs and the outputs, right? If we assume it's a box, like a software box, it has some inputs and outputs. And after a lot of thought and discussion, what we thought is that the network digital twin can focus on performance. on performance means that it has two inputs. The first one is the network configuration. By network configuration, I mean all the state that it's on network devices. So whenever you type conf term and then you start typing your configuration of your network, right? You define your links, you define your link capacities, you define your topology, you define your routing, your queue scheduling, you define your protocols. This is all what I refer to network configuration. And the second thing is the traffic load. So the users will naturally, or servers will naturally generate traffic, right? Packets. And this is the second input. So, and as an output, what we envision is that the network digital twin produces the performance of the network. So basically, this network digital twin, which focuses on performance, will tell you, okay, if I have this particular network with this particular traffic load, what will be the performance of my network? Performance meaning delay, jitter, right? The common metrics. And if you think as a network, as a black box, this is what a network is, right? A network, it's an infrastructure. It's a system that as an input, it has packets. We send packets to the network. And there is a network administrator which applies some configuration on the network, right? Maybe changes the configuration of a protocol, or maybe changes the routing, or maybe changes the configuration of a 5G antenna. And as an output, what the network will do is take the packets that are coming in, transmit them, and at the end, you will have the packets going out of the network. Some packets will be consumed maybe by users or servers, but in general, transit networks, this is what they do. And also, additionally, beyond the packets coming in and the packets coming out, what you will have is performance, right? So the packets will have an associated performance. Some flows will have a certain delay or a certain jitter or packet loss. Also, the network will have a performance. You will have a particular network link utilization or queue utilization. So if you think of a network as a black box, this is the way we see it. So basically, the network digital twin has exactly the same inputs and outputs. Because it's a virtual replica, it's a digital replica, we cannot have the packets themselves, because in a network, we have billions and billions of packets per second almost, right? So what we will have is a description of the traffic, some information regarding the traffic. For instance, this can be, you have this amount of flows, you have this amount of voice over IP flows, and this amount of video on demand flows. So you have a description, but at the output of the network digital twin, we have exactly the same. We have the flow performance. Okay, so this is what we want to build. Now let me discuss a few use cases to make sure that we agree that there are this can be useful. So the first thing is that, and we will discuss this later, there are certain requirements for this network digital twin. The first requirement is that it needs to operate fast. And this was discussed in the previous session, right? It needs to operate fast because otherwise it is not practical for the use cases. And the second thing is that it needs to be accurate, meaning that the estimates of the performance that the network digital team produces should be very similar to the actual delay of the network, right, when running through this traffic and this configuration. So those are the two most important requirements. And then we can discuss a few use cases. For instance, the first one is, okay, why I need this network digital twin? Let's say that I'm running a network and my company wants to acquire another company, which means that I will have a new set of users and a new set of services. And what I wonder is my network going to be able to cope with the new set of users and services? So the network digital twin should be able to tell you this. What you will do is you will take the network digital twin and change the traffic load, because you will have additional traffic load from new employees and new services, and you will ask the network digital twin, what will be the performance of my network if I double the amount of users? And the network digital twin will tell you, okay, this will be the delay, this will be the jitter, and so on. And another one is to try to identify which is the optimal network upgrade to support a new set of users. Let's say that the network digital twin tells you, okay, the delay will be very high, so I need to upgrade the network. Okay, which link should I upgrade, for instance, to reduce the cost and achieve the performance I want? So that's another use case. And this is a little bit more convoluted, but at the end it's the same. Mathematically it's the same. For instance, you may be asked, okay, you have a new SLA, a new requirement, so you may need to know if your network is able to support this new SLA So you can ask this network digital twin, which focuses on performance, and it will tell you if you are able to do that. So this is basically the set of use cases. So now that we have somehow clear what we want to build, let's try to see how we can build it. So there are many techniques to build it. And I'm going to focus first on simulation. Okay, we want to build this box. Let's try to build it with a simulator, right? If we want to build it with a simulator, this means that this box, we are just going to code it with the code of a network simulator. It's just, we take the box and we put there a network simulator. Network simulators are common, right? OpNet++ is one. There are others like Network Simulator 3. Then vendors also offer their own network simulators. And typically what they are is discrete event simulators. Typically, what happens in these simulators is that the accuracy is very good, meaning that the delay estimated by the simulators of the packet will be very similar to the delay that the packets will see in the real network. So the error of the accuracy is very low. So they are good in that front. The problem with simulators, because we actually did that, we tried to build a network digital twin with a simulator, is that the simulation time scales linearly with the amount of events. And in the simulator, an event is a packet. So because basically a simulator, what it is doing is it is simulating the transmission, propagation, and forwarding an each of every packet. So if you take a single, let's say you want to simulate 1 billion packets, 1 billion packets will take 11 hours in a quite beefy CPU. And 1 billion packets is just 1 minute on a 10 gig link. Okay, so this means that it is not very practical to use a simulator to build a network digital twin, because what will happen is you will have a very high computational cost. It will be extremely slow and not practical at the end. So we don't think that simulation is the right choice to build this type of network digital twin. So if you move forward, there are other techniques like emulation, and I will skip this part. You have the slides, or we can argue afterwards if you are interested. Okay. Emulation, then also queuing theory, which is analytical models. And I'm going to focus on neural networks, which is what we at the end saw, which was worked best. So, and actually in graph neural network. So here what I'm trying to analyze is what happens if we want to build a network digital twin using a graph neural network. So first of all, let me explain what are graph neural networks. So graph neural networks is a new class of neural networks. And if you think of neural networks, each neural network works best for a particular underlying structure of the information. So if the information is structured in the space, like an image, this means that the best neural network for that are core convolutional neural networks, which are the ones which are used in computer vision, because they work very well with information structure in the space, like in an image, right? If you want to identify a nose, what you need to look is that at the pixels surrounding the pixels around the nose. And this is how you identify, okay, this is a nose. And convolutional neural networks were a very big breakthrough in computer vision. And the invention of convolutional neural networks are the reason why we see so many applications in computer vision, because we have the right tool to understand images. Same happens with information which is structured as sequence, like for instance, in text or speech. In text or speech, if you want to understand the meaning of a sentence, you need to understand the words and the words before that word or after that word, right? So the information is a sequence. So for that, we have recurrent neural networks, and today we have transformers, which is the ones being used by ChatGPT. And that's why we see a big breakthrough in application regarding text and voice. What we didn't have until 2019 was neural networks which were designed to learn information who was structured as a graph, which was structured as a graph. This is called relational information. Graphs are, for instance, a molecule is a graph, a map is a graph, and a network is fundamentally a graph, right? A network is fundamentally a graph. So we didn't have the right tool until 2018. This was invented by DeepMind. So now there is a new family of neural networks, which is strictly defined to learn information which is structured as a graph. That's why we choose graph neural network to build our network digital twin. And well, GNNs are right now a hot topic in AI, and I guess that you can imagine why. We have a new toy And many industries which were fundamentally working with graphs, they didn't have the right toy to play with machine learning. For instance, the chemical industry, pharmaceutical industry has put a lot of money into GNNs because they work with molecules and molecules are graphs. So finally, they have the right tool for that. It is a big topic in AI. There are plenty of papers. GNNs have helped solve a long-standing problem such as AlphaFold. So it's quite a big deal, right? And we believe that that's why we believe it's the right choice for computer networks. So then how you can build a network digital twin with graph neural networks. So this is what we did. And I want to focus now on how you train it. So the technique is graph neural networks, but I want to focus very quickly on how you train it. So the way to train it is exactly the same as any other neural network. You need a data set. You need a data set of inputs and outputs. And the outputs must be, so inputs, for instance, in computer vision, you have a data set of pictures of animals, and the output label is, this is a dog, this is a cat, this is an elephant, okay? And this is how you train your neural network. So we need to do the same with a network. And the way we do it is, we take one network, and we apply a particular configuration. Let's say it's random. It's not truly random, but to simplify, it's random. And we apply a particular traffic load, which is also random, right? It's like taking a picture of something, and then we need to label it. And the label in this case is the performance. So that particular network with that particular configuration, it has this particular performance. Okay, this is the first row of my data set. And now I need to do this thousands of times. Once I have this done thousands of times, what I will do is train a neural network, in this case, a graph neural network, so that it can provide inference for a new network configuration that has never seen in the past. It's equivalent to a new image of an animal that I have never seen in the past, with a new traffic load, which I have never seen in the past. The neural network should be able to tell you, this is the performance that you will get. So this is the animal, right? It's exactly the same. And this is what we did with RAWNet. RAWNet is an open source network digital twin. You can find it online, and there are reports, and the code is open source. And it is doing exactly what I was saying. We can discuss the inputs and outputs. It's a little bit more complex. It has many inputs and outputs, but fundamentally, this is how it works. And this is the architecture. I don't want to spend too much time on it, but there is a key insight. So graph neural networks are not a black box, meaning that it's not a code that you take over a data set and you get a trained neural network. It is way more complicated, luckily for us. What you need to do is you need to design a GNN architecture which understands networks. And for this, you need network expertise. So this is not an AI field where you can, people from data science can come, okay, give me the data set. I don't care about anything. I will just train. You need to design your architecture, your neural network architecture, such that it understands the what a computer network is. So it's really an interdisciplinary field. And well, this is kind of a summary of the results. But just to give you an idea, the error when estimating the delay is below 10%. RAWNet can also estimate jitter, packet losses, link utilization, and many other parameters. And just to give you an idea about the accuracy. And more importantly, RAWNet can operate in networks which are not seen during training. So you can train RAWNet in let's say that you are a vendor and you have a lab. You cannot go to AT&T and train it there, because producing the data set to train RAWNet means that you need to produce instances of configuration where you break the network. Otherwise, RAWNet will not understand what happens when the network is broken. And this is not going to happen in a production network. So you need to train it on your lab. And one very interesting property of RAWNet is that you can train it on a lab, on a very small network, but then you can use it after training. Training is a big deal, and I don't see training in production networks. That's something that we don't discuss enough. But someday we will discuss it. You train it on a small lab, and then you can test it on a production network. So you don't need to train it just for estimation. And this production network can be 100 times larger than the ones you train it on the lab. And then the speed of RAWNet, this is because it's a neural network. There is nothing with it. It's just fundamental to neural network, is about a few milliseconds. So it's very fast, not for training, but for inference, for estimation. And then I have 2 more slides. This is kind of the comparison of different techniques to build network digital twin. And the conclusion, I just want to highlight one thing. So graph neural network seems the right choice to build a network digital twin, at least the way we see it. There are other digital twins. I'm not commenting on them. But for this particular one, with this particular inputs and outputs, this seems at the right choice. And in my understanding, graph neural networks are to networking what convolutional neural networks are to computer vision. They are the right architecture that will or should provide the breakthrough that we need in our field. And finally, I will take 1 minute for promotion. As I'm sure that you already know, Vishnu and Thomas, they are organizing these fantastic challenges. And we're organizing our own challenge. This is the 4th edition of Graph Neural Network. Actually, RAUNET is not only our invention, but rather is the invention of the community, because all the challenges have been around problems on how to evolve RAUNET. And after 3 years, we have gathered a lot of knowledge. So RAUNET is really the product of the community. Now we have the 4th edition. And what we are asking participants is to build a network digital twin using data from real networks. RAUNET has been trained so far with data coming from simulation, but now we have built a testbed, a real testbed of a real network. We have produced a data set, and we're asking the community, take this data set and train a neural network, which is able to, do what RAUNET does, but with a real network. So we are asking participants, we are challenging them to build the first network digital twin using data from real network. And registration is now open. We opened it a few days ago, and you have time to submit your solution until October 2nd. So that's it from my side. I was almost in time.
Thank you so much, Albert. That is actually, I think, about 5 years that I know about, maybe more, maybe 10 years of research into 15 minutes contest. Thank you so much, Albert. I want to ask Albert about several questions.
Afterward, right?
Yeah,
Okay.
yeah. So I want to ask him about this scaling thing that he mentioned. I want to ask him about the training for error case scenarios. And then I want to ask him about the design of graph neural networks. There was a very excellent webinar that he did the day before yesterday in the context of the challenge. You should, if you have been there, then you should listen to that recording. But now, Henning is waiting. Please, Henning, there is another excellent set of inputs that we are going to get from Henning. Please listen to him.
Yeah, thank you very much, Vishnu. So great to be here. Thanks for inviting us. And yeah, I'm going to talk about native network intelligence, and we have actually already quite a bit of 5G advanced baseline. I'm also talk about the 6G perspective. This is joint work actually with many colleagues from Lucas Standards, also Bell Labs, in particular Janne Alitolpa, who's worked on the use case I'm going to show you actually in the end. Yeah. Okay, so usually I don't start this workshop presentation with a slide actually from our topmost company level presentation, but which actually only I think has a dozen pages or so. But this slide fits actually perfectly. So networks that sense, think, and act. Yeah, and what is shown here is that on one hand, of course, we need to make high performance connectivity operable and in the end then more consumable and sustainable. So that's really the operator perspective. We want to support making the network operations really feasible and easy for deployment. Yeah, but on the right hand side, you see also the other aspect, right? So once we have this good insights from the network, we can really also foster, let's say, the applications on top, let's say the slice tenants up to the end consumer, and make then their application, their business much better and easier. So how the networks are applied. Yeah. Okay, then first of all, let me come to the 6G system architecture point of view. I think today we already heard quite a bit about the framework for 6G. In the middle, you can see here all of this nice words, XR, metaverse, what we want to enable. So that means, as usual, we try to track, what are these application requirements are. Typically, yet another application comes, which is then the foreground. So that means in the end, networks need to be flexible to support in all kinds of future applications we envisage. Yeah, for 6G, maybe notable is also that we have this, let's say, true new way of using the network in terms of joint communication and sensing. And then, things like security, sustainability, across as a design criteria across the whole system. And then in the end, for the architecture, of course, important, how can we really suit all of this trends and applications for example, in terms of ultra-dense deployments, but of course also still macro deployments. Yeah. Then on the right-hand side, you see things like service-based architecture, which is already a proven concept in 5G core and in 5G, yeah, which then will also extend into other network domains, and also radio network disaggregation, basically, yeah, which of course also will play a big role in 6G. And of course, what I want to mostly talk about is then cognitive autonomous network functions, also management functions, and then native AML support, yeah, where AML is then really the enabler for the cognition. And in terms of the nativeness, I'm coming to this also in a bit more detail. We think that it really means design through AML, so meaning designing network functions in a way which is only, say, enabled by specific AML technology. Yeah. Okay, when we take a step back to 5G Advanced and O-RAN, what we can observe that actually AML is already across the board here, basically in the air interface, in the RAN system architecture core, and then also AML for management, also management of AML. For example, in the air interface, which I'm not focusing in this talk, right, you can have on the device then training inference for over-the-top applications, but of course also for network related, yeah, in the network stack, like beam management or so. And then of course also have functions which then train and do inference jointly across the U in the network. Yeah, for example, using autoencoders for channel state feedback. And then we see in the RAN and system architecture, we have then basically platforms like, for example, NWF as an analytics engine and yeah, model trainer, which supplies then trained models to the other shown core functions, or the near real-time RIG as the AML platform. Yeah, and then similar in the management plane, yeah, which again is of course then dealing with use cases across the control, so yeah, the control in the user plane, but then the RAN in the core as well, basically. Yeah. Okay, in the end, I have an example use case. Therefore, I just try to briefly flash here the use cases, which are, you could say also, of course, when you look at RAN and core in particular, and also the management, are like known use cases we step by step AML enable, and then also in the end want to transfer to native AI implementation. What is maybe notable is that all of those are, of course, interdependent, or that basically you have at multiple levels kind of the same use case, but once you create the policies and then which you enforce then rather at the lower level, basically. Yeah. Yeah, here you can see then a collection of the different study and work items. Yeah, for example, round 3, we have the AML for NG-RAN, which then also corresponds sort of to the work item in O-RAN on AML. In SA2, we have enablers for network automation. I was already mentioning the earlier discussion, but for example, federated learning is already started to be standardized, and then also the other way around. The AML-based services, where it's more about network support than for AML-based applications. Yeah, security, of course, then related to the respective round 3 and SA2 items, and then across this, then also in SA5, the study and work item on AML management, which actually deals mostly with the management of AML, meaning once you have in the RAN and core domain active training inference, how to manage this, how to do model versioning, and all of these things, basically. Yeah. And this corresponds then also nicely to the already introduced standard here from ITU Y.3172, which basically has this architecture blueprint, how you orchestrate ML pipelines, how I set them up. And basically what the SA5 work does is then transfer this, let's say, into the telco architecture. Yeah, last but not least, we have also this end-to-end AML aspects in at CCSM. This is also a lot about this kind of, you could say, patterns like closed loop, and then there's different enablers. But of course, in the end, deals then a lot with, say, cross-domain interaction, you know, from the AML perspective. Yeah, so this picture is actually from CCSM, and I just have, it's very basic, of course, right? So all of these aspects, let's say, we need to deal with when looking at AML. In AI means here simply the choice of algorithms, you know, mapping algorithms to the right problems, similar to what Alberto has just said for GNN, right? So showing improved performance. And then, of course, all of these framework issues like, you know, what platform do I need to execute? How do I do the data collection ingestion? How do I convert insights to actions? Yeah, and this is all stuff we have then, you know, I think pretty well already captured for 5G, or at least laid the foundations For 6G, I think we'll talk a lot more about now what we call here inter AI. So meaning how we actually build systems. So meaning, different functions which are AI enabled, or then ultimately also native AI. How do they communicate? Or also native AI, of course, might also mean that we actually create larger models, covering even several use cases with a bigger impact. Yeah, and then also the governance, right? How do we expose information to the human operator? How the human operator expresses intent, trustworthiness in particular, and also sustainability aspects. Okay, then an important aspect is also what is cognition, what is autonomy, and often these are also a bit mixed up. So therefore, I try to here really explain this a bit from the definition point of view. So automation is really how much, in terms of both the execution and supervision, we transfer actually from the, for example, network operations from the human to the machine, ultimately leading to autonomy. And then cognition is really like in biological systems, the ability to perceive. So we conceptualize network states, we put them into context, and then we reason basically on those. Yeah? And then data ingested into ML algorithms, actually the enabler for cognition and intent, you could say, really expressing what I want to do, and then also labeling what is more, what is less important, even down to, of course, then labeling data and events is the enabler for autonomy. And also what is often forgotten is that, like in a biosystem, right? So like you in your body, you can actually take actions any step in the cognitive process. So meaning what we typically have done is the costly, frequent but simple tasks. We have a high degree of automation with a low level of cognition, doing basic threshold crossing and cell resets, for example. But then also we had in the past complex and rare tasks, for example, ingesting a lot of data and presenting data to human, for example, to decide on marketing campaigns for mobile networks or so. Yeah. And now, of course, the crucial thing is go to this upper right-hand part here in the taxonomy here on the coordinate system. Yeah, also going for the complex and the frequent tasks. So that's what we call cognitive autonomy. And then, and this I think we have already heard today in some of the talks, for example, from Abhishek, how do we design the system? How do we find new ways of interoperability? And there I think this native AML is really interesting. So we define this as, say, rather enhancing with AML, really designed through AML, meaning, how I shape the network function, what is the scope, what is the life cycle? This is then really, say, governed or designed through the AML. And of course, we have plenty of challenges here. In network operations, typically the biggest challenge is legacy, right? And diversity. So we have huge tool chains. They vary very much across operators, and they have their own evolution. And still, of course, it's a technology novelty. Yeah, we have a huge, let's say, evolution in the AML technology field. And of course, people need to trust this. We need MLOps, to really make it happen in real systems. Okay, so here we try to summarize this as in terms of the technology evolution towards native intelligence. So in 5G Advanced, we have basically also the traditional SON rule-based system. We have learning management function, which are driven by intents. Yeah, and then if we go to 6G, we have all of this still, right? But then you can argue, okay, we can transfer a part and only a part of the management level function to what is called here native AI network management. Yeah. And once we add actually the trend that increasingly we push actually, let's say tasks or functions we have done in a management layer actually to the user and control plane, then we can actually speak of native network intelligence, which you can also here see that then the relevance of the management layer actually shifts much more to the management of AI, kind of the MLOps, but in terms of really embedding this into a telco architecture. And what is also mentioned here, the trustworthy AI. So it means then again, it's much more important to expose the human operator, okay, what the AML is actually doing and how he or she can instrument this basically. Okay, and then at the end, I like to show you, it's always nice to talk about high-level things, and just to give you one example, which, it's already in this category or maybe going also in some aspects towards native AI. This is from the German-funded project KIC, which stands for Artificial Intelligence in Campus Communication. We did together with Bosch, HHI, and Infosim. So here the idea is that you have actually vision-based indoor positioning for industrial AGVs, which is a very compute-heavy task. Yeah, and the idea is that ideally you can actually offload this task, ideally always to an edge cloud, with of course the added value that if you have many AGVs and they all offload, you can actually do the vision, the positioning, the mapping together basically. So that means that the optimization problem is you should offload as much as possible, but of course only if the network QoS is sufficient. And then at the same time, of course, minimize the number of offloading operations. So you don't want to have any ping pongs. And then of course the offloading has a cost, as the operation, but also then with a delay. Here you can see the setup, which is shown basically where it is actually offloaded. And then the idea is, of course, to have a machine learning algorithm to predict minimal achievable throughput and uplink from the AGV to the edge cloud, and to have this kind of proactive offload decision considering the offloading delay. And basically what we do is here, which is also, you could say, the combined network and application layer use case. So we take the AGV's data, the speed, the directional data, and the local radio measurements, say from the terminal, combine it with network KPIs, and then create a model for uplink throughput prediction. And then at the edge cloud, of course, we can also connect this then with orchestration inputs like the status of the edge cloud load and so on. And then here you can basically see the solution performance. So here we have an example where actually the algorithm then predicts much worse quality situation, radio quality situation. So this is a situation where already offloaded and you might want to do then an onboard decision. And you can actually see that in terms of the placement, the reactive one does this, let's say, onboarding decision way too, I mean, not in time basically, so too late, right? And which even leads here to, let's say, disruption of the system where you can actually not continue the service basically. By the way, here you see the factory floor. So this is already the way we have basically passed here in the factory floor. And then here you have basically the performance data for the reactive one. So meaning we managed to offload 63% of the cases, but we have 9 replacements for this small amount of way. And then also this one, say, state failure. Then as it is recorded data, we have this, what is called here the oracle. So this is the ground truth, basically, where we can really actually look into the future. That we manage 89% offloading, 4 replacements, and no state interruption. And then here you have basically 3 different types of machine learning algorithms. And for the best one, which is in this case is the convolutional network, we manage actually 76% offloading and 4 replacements similar to the Oracle, and also no state interruption. So this works quite well. And like I said, this also gives then this industrial application, a lot of flexibility actually what to do with the AGVs in the end. Okay, so then let me summarize the takeaways. Native network intelligence. This is basically cognitive autonomy with some native AML system design. So basically we try to enable this machine level understanding of system concepts and context to enable decision making. And of course we want to do this in a multi-domain view, which is already going on in 3GPP and other SDOs. And we have a shift from network management to the management of AML. Of course, not completely. So really it depends then on the advanced sophistication of the use case. And we also shift from enhancing individual network function with AML to redesigning them. This is kind of the native aspect. And then also building this AML-enabled systems, keywords inter AML and AML governance. And of course, then I was already touching challenges, which are actually relevant for this workshop. Is really then, of course, keep up with the pace of AML technology. Examples, for example, federated learning, right? There's a lot happening. And then in some ways, it's maybe even coming a bit too early to standards because the technology is not yet mature. But on the other hand, of course, it has a very fast pace and we need to follow this. Then collaboration with IP protection. This is, of course, important for the players in the value chain. When you look also both at the R&D and the operation life cycle. So how do we share data sets? How do we share models in a way which balances this trade-off? And then, of course, the combination of AML standards, network standards, open source initiatives, both from AML and network side, and last but not least, the whole research community. And with that, I'd like to conclude, and there's a few references still, of course, you can consider. Thank you very much.
Thank you so much, Henning. Next, we would have welcome Professor Tom, please. We will take questions during the discussion session. Please hold your questions and let's hear from Professor Tom.
Okay, so thank you. My name is Tom Luo. I'm from Chinese University of Hong Kong in Shenzhen, in China. What I'll talk about today is a line of work we started about 3 years ago jointly with Huawei. It's about how to use AI in 5G network performance optimization. It's actually related to the previous two talks in some sense. So a little bit of self-introduction. I was asked to do so. So I did my undergraduate degree in mathematics from China, and then went on to pursue my PhD at MIT in the area of operations research. So what I do is use mathematics and algorithms, models to solve real-life problems, most notably in information science, signal processing, and wireless communication. So I've worked for many years, 20 plus years in Canada and also in the US before moving back to China in 2014. Currently, I'm with CUHK, the Chinese University of Hong Kong in Shenzhen, serving as vice president academic and also professor in the School of Science and Engineering. I'm currently also serving as director of Shenzhen Research Institute of Big Data, which has annual funding of 150 million RMB per year. Okay, so my areas of research are two fronts, basically. One is mathematical optimization for signal processing and communication research. Notably, recently I've been working on AI techniques for 5G network performance optimization, mathematical algorithms for big data applications for signal processing. My future, I'll be involved in this wireless network performance enhancement problem challenges 3 years ago, and then I intend to continue in this line of work. I'm also quite interested in this ISAC, integrated sensing and communication aspect of 6G, many other things, so energy saving. All right. So potential collaboration with ITU, I was asked to say a few words. I didn't know too much about ITU before coming here. So I sense standardization is one aspect, and also workshops and sort of information exchange, getting to know some folks in ITU and making more kind of a global impact of our research. So that's what I'm interested in. So this is my real part of the main part of the presentation. I'll talk first about the challenges of using AI for network performance optimization. And then second part, which is the main part of the presentation, I'll talk about the current progress and then the results. So challenges. So as we all know, China is a 5G technology leader in terms of not only in terms of the patent, but also in terms of the equipment providers and so on. So these equipment, so base stations, cell phones, and all these other equipments related in 5G, they're tested in the lab setting. They're great. Cheap and they're reliable and fast and so on. However, next slide. When they're connected in real practical wireless networks, they don't necessarily transform to top network performance. That means top hardware doesn't mean you have top wireless networks. Reason is because hardware, why? When they're connected to real life networks, each base station has several hundreds or 1,000 parameters that need to be chosen to match the local electromagnetic propagation environment, to match the user traffic distribution, without this clear matching to the local propagation environment and user distributions and so on, then all you can do is set these parameters to the default values in the lab setting. And all the networks that you build in Beijing or build in Geneva, if you all do so, they all look the same. And then the capability of the hardware cannot be exploited or utilized in real world networks. So how do you do that? That's requires, how do you choose these parameters in the network, wireless networks? Similarly, I mean, to the first talk, I mean, that's more of a fixed network. I'm talking about wireless networks. So how do we do so? Without choosing this carefully, then your networks will be just mediocre, okay? 60 or 80% of the full potential maybe. So the traditional way to choosing these parameters, engineers scouting this environment and say, I think you should do this, choosing these parameters, or test them in a few combinations of network parameters locally in a small region, and then just replicate, deploy to the whole city, to the whole geographic region, big region. So that's it's ungreen, it's costly, labor intensive. Huawei spends hundreds of millions of US dollars just to do so every year. So 3 years ago, I was asked to do mathematical approach to this to take on this challenge. So how do we do so? Challenge number one, we have limited real data. We collect lots of data, but this data only corresponds to one network parameter configuration. We cannot sort of reconfigure the network and then try to collect another. I mean, keep doing so. We actually can collect the network data corresponding to the current network configuration. How do we build a model that can generalize? That's the real challenge, number one. Number two, how do we optimizing a real life wireless network? It's very risky, can be very sort of, you cannot have sort of, one parameter is set wrong, you can sort of screw up all the network performance. Thirdly, the number of network combinations, the network parameter combination is just astronomically large. For example, in the city of Shenzhen, this is where I live and work. Yes, it has 50,000 base stations. Each base station has at least 3 cells. Now, each cell has about 1,000 common sort of network parameters that you can choose and optimize. And each parameter has like maybe 50 or different values you can choose from. Now, if you multiply all these combinations, you get a number of 10 to the 2 million. So large compared to, put this in perspective, to 2 million zeros. Put this in perspective, you consider the game of Go, which is very challenging, most sort of complex game that human can play. The solution space for that game is 10 to the 100. This is 10 to the 2 million. So we need an efficient algorithm to optimize this. So number 4 challenge, there's no prior art, no published literature in this field, how to deal with this problem, because academia have no access to real life data. No mathematical models have ever been created for this problem. So what we needed to do actually in year 2000, when we started this project, is to really look at what sort of similar to AlphaGo technology developed for the game of Go by DeepMind. We need a new AI approach for this 5G network performance optimization problem. Completely new one we have developed, okay? So this is precisely what we've done in the last 3 years. I'm happy to report here to the colleagues here. We have a model. That's what we call SRCOM is a key technology, simulated reality of wireless communication networks. It's data-driven simulator, much similar to the first talk, but it's real life-size commercial wireless network. We take some data, collect data from the current network configuration in real life data, and use this to build a performance simulator or predictor. If you change the network configurations, this simulator will predict what's going to happen to the live network. and then coupled with a mathematical optimization algorithm to search in a 10 to the 2 million solution space. So because this is the first time we've done this, so certainly we have our goal initially when the company asked me, challenged me, if you can beat our best network engineer, you have succeeded. I'm happy to report we have done much better than network engineers now using these mathematical tools. Okay. And then the technique is basically we don't simulate in the packet level. I mean, this is just not scalable for a big sort of a size city like Shenzhen with 20 million inhabitants. So we use wireless communication technologies, the models theory and so on, coupled with real hardware simulator, measured sort of feeding the different sort of network configurations and see what each equipment will behave, how it will behave. Each node of the network will behave and so on, okay? Yeah, and then also we have a neural network to predict the actual network performance. Given the prediction, we predict the channel condition, the user distribution. Once you change the network configuration, how the users will automatically register to different cells because topology will all be changed. So we have a completely, the whole model consists of more than 24 of mathematical models in there, doing prediction, user to base station association, all of that. So that's technique number 2. Number 3 is a large-scale network parameter optimization algorithm that's highly decomposable, scalable, that can search in the large space of 10 to the 2 million, this kind of solution space efficiently, okay? Altogether, I mean, this is still a very simplified model. I told you like more than 24 of mathematical models we've developed over the last 3 years. This needs you have black box, you have white box, or you have black box model, you have a large scale optimizer, but critical things is have to be safe. You cannot sort of do something that they'll screw up the real life wireless network. So we built in a lot of safety mechanism, robustness, and we have to deal with the messiness of the real life network, the parameters, because the configurations, this network operator, they don't know what their configurations are. 40% of the parameters that we collected actually are noisy, faulty. We have to deal with this at the algorithm level. You have to take that into account. Yeah. So let's see the initial results. Last year, for the first time, we deployed this in a large scale in the city of Seoul in Korea, South Korea, and then the adjacent city, Incheon. This is a network built by Huawei. The top two, the third largest network, the top 2 networks built by Samsung and Ericsson, respectively. So the Huawei's network has 20% bandwidth reduction, I mean, less bandwidth. And yet, with our algorithm, we were able, without adding any hardware, any bandwidth, physical resource, algorithms and models enable Huawei to compete successfully, surpass the performance of the other 2 networks, top 2 networks. And then this is rated number 1 out of 1,000 score MLOps. This is the sort of a third-party, well-known, accepted sort of a system evaluated, they rated this as the top network in the world because of this technique we have used. Some other, I know my time is up, so I'll quickly. So let's just, many other places in the world, in Europe, let's just quickly go through this. I'll do this myself. Okay, oh, sorry, I messed it up. All right, so Philippines, Switzerland, also many other places we have tested this technology, and we are still refining. This is the technology version number 1. It's on the cloud, okay? Thousands of engineers throughout the world are using this already. Many challenges in the standardization process. I mean, some of these because it involves sensing the real environment, traffic distribution, and so on. This information will be very valuable to the network performance enhancement, self-enhancement doing this. So what I've talked about today is really AI plus 5G networks, is what we call SRCOM, has many aspects. I shared a little bit with you. Hopefully with colleagues together with ITU, we can make this even more, maybe a global standard in the future, how we actually can use mathematical tools to enhance the performance of the network without actually injecting any additional physical resources. We can use fewer base stations, use less energy, and achieve more. Thank you very much. That's my presentation.
So I you know what I call Professor Tom's research as this map-reduce concept applied to network optimization. You know, that's exactly how I fit his research. It's extremely interesting, very interesting. Thank you so much. Tim is here. Please let's listen to Tim about deep learning in physical.
All right, thank you. So thank you for inviting me here. It's great to be part of this and exciting to see ITU really looking heavily at ML and 6G, which I think is a very exciting space. So just some brief background. So I'm the CTO and co-founder of DeepSig. DeepSig is a startup based in Arlington, Virginia. We got started in 2016, 2017, really focused on the intersection of machine learning and communication systems. And really our focus is on value and optimization of kind of the core of wireless systems, the physical layer and the air interface. And if you look at our wireless systems today, 80 or 90% of the energy consumption is usually in the RAN, so in the radio unit and the baseband unit. And so that is really where we focus. That's, I think, the key of performance and efficiency in wireless and where some of the biggest impact can be. Right, so at a high level, and I think Jan LeCun recently popularized this image, which I think is a great high-level abstraction. We've seen virtualized RAN really take over and turn much of our networks RAN into software. And now we're really seeing this trend of all of that virtualized software can be optimized, deeply end-to-end in many, many different aspects of it. And so just a few of these pieces where this trend, which has crossed all of signal processing, and is obviously very mature now in natural language and vision and audio in many of these different fields, is really coming for wireless. We've seen a lot of it today, but this is really an inevitable trend. And so a lot of the pieces here in wireless where this can have a major impact are within kind of spectral awareness and what's going on. I think we've seen some nice examples already of digital twins and what you can do when you have an accurate picture of the world and the propagation and the emissions and interference around you. And then, how you can build these physical models of the world for user content, user behavior, for channel response, for propagation. These are all the things we need really accurate models of to optimize our networks very quickly. And then for using that to do optimization of multiple levels of the stack, from the PHY to the scheduling to the orchestration to the parameter tuning. All of these things can be optimized. There's a nice illustration of the combinatorial size of this problem in the last talk. So next slide. So these are just some examples of what we've been working on to try to tackle this problem. A big piece of this for us as well has been looking at AI and machine learning within 5G. And so a piece of this is really looking at how do you look at the L1 design from an AI native approach? Can you look at the receiver performance? Can you look at the massive MIMO algorithm implementation performance? And can you improve within the current standards using a lot of these techniques? And so we're doing some trials now over the air with deployments and doing kind of macro cell drive testing for the capabilities where we're looking at neural receivers has been one piece. And so if you look at Open RAN, Intel FlexRAN has been probably the most widely used baseband stack out there. And so that's kind of what we've been working with as a smaller company. And so we've shown some really pretty significant improvements both in link margin and speed up. So I think these are really exciting to show that you can in some cases double your throughput in sectors by using the link margin that the sensitivity gives you here, and you can reduce your compute complexity and the load and the cost and the energy costs of deploying these networks. And then similarly, when you start looking at scaling this into massive MIMO networks, a lot of these tasks for channel sounding in massive MIMO are very expensive computationally and energy wise. And so applying these there has shown even larger speedups. So we've shown in this case on the order of 5x speedups with kind of the traditional MMSE approaches and 4x roughly accuracy improvements for the channel state estimation. So switching modes to sensing, this is kind of the other big area we've been looking at. And how do you use an AI native approach to making sense of the spectrum around you, the activity in that spectrum, and then kind of the model for the world around you. And if you see this as kind of the way to keep the models in your RF digital twin accurate and current and consistent with the world around you so that you can continually optimize for them as objects move, as emitters move, as other networks move, as interference sources move. And so, by applying a lot of the deep learning kind of computer vision type methods adapted to RF types of data that have very different requirements and architectures, you can build these kind of no code or low code capabilities to detect and localize emissions and then use this to populate the data. So these are some examples where we're visualizing in XR kind of what's going on around you. And this is a nice way to look at, what is the raw data that's needed to optimize these networks in the future. So I think for 6G, all of this has to come together. So we've looked at kind of the transparent optimization. We've looked at kind of the sensing optimization. We've also looked now at this kind of end-to-end learned communication system, which people have been referring to now as this AI native air interface. And so we're now on kind of our third generation prototype of the AI native air interface internally. And this really has to come together. So at the bottom here, we have, kind of what are the ins and outs of the entire digital twin. So there's been a lot of nice talk about how a core of the digital twin is the ability to estimate performance for a specific set of conditions. Well, you need to have the in-network information, all of the CSI, the KPIs, the configuration, and the demands on the network, alongside the out-of-network sensing, probably from the infrastructure, from the UEs, from a wide set of platforms, all feeding this digital twin platform so that it can keep the physical world models all up to date. So all the propagation models, all the models of emitters and locations and trends, all of these models within the digital twin need to be fed by and fit to these data sets. And so by doing this, then this digital twin and the ability for it to estimate performance across each of these phenomena can then be used to optimize a wide range of pieces of the stack. So throughout the physical layer, the mode adaptation, this parameter tuning, how you can do spectrum sharing between networks or within a network. So all of these optimizations are really driven by these physical world models. And so I think that this cycle is pretty critical. Right, so I think this is just a nice look at, how rapidly machine learning is being adopted within 3GPP. We saw no mention of this in any work items until release 18. And now it's just kind of like this exponential curve where it's beginning to, be throughout almost every topic and work item is affected by this very rapidly. And these are just a list of some of the 5G advanced and kind of forthcoming probable 6G topics in this area. And so I think, with this effort here, we're kind of looking at what are some of the pre-standards work and areas we can focus on accelerating. All right, so just some kind of thoughts on this panel and prompt that we're looking at here. what are the right platforms for 6G? I think that there's a wide range, right? So there's a need for very low power, low latency, efficient inference at the edge. And there's a certain class of silicon that's very good at that. There's a lot of different novel approaches to that. And then there's a whole other set of more centralized and cloud type processors. And so there's no one winner. There's still a wide range of different processing types, but they're all somewhat converging to this sort of tensor type operations at low precision that can be very efficient. But this is going to be a competitive environment for a long time. Private 5G, we're starting to see take off, as spectrum licenses are coming out. And so this is kind of one of the early adoption areas, I think, for vRAN and for customization of vRAN for new different types of applications and demands. I think, back for a second. Sorry. Yeah, so I think it's nice also to look at this this model for applications from Open RAN, where we've kind of divided things into R apps, X apps, and then there's kind of a debate between whether it's a D app or a Z app currently. But this is a nice model for like the centralization versus edge, and then the latency demands of each model. And so if you go down to the Z app, this can be sub-millisecond inline processing in the baseband, or maybe in the RU at some point. Whereas the R app could be all the way up to kind of a national data center level where you may need seconds of latency, and you may have super compute level things. So there's a wide range, of different fit models. Yeah, and I think lastly, just wanted to touch on open source there. I think open source is an enormous enabler for this in terms of helping with open reference architectures, open interface references. But I think it's important for us also to understand that, there's this tragedy of the commons in open source. And, open source is not a self-sustaining model by itself. And so as we look at, how does open source help to enable ML and 6G, how do we find the right business models and the right pieces to be open and the right pieces to be competitive and differentiating so that this whole ecosystem can grow quickly and healthily. And so, these were just some kind of thoughts on, how can ITU in this ML 6G effort kind of engage? And I think it's great if this can help to kind of highlight some of the proof of concepts and contributions that we think will be high impact in this area going forward. I think it's a great way to try to, highlight new non-traditional organizations that are working and developing IPR in this area. And I think there's a lot going on also in technical driven standards bodies like, Open RAN and IEEE beyond 3GPP as well. And so it's a great place to potentially partner with and emphasize things there. And right, so for key technologies, I think also that, this is a great time, as we're going into WRC 23 this year to potentially emphasize, how, sensing driven technologies using AI can give us an order of magnitude better spectrum reuse and sharing as we start to embrace them more within the RAN and these networks. And then really an opportunity to focus on kind of the key performance enablers within the RAN KPIs. So things like the AI native air interface, how we scale multi-user MIMO, and how we really continue to reduce power and cost, and then continuing to look at things like semantic communications and kind of end-to-end design. So I think these are all really exciting areas to help do pre-standards and proof of concept work to help mature these areas for standardization. And that's it. So thanks for having me. Look forward to your questions.
Yeah, thanks a lot, Tim. I have to tell you this. In between doing all this, Tim actually manages open data. He has published open data. You can look it up from his website. It's quite interesting. So I think his knowledge is coming from experience. I believe the points that, let's get to the discussion. Can we, Emmanuel, do you have questions online?
Yes.
Okay. Is there anything from the floor here, please? If there are questions from here. No, we can take a couple of them from online. Can you put them here? All right. Okay. Yeah, right. GNNs, yeah, I believe that is for Albert, no? Akshay is asking why analytical methods fail as compared to GNNs. Is complexity given diverse set of network instances they have to process, Albert?
Yeah, so it's a good question. Thank you, Akshay. So analytical models fail because typically the best analytical model that we have is queuing theory, and queuing theory fails with realistic traffic, meaning that it works very well when the traffic is, well behaved, but in reality, traffic is not well behaved and it works really poorly. We have reported the results and the accuracy is really bad for queuing theory.
Thank you so much, Albert. Maybe we can take Aliu's question. Aliu is asking, I believe this is for Henning. What role can DTN play in native 6G intelligence advancement and problems with DTN help to solve? Please, Henning.
So I guess DTN is digital twin as well, right? So yeah, yeah, very good question. Because I didn't include it simply, you could say, for space reasons. Yeah, I think okay. I just saw talk. There was a lot of this, right? So this kind of what if scenarios. This is really important. Yeah, which you could say also sometimes inherent. Yeah, question also when it's about then supporting, let's say, human decisions. Yeah, then for example, digital twin, when you see reinforcement learning as a technology, right, then you don't want to run your, let's say, very explorative algorithm immediately on your live network, yeah, which I think was also mentioned by some speakers in terms of this. It needs to be operationally safe, yeah, and everything around operational safeness, I think safety, this is where the digital twin will kick in, yeah. So I see it also really as let's say, an integral part of this 6G picture, basically, yeah, particularly for the network optimization. Yeah. And then if I may also, I think there was also this previous question on, why, I mean, in general, why don't we solve this with analytical models? I think in general, we have simply use cases we could not solve before at all, like anomaly detection, right? You cannot configure all your cells in a network, with some rules which are, have to constantly be adapted. Yeah, so there are literally new use cases which have been enabled with AML that we should not forget.
Thank you so much, Henning. Marco is asking Professor Tom, you mentioned collaboration with ITU concerning technique 1. Data generation via statistical modeling. Do you think we could derive standardized data sets based on statistical modeling that could reusable across different networks?
Regarding the data sets, I believe so. After some sort of a desensitization about privacy, so maybe user IDs or these stuff. It should be possible. Yeah.
Yeah, please, could you state your name? Sorry, I don't know.
Yes, my name is Luis. I'm a senior researcher at Quadrat. I actually want to follow up on the question that Marco did for Professor Luo. First of all, great presentation, Professor Luo. I really liked it a lot, and your insights are very valuable. But continuing on that question is, I saw that the techniques that you're using are data generation via statistical modeling and network performance prediction via AI models. So, and then the deployment of the works that you have done has been done at different cities that have different network topologies. So if I understand correctly, every time you deploy your solution as RCON into different cities, you have to apply data generation via statistical modeling and then train a new model. continuing on that question, like how is it generalized? I mean, is there any insight regarding how to make these techniques generalizable, not just when you deploy it in different networks, but as the same network evolves? Because as you know, the networks in different cities, they change topologically. Different base stations are being added. The identity of the base stations change, and also the amount of users that come in and out also evolve. This is not an instantaneous process. It's usually very progressive. So I just wanted to know if there are any insights in techniques 1 or 2 that will take this into account.
Okay, so a lot of good questions in this big question. So what we do is actually the performance part, performance prediction module is universal, it's used everywhere. But the channel condition, traffic prediction, all of this is localized to the city. And then because network evolves over time also. So every time you want to do an optimization of the performance of the network, you collect a bit of new data, leveraging on the existing data model that you already have. So this is sort of a legacy. You have a digital asset in a sense you keep. And then you just adapt that with additional new data. But the performance prediction part, that's universal, it's used everywhere. We don't change, you tinker with that. Unless, of course, your base station has been upgraded, your equipment, your software has been upgraded. Then we have to do that accordingly. So, and then user migration, all of that, we have prediction models. That's why I said I have more than 24 of these models in the overall framework. It's not an easy task.
Yeah, it's not easy, especially because like when you get new data, you basically have to integrate it with the old data. This is digital asset that you don't want to get rid of.
That also is challenging. We have gone through all of that struggle.
Well, if I could add to that, I think that continuous model updating, is critical for as the environment changes. And there's not really standards today, right? That's all kind of within infrastructure implementations. So that's one of the things that if you look at within Open RAN, you're starting to see things like E2 service models that can start to support these sorts of data collection. And those aren't standard functions today. But those are sort of areas where the data collection to feed model training and updating is going to have to become more and more standardized for this to become interoperable and multi-vendor.
Because that's one of the main things. We might develop that will be able to simulate, emulate, to have a digital twin of the network that might be useless in 5 years. And then we have to retrain and retrain and retrain. But I think the thing is how do we handle the evolution of the network in terms of the data monitoring and how we process it. And also in the models for the techniques 1 and 2 that Professor Luo mentioned. And the fact that there's no standardized methodology, that's what I wanted to see if there were insights on that.
So one maybe comment with what Tim said. So I mean, I totally agree. You need these interfaces to get data from, for example, let's say UV, which do not exist today. But you also need to think that you might need different kinds of data tomorrow, and that means even newer interfaces. Or we can go with what I presented, something like more semantic approach to these interfaces. So you don't need to have hard-coded standardized interfaces, because your requirements of your application will evolve, and then the interfaces would be still fixed on paper. So that might be an interesting path for this as well.
Maybe I can also add to this. I think even generalizing a bit your question, I think you raised the question, how can we actually make use of knowledge which is generated inside the network, right? And how we can actually transfer it and reapply it according to certain context, yeah? And there's also this, which I think also should mention here, we already mentioned federated learning. We should also mention transfer learning, right? Where the idea is that I've learned something on a certain feature set, I can reapply it to a different feature set, or I can reapply it to a new task, basically, right? But then the tricky part is, of course, always to understand what part can be reapplied of your model and what not, right? But this, I think, is also a very interesting discipline, because otherwise, as you say, It's a bit like, you know, if you would always be reborn as a baby and you don't have any experience, right? So we really need to make sure that, of course, it's also very different, let's say, from going from the physical layer to network operations, right? That we also, you know, what we know from the human world, right? You have a network operator working on one project, and then he goes, for example, to another country with different bank holidays or whatever, different traffic characteristics, right? But a human, of course, has this inherent capability of reapplying the knowledge, and that's exactly what we need to enable also.
Yeah, I think it is quite interesting, especially if you look at if you look at larger models, right? We talked about larger models. If you look at the context of larger models, training them, tuning them is a task by itself. So yeah, great question. Ahmed, please.
Yeah, thank you very much. And thanks for the great presentations, actually, a very informative session. Just a quick question, because one of the things, I mean, I'm Ahmed from Huawei, and one of the things we work on that's very complex actually is the roaming, especially when it comes to packet core roaming, because you work with two networks live, you know, open the PDP context at the same time between two networks. So in the case of national or even international roaming, has any of these maybe digital twins as an example for the presentation, or the mathematical model of parameters have been tested to create some sort of emulator or simulator between two different networks, not in the same network, so we can emulate or see what kind of parameters be working together, even in the case of international or national roaming? This is my question. Thank you.
I don't know who is working on this, but I can tell you there was a paper from our colleagues in Telefonica. Telefonica Research. They studied this problem. It is published in our journal, ITU journal, and I can send you the paper. I am not the expert in this, but I know the problem that you are saying, Ahmed. That is addressed. That's a very important problem. They were looking at it from what do you call that? Trucks moving across the border, where you have constant traffic between countries, international roaming happening right there, and they were trying to look at what the mobility parameters which are used by these vehicles and the people who are inside that. Would that be seamlessly applicable across the border? This was the question which they were trying to address. Unfortunately, I'm not the expert. I'll send you the paper. Yeah. Yeah, good point. Good point. I think it is an interoperability problem right there. I think that's a great point. Yeah. Do we have let me just switch to the online again. Question for Albert. How do you see incorporating DeepSeek functionalities? Okay. for sensing the spectrum into graph neural networks for digital twin performance prediction? As well.
Yeah, there is a bunch of literature regarding how to apply graph neural networks to, let's say, electromagnetic environments, like wireless environments, both to the fundamentals, to electromagnetism, and to, let's say, physical layers and so on. And then I believe that Dr. Suarez from Telefonica, in his presentation, he has some related answers to this question.
Great. Thank you so much. Yeah, maybe. And so you could wait for Jose's presentation. That will be answering some of your questions as well. Marco is asking, we are handling a correspondence group. Yeah, CG data set. There is correspondence group under study group 13. Today's exchanges will be very helpful. Yes, thank you, Marco. Thank you very much for that comment. Any other questions from the room? I know you guys are hungry, but I hope you're hungry for questions as well. Is there any other questions in the room? Otherwise, we could look at what we did today. I believe we are good boys and girls. We have been doing hard work. I think this session, especially the morning sessions that we had, were quite interesting knowledge that we gained about various topics, 6G, open source. My notes are full. So let's actually look at lunch now. Lunch is in the cafeteria. Thomas already explained to you that there is a table reserved for you. Otherwise, you may not get space. so there is a Thomas, please.
Okay, thank you so much. So as we can see on the program, the lunch is from now around 1 p.m. to 2:30, 90 minutes. We have a table reserved for about 20 people. So we expect people to join the table and continue this conversation as we are eating our lunch. It's a paid lunch, so everyone will pay by themselves, but we hope we can network and enjoy the time with some nice conversation around AI, ML, digital twin, open source, and everything in between. Yeah. And also just to remind you, we have a reservation for like dinner at 6:30. It's just 10 minutes walk from here. So we can, after we finish the session at 6, we can walk together. This is also paid. Everyone pays for themselves. So we didn't have any sponsorship to sponsor these functions. But anyways, it's good to have everyone. So yeah. Time for lunch.
Can we look at the next sessions, Thomas, if you scroll down? So while you're eating, please think about this. Ahmed is here. Thank you for coming. We have Shilin online, and Jose is here, and Paul is here. So we are going to have. They are going to wake you up. Hopefully after lunch. Let's meet at 2:30. People online, colleagues online, please come back at 2:30 Geneva time. Thank you. We have another set of excellent presentations now. Can I just check? Can I just check if Shilin is online? It's quite late for Shilin, so we will try to get Shilin if she is there. Shilin, can you hear us? Can you hear us, please, Shilin?
I should unmute myself.
Now we can. Yeah. So yeah, if you don't mind, we can. You can go first, please. It is late for you. Thank you for staying late. So please, you can share your screen, and we are ready to go.
Okay, that's great. Thanks so much for the consideration. Okay, let me get started. So, well, can everyone hear me? Okay.
Yeah, we can hear you well.
Okay. So thank you for the consideration. But first of all, of course, I appreciate this opportunity to share some of our thought in this really very important workshop. Actually, I have enjoyed the previous 2 sessions. I kind of stayed quiet online throughout. Didn't want to miss the opportunity to learn from all the experts. But anyway, so let me start with the architectural platform enabling AI machine learning from 5G to 6G based on some of our experience. Is the screen moving?
We can see the screen. If you could just try moving it, it is fine.
Okay, is it?
Yeah, it's
okay.
moving. Yeah.
So of course, coming from the China
You
Mobile.
could try making it full screen, Shilin.
Okay. Well, coming from China Mobile, I guess I'm obliged to share a little bit of our status with you on our 5G network and also the current status. We already have more than 1.5 million 5G base stations deployed in our network. That is on top of the more than 3.5 million 4G base stations. They are coexisting. And of course, our 5G network is standalone mode completely. So it's fully end-to-end 5G. And among our somewhere between 900 million and 1 billion subscribers, we have already close to 700 million subscribers that has converted to 5G services. And our network is made of tri-band, making use 700 megahertz band for coverage and the 2.6 gigahertz as the main band, plus the 4.9 gigahertz band. And in terms of enabling the verticals, so far we have more than 20,000 successful vertical industry cases. However, considering the scale and the size, the potential market size in terms of enabling vertical industry is still a very small subset of the available opportunity, of course. And here on this page, you'll see some of the example cases where we have served the medical industry, the mine industry, surveying, teaching education, smart grid, high-speed rail, and also petrochemical industry. With reasonable success, but we are still trying to figure out how to be able to have scaled up replicate of somewhat successful cases across the similar industry segments. And I think this is kind of one of the most major pursuit of all of our I guess global colleagues in our 5G pursuit. And we are actively exploring AI and machine learning capability in our 5G network. As you can see that we are looking at from planning to construction to maintenance, mobilization and operation phase, and also how to actually embed deeply the network optimization capability at various levels, the link level, network level, and service level. But we can see that there are great opportunity and an open field for us to explore. But so far, I would say that we have some progress, but it's certainly not in a holistic, systematic manner. And I would like to share with you a little bit of our actually thought about technology trends, a very interesting transformation journey that we have started on since going from 4G to 5G, and then now from 5G advanced to 6G. We believe that we are actually in the middle of a very important paradigm shift, meaning that up until 4G, all of our generation by generation progress has been based on mostly communication technologies. But from 4G to 5G, we see that the communication technology and IT technology are getting integrated. So ICT convergence has started, which brings us naturally a efficiency and agility, which is green and soft as a key feature in this journey. But going forward from 5G advanced to 6G, it's the second part of this important transformation journey, which is in addition to ITCT, we also have DT, the data technology being deeply converged. And this will bring us further into a open and smart era. And as a result, the operator of the future will have to consider very different environment and also roles and also behavior in a way that in the past, for a long time, operator has become very much TAM dependent. And so in the future, we see that with ICDT convergence, we will have to participate in the CI/CD CT mode of life. And so cloudification, AI ML, open source community, open reference design, open ecosystem, and faster innovation are all going to become our daily life. So I think as operator, we are still learning how to really be able to thrive efficiently and successfully in this new era. And one of the biggest effort, I think, is the Orion Alliance, which is actually operator-led alliance. We do enjoy great contribution in the participation of ecosystem players across the board. However, the alliance is led by operator community primarily. And as some of you may remember that it was announced about 5 years ago in Barcelona, 2018, but it's officially actually established in October 2018. So we are going to be 5 years old soon, but not quite yet. And this particular alliance really is focusing on the ICDT deep convergence and focusing on open interfaces, open APIs, open reference design, or focusing on bringing embedded AI support into the RAN radio access network. And of course, cloud platform is a foundation. And then in terms of reference design, I think there's two types that we are working on in general. One is on the hardware aspect. It used to be called white box, which is basically open reference design for hardware. And then we also have open source community, which provides open reference design of software. I think some of this, the value of this work has been touched upon by the earlier sessions already today. And so in less than 5 years, we have enjoyed a good, healthy growth of the membership. Because you can see that currently we have about somewhere between 4,000 and 4,500 active experts participating. We actually have a very agile mode of operation. Most of our members are involved in online meetings on a weekly basis, if not more. And you can see that this is kind of a collection of our members that cut across really academia, application developer, chips, cloud, hyperscalers, network equipment operators, et cetera, et cetera. So we have a very rich, I think, portfolio of the membership. And under the technical steering committee of our alliance, with time, we have now evolved to having 11 working groups, where you'll see that working group 2 and working group 3 particularly are working on the RICs. Some of the early talks that touched upon their work. And then we have 5 focus groups. One is particularly for open source community. The other is also very important, I also highlighted, is for testing and integration, and also encouraging prototyping and global plugfest. And we also have a research group that was established specifically to address the 6G opportunity. Now, a very important part of this in the operator-led alliance is the OTICS, the Open Test Integration Center, which is originally the goal was to provide a vendor-independent, collaborative, and open impartial environment for everybody to come try their latest, newest hardware or software out, and also encouraging multi-source, multi-vendor interoperability. And so far, globally, 15 such OTICs has been established. As you can see that there are 4 in Europe, 5 in Asia Pacific, and then 6 total in North America. So there's a total of 15 today. And also among these OTICs, as well as other labs that are interested, we have held annual plugfest, and now since last year it's converted into biannual. So we have a spring and a summer and a fall. We have just concluded the spring Plug Fest this year, and then starting, we'll have the call for participation of the fall Plug Fest soon, later this month. And we jointly established the open source community of ORAN Alliance together with Linux Foundation in April 2019. And since then, it has been regularly providing a release once every 6 months. And currently 13 active projects are being pursued. And as you can see that the PTL of these projects actually come from very diverse background, also including operator, traditional vendors, as well as new IT players, and include as well some medium-sized or small-sized enterprises. And the latest release is H release, which is the number 8 release, which is just released last week, at the end of June, actually. Now, for research towards 6G, we have launched the ORAN NGRG, which is led by a 16-member technical oversight committee. The 16-member composed of 6 operators, 6 vendors, plus 3 academic thought leaders, as you can see, 1 from each region, Professor Vincent Poole from North America, and Khaled Ben Latif from Asia, and Hans Schotten from Europe. And plus the 16th member of this TOC is actually a hyperscaler, as you can see, that it's Microsoft that's included here. So it has actually been focusing on research pre-standard work, very different from our working group and the focus group. And the goal is to ensure good collaboration with other 6G initiative and 6G organizations to hopefully together deliver a unified 6G standards across the globe. And this particular research group is also very special in the sense that non-ORAN members from academia are welcome to participate. Okay. Now, a few words about the intelligence. I think based on the talks this morning, it seems that our participants has a reasonably good understanding of the work involving AI machine learning in ORAN Alliance, mostly focusing on our SMO, our non-real-time rig, and near real-time rig. Of course, our OAM also has the flavor of AI and machine learning involved, but this work are spread across our working group 1, 2, 3, 6, and 10. Let me just very quickly show you non-real-time rig and SMO. This is primarily working group 1 and working group 2. And you'll see that the non-real-time rig actually, its original role was to provide offline training or basically longer time duration operations. I think our initial target was about 1 second, longer than 1 second loop. So it's in the management plan. And through our apps, it provides service management and exposure services and data management, exposure service, as well as AI machine learning workflow services. And the A1 is a key interface between non-real-time rig and near real-time rig. And let me show you near real-time rig. The near real-time rig is meant to provide inference work for the most part, but of course it also gathers data and send it up to the non-real-time rig and the SMO for SMO use. And here XApps has been mentioned already by other speakers earlier this morning, which is where we provide various control plane optimization functions, be it mobility or interference, load balancing, or QoS, QoE, or energy saving, etc. And let me show you some examples that we actually use the rigs in our network for. This one is using the rig to predict the the traffic and also the channel condition, so that we can adjust the resource for the different slices. The 3 slices in this particular case are the industrial CCD server, the 4K camera server, and also HD camera server. As you can see that they have very different SLA requirements. And so our rig actually improved its SLA satisfaction rate from the round robin approach of a slice resource allocation from that would only give about 70% SLA satisfaction rate. But with the rig, it improves to about 90, especially for the 4K camera case, it went to almost 95% from 70%. And then the other good example is actually the surveillance camera. Surveillance camera are mobile cameras. So our rig enabled the bandwidth prediction and also expose the prediction to the various mobile camera that based on the predicted bandwidth, because while the camera is moving around doing the surveillance, the link condition would change. So based on that information, the video coder would adjust its coding rate, okay, so that you could get a smooth frame of the video. You can see that in the bottom, we're showing that with the rig operation on, the video stream codec rate actually varies according to that particular camera's channel condition, whereas with that varying codec rate, it actually could keep a smooth frame interval at a constant rate on the right-hand side. Okay. Okay. This chart actually I did not include in my talk initially, but I had a very interesting breakfast meeting with the ITO team this morning time, your time today. And based on that conversation, I thought it's worthwhile showing this particular chart, which is, this is my attempt of putting in all of the AI machine learning related work that has been kind of progressed in various organizations, from ITU to 3GPP to ETSI and also ORAN, of course. And it's very interesting to see that actually 3GPP had started NWDAF very early on, since release 15, but that was in the core network, and there was not really end-to-end consideration involving the RAN. So we had several forums, including the Future Forum, the WWRF, and also WAIA. Joint hand, they delivered RAN data analytic, RAN-DA, to complement NWDA, which is composed of DODA and CODA. And this work did not make it into 3GPP, but did find a way made into ITU's work in the focus group of ML5G. And then in the meantime, as many of you know that we've talked about the establishment of ORAN Alliance instead of the RAN-DA, DODA, or CODA. Actually, we proposed the non-real-time rig and near real-time rig, basically the hierarchical rigs architecture together with SMO to bring AI machine learning into the RAN. And this hopefully, right now, I think our ecosystem are accepting this as the way forward, but we still have to see how this will facilitate 3GPP's 5G advance towards the 6G design involving the AI and machine learning. And I think for the time limits, I'm not going to cover the other aspect, but you can see that here SA5 has also MDAS or MDAF, and also AI machine learning management work that's starting. And then RAN3 also has 2 AI machine learning work items. However, it doesn't involve adding new functional element yet, or new interfaces yet in the RAN, which we feel that it's probably necessary and essential for 6G architecture. Well, for just this one page, we could probably talk for a whole afternoon. So I'm just gonna skip and I'll leave it here for maybe for discussion later. Okay, now going from 5G to 6G, we think that there are several fundamental rethinking that we need to have. First of all, so far, it's an add-on AI, kind of afterthought AI to enhance our 5G. But like many speakers had said this morning, for 6G, it needs to start with AI in mind. So it would be native AI. And that, I believe, one of the most important things is make sure that the data, the designing data is well thought out in a holistic manner, because our current network really does not have easily accessible data for many of the AI machine learning enabled capability to be materialized. Okay, so the data is going to be the key, and I think the data will be something that a lot of us will have to spend a lot of time to sort out for 6G. And then currently, whether it is use case driven AI capability or separate domain AI, core network, edge, and the RAN kind of all separate. For 6G, we need to look at the end-to-end total picture, and also we need to look at AI capability rather than AI use case. Okay, well, I show some use case using the rigs, but this is basically currently how everything is done. But really, a native AI network should be providing AI capability that can address a large array of use cases. Okay, large variety of use cases. And then so far, I guess our AI capability is also kind of a best effort. And though we don't really have a metrics to evaluate how good that the particular AI services really is. We believe going forward, we need to start considering multidimensional QoS of the AI services, which of course, not only in terms of the performance improvement, such as latency improvement, jitter improvement, frame rate, etc., but also the cost, like the resources it requires, the computation it requires, and the energy consumption that it involves. So we would need to evaluate the quality of AI services with multi-dimensional parameters and consideration. That's also something I think very important for the future. So I think I'll end my talk with this, because also in this morning in the breakfast meeting, I think Vishnu brought up the perfect storm that I used to talk about 5-6 years ago. I think this was 2017, 2016. Kind of was forecasting the impact at that time I was looking at the 5G era, but now of course I think it's 6G era. The impact of traditional on the traditional standards brought by the open source community's agility and also AI machine learning's innovative opportunity going down the road. So I think this three mixing it together will bring us very exciting kind of, I used to use a scary word that's called the perfect storm, but there is going to be rainbow after perfect storm if we sort it out properly. But these three elements is really also kind of a different way of looking at CT standards, IT open source community, and DT, the AI machine learning capability, looking at this ICDT convergences and brave new world that we'll be facing. Okay, let me stop here, but my colleague wants me to show something. This is a workshop that we are organizing at GlobeCom, calling Communication and Computing Integrated Network, CCIN, which I think some of the speaker earlier mentioned the CFN, maybe it's of a similar similar intention. But the CCIN really, in a way, is a natural derivative evolution of bringing AI machine learning into our network. Okay, because the computation power, complexity that AI machine learning will require in terms of our resource planning and how we can have a better joint design considering both connectivity and the computing is worth pursuing, I think, as a part of the AI machine learning related effort going forward. And the deadline for the paper submission of this workshop is actually basically the end of this month. So hopefully some of our participants will find it interesting enough to be part to submit your contribution. Okay, Vishnu, I'll send it back to you now.
Thank you very much.
I hope I'm doing a reasonable job in the time control.
Yeah. Thank you very much, Shilin. Thank you for staying late, and we appreciate your time. You know, Shilin was supposed to be here, but unfortunately she could not come. But she has stayed late. It's night for her. Thank you very much, Shilin. And yeah, I think it's a perfect opportunity. As 5 years back, Shilin explained the perfect storm, and now I think it's a perfect opportunity that she's explaining. We should not miss it. We have thank you very much, Shilin. We have Ahmed here. Ahmed is our great collaborator from Arizona State University. Thank you very much for coming. And let us see multimodal sensing to digital twin assisted communications.
Okay, perfect. Right. Thanks, Vishnu and Thomas, for inviting me, and thanks everyone for attending here and online. So in this talk, very short talk, would like to basically motivate the use of multimodal sensing and digital twins towards communication, towards next generation communication systems, and also motivate the need for credible data sets and the need for, I think, community effort like in building and maintaining and standardizing these data sets. So if we start by general motivation, looking at, okay, perfect. Yeah, if we look at current communication systems, so there are certain key trends. Two of these key trends are the use of large antenna arrays, so from sub-6 GHz massive MIMO or millimeter wave terahertz MIMO, cell-free massive MIMO, reconfigurable surfaces, and so on. So all are different ways in using larger and larger MIMO systems. Another key trend is the use of higher and higher frequency bands, from sub-6 GHz to millimeter wave and 5G, and potentially sub-terahertz and 6G and beyond. So if we look at these two key trends, they are mainly motivated by the need for higher data rates. So we want higher data rates, we deploy more antennas and more antennas, and or we go to higher frequency bands and also still use more antennas. And in order for this to scale, so we need to continue to scale these large MIMO systems, and also we want to be able to continue moving to larger bandwidths and potentially at higher frequency bands. But the problem is that they come with challenges. So the use of larger antenna arrays make it hard to, it increases channel acquisition overhead, and this makes it hard for these systems to support mobility and increases the power consumption, especially at the UE side. The move to higher frequency bands makes it hard for these systems to rely on line of sight, so they mainly rely on line of sight links that's associated with higher with challenges for reliability and latency. So, for example, anything can block the link, and then this requires migration or the switching to another line of sight base station, which takes overhead and also challenges the reliability of the system. And broadly, we can think of the channel information as a key reason behind these two challenges, even the second one. So if we have a way to acquire this channel without consuming wireless resources, then we can form beams, the base stations and mobile users, they can form beams even with high mobility. And also if we know the channel, not just at the current moment, but also in the future, then base stations and users can proactively predict blockages before they happen and giving the network time to make proactive decisions. For example, moving this user to another line of sight base station or switching to a different beam. But how? So if we have a way again to acquire this channel knowledge, say with genie-added approach or with free without in terms of wireless resources, then this could be a key for overcoming many of these challenges and then enabling these systems to scale in a number of antennas and frequency bands. And this motivates the use of machine learning and multimodal sensing. If we look at the channel information in general, it is a function of the different aspects of the environment, geometry, etc., and locations of the users and base stations. But these functions are hard to characterize analytically, which motivates using machine learning to learn this mapping from, imagine if we have this machine learning models that knows how to map location information, geometry information to channel information or beamforming vectors. And if we have a way to acquire these inputs without consuming wireless resources, then using this machine learning model, we can predict as a channel even for large MIMO systems. And how to acquire now these inputs? So this takes us to the use of multimodal sensing. So if we all the way from and when I say multimodal sensing, so this includes basically all modality or all sensing modalities that can give us information about locations and geometry and of the user, of the scatters, dynamic scatters, and so on. So this includes things like GPS or LiDAR or radar, even visual cameras. And now what's very interesting is that as we go to higher frequency bands and larger antenna arrays, so we start facing these challenges in the channel acquisition, but in the same time, the channel information becomes more and more dependent on the location information and the geometry information, which makes it very intuitive, in my opinion, to start using this information because they will even benefit the channel acquisition in these large-scale MIMO systems and higher frequency systems more. And this motivates what we call multimodal sensing aided wireless communication, where we imagine different user devices and infrastructure side units will have different types of sensors. And these sensors will provide a lot of information about the positions, orientation, shape, geometrical shape and mobility patterns and so on of the devices, of the different scatters, mobile scatters in the environment. And all that can help the network build this perception about the environment. And this perception can be used to do a lot of interesting decisions on channel information, maybe not acquiring the exact channel complex vector or complex matrix, but at least provide some information about the dominant subspaces of the channel, beam alignment, decision, beam management, handoff, and resource management, and so on. And this eventually can enhance data rate, reliability, latency, mobility. Now, in order to investigate these directions from research and then build products and so on, we need to have data sets with coexisting communication and sensing modalities. So we need in the same time that we have this, say, wireless channel, we know what was the LiDAR scan, we know what was the radar image and so on. And with this motivation, we built this data set DeepSense, which is publicly available data set. It includes data, more than 1.5 million data points. I think you will change it. So. Okay. All right, perfect. So it includes more than, thank you. 1.5 million data points, multimodal data points, including wireless information, camera, radar, LiDAR, GPS, IMU data, and more. And they cover different use cases from vehicle to infrastructure to vehicle, reconfigurable surfaces, drones, and indoor cases, and so on. I had a video here. It will not play now because it's a PDF, but this gives you like a sense of what I mean by this data set. So we have visual data, at the same time we have the radar, LiDAR, and wireless, say, beam forming information. We have also released recently this V2V dataset portion of DeepSense, which includes large-scale dataset collected from 2 vehicles with different communication and sensing equipment that are also publicly available. Now, with this large-scale data set, we think we can study a lot of interesting problems in wireless communication and also sensing. And maybe more interestingly is that because we have large-scale data set that collected from more than 20 different locations with sufficient variance, so we can use this data set to study a lot of interesting machine learning problems in transfer learning, fusion learning, data fusion, and more. And this is now talking about data sets and collaboration from community. I mean, first we used this data set last year in ITU competition on multimodal sensing aided beam tracking, and I think there is a need to community to continue to support data set effort, and not just for the generation of the data set, but also for accessing the data and making this possible for everyone. Okay, I was talking here about some of the applications that we looked at in using this data set, some initial results on, say, multimodal sensing aided beamforming on the left. Again, that was a video where we're showing a live demo for real-time beam prediction using only vision and position information, so without using any wireless resource. And we show that we can still maintain very good data rate by just relying again on this multimodal sensing, enabling again this millimeter wave systems to scale a number of antennas and data rate. We also looked at things like using radar information for proactively predicting blockages before they happen in realistic environments. So these are all papers that you can find also on our group website. And now if we want this sensing information, now if we want to really take this to a network perspective, we need to overcome some of the challenges. One of them is the coverage difference between sensing and communication. So communication coverage is typically, at least in millimeter wave, you can think of it as a few hundreds of meters. But in sensing, so most of sensing modalities, the range is maybe tens of meters. So this may motivate some sort of distributed sensing aided communication, where we will not have just one sensor per base station, but maybe you have a network of sensing that is helping a network of base stations or network of infrastructure. Now, if we look at all this multimodal sensing aided communication use cases, they may be interesting for line of sight applications, but if this vehicle wants to connect to an line of sight base station, then it maybe needs more than just its sensing modalities. If it uses the classical communication pilot signaling for establishing this link, then this overhead will scale with the number of antennas. But if it has some information now about not just the sensing, but also the 3D map of the environment, then it can potentially use this knowledge to that maybe include also the location of the base station. Then it can use this knowledge to establish some information about the channel information. And if it uses also its multimodal sensing sensors, and maybe from the vehicle and maybe from also other sensors distributed in the environment, it can also acquire knowledge about the dynamics in this environment. So it can have like 3D map information of the say static objects in the environment. It can have some information about the locations of the base stations, including maybe panel configuration, number of antennas, orientation, and so on. And it can also have information about the dynamics in the environment. Now, fusing all that together, it forms some sort of real-time digital twin of the environment. So it's different than when we talk about digital twin of the network. Here, I'm talking more about the environment digital twin, physical environment digital twin. And at least theoretically, as we go towards better mapping and multimodal sensing and real-time ray tracing, then it is not it's not as futuristic as it may look to run some sort of near real-time ray tracing on this real-time 3D map to acquire some knowledge about not necessarily the complex channel matrix, but at least the dominant channel subspace, or maybe what is a small set of beams that the space station or UEs need to look through instead of searching over the larger set of code book of beams. And again, as I said, like with the advances in 3D maps, high fidelity sensing, it doesn't seem very hard to build some sort of real-time 3D maps as look a little bit in the future. And also looking at the advances in real-time ray tracing, which is already advanced by a number of companies. then running real-time ray tracing again on real-time 3D map to have like some sort of real-time or near real-time digital twin, maybe running at the edge seems to be an interesting concept. Now you can think of this digital twin all the way from having a local digital twin that's maybe a device is accessing its own digital twin using its own sensors, maybe on device at the edge or cloud. Or you can also think of a different level where different devices somehow subscribe to a global digital twin that they all access. So they can all fuse their sensing information to build a more global and a more complete digital twin. But maybe every device can use this digital twin to make its own decision. Or maybe in an ultimate way, you can think of this global digital twin with also coordination between these devices, not just in fusing their sensing, but also in making joint and coordinated sensing and communication decisions. So they know maybe this car is here and this side unit is here. Maybe they don't need to sense the same thing again. They don't need to transfer all the same amount as the same data again. They can coordinate the sensing decisions and also the communication decisions, whether in a distributed or centralized way. So we have this magazine where we talk more about magazine article. We talk more about these different levels and different details. Now, how can digital twins help communication systems? We can think of different ways, all the way from building realistic site-specific, right? And this is very important, synthetic data sets for pre-training machine learning models. So they are not just statistical models that are averaged across different sites. Many of these physical layer communication, physical layer gains for channel estimation, pre-coding, and so on from machine learning, they appear mainly when we look at site-specific, leveraging the site-specific information, whether making this channel prediction site-specific or making these beam prediction models site-specific and so on. So it's very important when we talk about site-specific synthetic data sets to also account for the site-specific aspect and the spatial consistency and all these important factors. So we can use these. Imagine the base stations that's deployed in a certain section of the city. Now it can access a digital replica and can get site-specific information from the same location with the same panel orientation and beam configuration and so on, and then use this information to pre-train these models, which can reduce the amount of real-time of real-world data sets. Make these models also more robust to unseen scenarios. It can also be used in maybe an ultimate way in making or aiding real-time decisions or near real-time decisions for these networks. And maybe in an ultimate way, you can think of these digital twin or these digital twins as twins that will be sitting on the side, on the edge, maybe, or cloud, that will keep learning and adapting for also every site over time. So all these models from ray tracing, 3D map modeling, ray tracing modeling, communication decision making models, and all that. So all these are models that may keep adapting and calibrating to the environment over time, so that they become more robust and more accurate in their decisions. Okay, so there are several interesting applications for this environment, real-time environment digital twins, all the way from this physical layer examples that I mentioned to maybe helping access and user association, handoff decisions, service migration, proactive caching. So for example, if this base station knows that this user is this bus is blocking this link for a few tenths of milliseconds, then it can make some proactive caching decisions. And anyway, so a lot of interesting applications. Now, in order again to do research and to develop these different ideas further, we need to have now a data set that's not just including synthetic data or that it includes real data, but we need to have data sets that includes both synthetic and real world data from the same site and the same deployment. And for that, we built, we're now still working on the new data set, Deepverse 6G, that is essentially built to be a synthetic version of DeepSense. So with DeepSense, we have this multimodal sensing and communication for different use cases. And Deepverse is a synthetic data set, building on our previous work on Deep MIMO, but extending this to beyond wireless to also LiDAR, radars, wireless, of course, and vision. And of course, the beauty of a synthetic data set is that you can tune the different parameters to cover a lot of use cases that are hard to cover with just real data. And also we are building some of the scenarios in Deepverse to be digital replicas to the scenarios in DeepSense. So for example, in the same location and site. So this is one example scenario for DeepSense and Deepverse, where we are modeling the 3D map, including the material information, mobility information, as well as the panel configuration orientations with the height. We measured the beam patterns of the physical array, millimeter wave phased arrays that we have, and we modeled all that in the digital twin. So this is a digital twin that includes, it's not just a 3D map, but it also includes a lot of information that try to mimic reality as much as possible. And then we can use this to do a lot of interesting research. So again, that was a video, but again, we'll not play it, but we're providing early access to researchers who are interested. So if you are interested, let me know. I can give you access to this data set in beta version, and just testing now. Okay, so that was also one application where we use this digital twin scenario to show that we can massively reduce the amount of data sets, real world data set, by relying on the synthetic site specific data set for an application of position aided beam prediction. For sake of time, I will skip this. Again, we have a paper that was published in ICC on this application. Now, if we to summarize, so more antennas, higher frequencies are key trends, but they come with challenges. And having the environment, having some perception about the environment could help the network make different decisions that can maybe overcome these challenges potentially. And this perception could be built using multimodal sensing and then all the way to digital twins. Vishnu asked me to kind of provide some thoughts on how ITU maybe can help and community in general. So a few things. I mean, first, it's very important, of course, to kind of support dataset activities and building larger and richer datasets. And there are different ways to do that. It's also, of course, important. I mean, for this particular direction, and there's a lot of important standardization work that I imagine will come sometime about integrating this multimodal sensing in general in 6G and beyond. And another last point here is about as we talk about all this research in AI, multimodal sensing, digital twins, and all that. This all requires a lot of compute requirements, and this, in my opinion, is also challenging in terms of the gap between researchers working in developing countries compared to other researchers who have access to these large resources. So I think when I was doing my master in Egypt, like 13, 14 years ago, all what I needed was just a laptop maybe and access to MATLAB. Now, if I want to do research in AI or digital twins, and then even just the data set to download the data set, it's now tens or hundreds of gigabytes and a lot of compute requirements. So I think having some sort of access to compute capabilities is not sure how to do that, but it's definitely will become more and more important as we go towards these new research directions. Right, so that concludes. Thank you, and look forward to your questions.
I think those are golden words. I think what Ahmed just now told are exactly the points that we should be looking at. I don't know what your idea of vacation is. Ahmed is on vacation. So what he's here for presenting to us, Jose, please.
Okay, so first of all, thank you very much, especially to Vishnu and Thomas for the great organization, and thank you also for inviting me to share some thoughts and ideas. So I'm an associate researcher at Telefonica Research, and I joined the group, the Telefonica, like almost 1 year ago. So I would like to share some vision on my transition from academia to industry, and also to share some works that we are doing in the area of deep learning applied to mobile and network planning and operation. Okay, so first of all, let me briefly introduce my group. I'm in Telefonica Research, which is Telefonica is the largest mobile network operator in Spain. Particularly, we are a technology subsidiary of this bigger team, this bigger company, Telefonica. So we are a multidisciplinary team of research scientists working mainly in 4 different areas, covering networking and distributed computing system, machine learning and deep learning, security and privacy, and human-computer interaction. Currently, the team is growing, and now we are 27 researchers, and we hold an open collaboration format with mainly public institutions, including research centers, universities, standardization organizations. And our research is highly supported by funds from European projects and also national funding. So I particularly work at the intersection of these 2 areas. The format is a bit modified, but it's okay. I'm working at particularly at the intersection of networking and the use of deep learning. Okay, so in previous talks, we have already discussed about some interesting use cases and applications. So for example, in 6G networks, we expect to see more applications with increasingly complex demands from the operational point of view. And this may include applications around extended reality. So the combination between augmented reality, virtual reality. Now we are talking about mixed reality, and all this towards the materialization of the metaverse. At the same time, we are working on creating smarter cities, smart factories to transform the industry into a new era, and also on smart agriculture to make it more sustainable and work towards the sustainable development goals. As a result, most of these applications will be supported by networks, and we will need a huge leap in terms of intelligence and automation. And I think that the main challenges are in 2 main directions. The first one is that we need to work hard on efficient real-time data collection, sensing from the wireless environment. So this is, for example, related to the previous talk, efficient processing, and of course, creating decision mechanisms that can efficiently and quickly adapt to the network dynamics. And the second line is that we need to work on towards more flexible and fine-grained control. And this is also related to some works on virtualization, like the all-round talk that we already had. So the idea is that we'll need to support a diverse set of complex requirements. So for example, in 6G, we'll have more stringent requirements in terms of bandwidth, ultra-low latency, extremely high reliability, and also we'll have new requirements, for example, those related to very high-speed mobility. So the community is talking about the use of non-terrestrial networks, and we'll need to support very or high-speed mobility, for example, to control UAVs. Okay, so in all this context, during the last few years, we have already seen many groundbreaking applications of deep learning to many network control and management use cases. And of course, during the last year, we have seen a revolution in the field of machine learning around, or with the new applications around natural language processing, transformer-based models, and reinforcement learning with human feedback. So today, I think that we must say that deep learning is probably or will be probably a cornerstone for achieving network intelligence and automation in 6G networks and the next generations. And I think that it's particularly interesting because of three main features. First of all, it will enable us to process the vast amounts of monitoring data from distributed network elements and deal with the heterogeneity of networks. Then to gain insights and find complex data patterns into all this network data, and ultimately to create intelligent agents that can enable us achieve more efficient network automation. So if you remember the title of my talk, this is my main motivation of this talk. No? Now we are forging the networks of tomorrow. So we need to think carefully about the technology and building blocks for these networks of tomorrow. And I think that deep learning will have a main role. So we need to think about the opportunities and the open challenges on how to efficiently apply it for different network related tasks. And since I'm working in a mobile network operator, my main interests are on the applications of deep learning for network operation and planning. And well, I have some time limits, but I would like to share quickly some recent research work that we did in the area of network planning. So from the practical point of view, for a mobile network operator, the rollout of a new generation poses novel hard challenges. And it involves several cost-benefit trade-offs, such as we may want to maximize coverage of the new technology, but at the same time, we may want to use new frequency bands to maximize capacity. And at the same time, of course, we need to meet the quality of experience requirements that are set for that generation. No? For example, for 6G, we expect to have very high mobility. We need to take into account this new aspect. At the same time, we have new technology aspects like new frequency bands. So for example, in 6G, we expect to use terahertz bands for specific use cases, and also new equipment like MIMO, advanced MIMO techniques, or reconfigurable intelligent surfaces. But if we look from the perspective of the network operator, it's very important to think that we are building a new generation on top of existing infrastructure from previous generations. So it's very important to think about all that infrastructure, including the cell sites already deployed, the cabling, and the power supply infrastructure. So we need to optimize planning, also considering the reuse of this infrastructure. So there are many dimensions and many things that we need to take into account in this planning process. And nowadays, the state of the art, arguably, if we look at commercial tools, is mainly based on physics-based propagation models. So with these techniques, we can perform cell planning. And of course, we also leverage some information from previous generations, from monitoring platforms in previous generations. So we started from this context, and we started with this question. No? So can we apply deep learning to enhance all the radio planning process for next generations? And well, we came up with a solution. This is a work that we developed recently, and it's an ongoing work. Let's say that it's a first phase towards a more ambitious result. But the main idea is that from the operator perspective, we have already monitoring platforms. So why don't we use all the data from current deployments as a big sensor of the radio environment to then predict what would be the resulting performance for new cell placements? So we use historical KPI records from previous generations, and we propose what we called the what-if planner module. And basically, this module relies on a graph neural network model that represents the radio access scenario and allows us to predict what would be the resulting performance for specific cell placements. I will show some results later, and we validated it particularly in the transition from LTE to 5G new radio to 5G NSA. And the idea, if you look at this figure, is that we can use this what if planner module iteratively refine the planning process by simulating different deployment strategies, looking at the resulting KPIs, and iteratively find new, more optimal placements. So, well, this was in the context of a collaboration with some researchers from the Polytechnical University of Catalonia. I won't go a lot into the details, but I would like also to say that, well, in the past, I was working also in the context of the Graph Neural Networking Challenge, and I was exploring the applications of graph neural networks. And I think that, again, for modeling the radio access network, they have very interesting properties. So the core feature of our what if planner is basically that we represent the radio access network as a graph with all the LTE cells and some KPIs collected on those cells. And then we represent in that graph some candidate 5G cell placements. And as an output, well, we use a graph neural network model to process all this graph and finally produce the resulting KPIs. So here you have some small results with real world data from the area of London. So what we did was to train our what if planner in an area of London, again, to model the transition from LTE to 5G NSA. And if you look at the results in blue, the box plot in blue, these are the results of our solution. Basically, here we have the results when we apply our what if planner to another different area in Greater London. And we see that even when we apply it to other area, we get good results. We tested it with 3 KPIs. Again, this is a work in progress, and we plan to extend it to other relevant KPIs. But basically here we have physical resource block utilization and uplink and downlink throughput. And overall, we can see that the mean relative error across all these KPIs was below 20% in the worst case for the uplink throughput. And the takeaway here is that by using a graph representation and a graph neural network model, we could effectively capture the relationship between all nearby deployed cells, 4G cells in a given area. And this enabled us to predict some relevant KPIs on candidate 5G cell placements within that area. Okay, so before I finish, I would like to briefly share some open challenges and future research directions that I think are interesting in the context of deep learning for 6G mobile networks. And the first message, and this is because I recently shifted to an operator. I think it's very important to take into account this message. Network engineers don't want to use a black box. And we still need to work a lot on that, in this. So we need to improve a lot in explainability, even if it was a hot topic during the last few years, there is still a long way to achieve it. And I think that a very interesting direction is to produce not only some insights on some interpretations on the output and the decisions of the model, but human readable descriptions. And I will share some ideas on how we can work on that. Connected to this first point of explainability, we need to think about usability. Nowadays, we have very efficient tools based on deep learning for network analytics and also for decision making. but still there are many open challenges towards creating more actionable recommendations for network engineers and achieving full automation. And a clear example of this is that if we look at the literature, we find many good solutions for anomaly detection in the RAN, in the core network. But then if we look at root cause analysis, the set of solutions is much smaller and has more limitations. And if we go to the next step towards troubleshooting, definitely there is a lot of work to do. No? So how to fix the problem, how to identify what are the faulty and devices and what's the configuration problem. No? And well, another important area is around automation, and this is very connected with the talk we had this morning, sorry, on MLOps by Sally. I think it's very important when you think in the context of a network in production about how to automatically retrain the model, how to check that the performance or the accuracy is within some expected confidence intervals, and how to maintain all the deep learning based pipeline, including data collection, processing, training the model, and putting it in production, for example, in the edge. And last but not least, and this is connected also to the main goals set by the United Nations, we need to think about how to limit the energy consumption. If we look at the area of NLP, recent large language models, the trend is having larger models with larger parameters. And I think that we need to think how to design good training and deployment pipelines, and also how to reduce the size of models applied to networking, given the distributed nature of networks and the massive amount of data they manage. And for example, in this line, I think it's interesting the works that have been done in the area of machine learning quantization, but still we need to work a lot on that, also to think on how we can efficiently use the resources at the edge in the network. And well, I had like a very long list of future research directions that I think are promising, but to make my talk shorter, I finally decided just one, which I think that can be the killer app in terms of operation in mobile networks. And of course, we saw the revolution in the field of natural language processing during this year, no? And I think that I'm pretty sure that in a few years we will work a lot on unlocking all the power of these models for mobile network operation. And one first approach is that I think that can work, no, for mobile network operation, is that we already have many solutions based on deep learning for network analytics, and these solutions can produce either labels or values or decisions. No, in the end, these models can be easily adapted to produce data embeddings instead of the final outputs. Data embeddings are basically low-dimensional representations that contain only the relevant information for the model to produce the final output. So if we use these data embeddings and use, for example, pre-trained large language models to produce some human-readable descriptions from those embeddings, we can create what I call the virtual network assistant. No? We can create an assistant that can directly produce actionable recommendations for network engineers. And I think that nowadays we almost have all the technology needed for that. Maybe we need to work more on creating good data sets and open sourcing this technology. And thinking about the longer term, these kind of solutions can also be integrated into autonomous network controllers. No? So we can produce or use these NLP models to produce directly the set of configurations and instructions needed to deploy them directly in the network. And this is also related to some talk that we had this morning, no? Where we can use language models also to create some structure on the data. And well, that's the end of my talk. I hope that you found it interesting. And of course, if you have any questions, I'm open for that.
Thank you so much, Jose. I think this is kind of answered some of the questions that we were discussing earlier as well. Can I ask Paul, please?
Thank you. Right, hello, we're almost there. The coffee is waiting. We've got like a very, I'm assuming quite a short talk if we want to have a discussion session. So I'll be short and sweet. So my name is Paul. Opposite to Jose, a year ago, I used to work in an operator, but now I work in Hogwarts or the University of Glasgow. And so I'm going to talk about why telco should stop solving problems to survive. But what does that mean? So super high quality content driven description of a mobile phone network that we find today. There's stuff, it's connected to other stuff. There's networks connected to other networks and the internet. There's things talking to people, people talking to people. That's nice. There's also toothbrushes, because for some reason we thought it's a good idea to shove a Bluetooth chip in a toothbrush because that was necessary, but we did it. But the problem of doing that is that we end up with this. And this is the kind of reality that, you know, networks face. I think this is a kind of what we just heard before. And thank you so much to all the other presenters and organizers for giving me the giant setup, because I don't have to talk about most things now. So yeah, you have pressure coming from the outside. You have more users, you know, who don't want to pay more for different things. We have higher coverage demands so that we can use our phones in different places. And you have these things talking to each other. But equally inside, from the operator's perspective, you want to reduce what you're paying to run your network so you can make profit. You want to save power because sustainability is increasingly important. I think the other week, one of my colleagues was saying about how if we have any sense of production deployment of ChatGPT, it will burn through 50% of the UK's carbon budget for all of the ICT sector. Right? So this is not a scalable thing in terms of power. You want to fix faults and you want to increase throughput. Fine. So what do people do about it? They come up with solutions, right? So, you know, we find interesting ways to bring different types of automation into our network. This is one little startup, well, not little, growing startup that happens to know. And here is a set of different solutions that they offer for different things, from quality of experience prediction, you know, business analytics, traffic decomposition, etc. Many people offer many of these type of things. It's just to say this is what companies do. They offer solutions to solve problems. And academia do this too, you know, in terms of, oh, if we want to do radio channel slicing, we're going to bring an interesting, intelligent way to make that happen or perform in an automatic type way. And if you decompose this down, it usually is some combination of intelligence, and we've been hearing about, for example, cognition this morning, etc. And that is then applied to the use case, right? I'm not telling you anything you don't know. I'm simply kind of setting the scene. But the problem is, if in this kind of way of creating solutions by combining these different things together and packaging them up, is what does that mean, right? So up in the top left, you have the use case that you want to actually solve. And that has to successfully operate at different times of the day as the network behaves in different, you know, undulations of people waking up and going to work, or people being asleep, or software updates. Then you also have to consider, you know, the geographical context in which you're actually trying to achieve your automation. Is this rural? Is this downtown Shibuya in Tokyo? Is this, you know, super urban Geneva? Then you have to cross that with the particular machine learning or AI technique or technology that you want to configure to make this happen. And what does that need in terms of training, in terms of serving, in terms of doing inference and such? Then you have to take into account of the errors that will come along the way that you can think about. And then there's always the X factor of, well, the thing you just simply don't know about, right? And to make this possible, you need this, right? You need your army of engineers who are sufficiently trained, not only in the machine learning or AI technologies, but also in the specific domain that you want to try and apply this in, right? And you know, that's not good, because people are quite expensive. And so at the end of the day, I think it's fair to say that this isn't the most scalable of solutions that we have to do. So So what do we do? And I think this pitch, I guess, is a little bit different from perhaps the other things we've been talking about, but I thought I'd give something a little bit left field, as they say. Okay, so how this works at the moment is that a very capable person will come along and they'll be given their challenge, for example, deep learning prediction of traffic behaviors, whatever it happens to be, and they take together all their knowledge and they produce a solution, some sort of hopefully reasonably self-contained thing that can be then applied in the network. Perhaps it comes with a license, perhaps it comes with a maintenance agreement, but it's a nice packaged thing. But of course, the reality of what's happening here is that when someone or a team sits down to actually do this, what they're really doing is, you know, they have the wealth of their own experience from whatever it is they've done before. They have, you know, things like GitHub or many of the different open source projects to help them. They have Stack Overflow to help them fix their bugs and realize what's going on. And they have a community of people that have gone off and create what I tend to call Lego blocks of functionality, whether in, you know, logging mechanisms or pre-trained models like PyTorch or something smaller. So it's this modularity bit I think I want to hit on, right, as being a key thing that we should be aware of that's part of this process that we use to create solutions. And the solutions themselves are composed of modules, right? And this is normal, right? I'm not telling you things that you don't know. But this is what you find in the world, where it's the periodic table of elements that we use to make molecules and, you know, bigger composite alloys, or, you know, when we build our circuitry, the different capacitors and resistors and things that we plug together to make the thing that can do something that we actually want to have. The machine learning technologies or just Lego blocks themselves, because Lego's fun, right? So in terms of that being available and embracing this idea, open source, you know, we've heard it all today, is becoming increasingly, I guess, accepted within the telecommunication industry in various ways and to different levels of things. So this idea of reusing things, accepting contributions from open source is, you know, it's becoming accepted. And again, if we're thinking about modules or building blocks as opposed to entire complete finished solutions, perhaps some of the challenges that we find in open source to do with maintainability, you know, maturity, constant maintenance becomes maybe easier because the size of the artifacts we think about is now smaller and more diverse. And perhaps it encourages participation from other players that aren't necessarily big vendors. So the community is waiting, right? People want to get in on this. I think every grant application, public paper thing that we try to put in says that, you know, where's the third sector? How do we get away from the big vendors and embrace all these kind of new startups that want to come into the scene, right? Because they want to contribute. So maybe this modular way of thinking about contributing to the software ecosystem in telco is kind of a cool way, and one that actually might have some traction and possibility to get behind it. Because if they can make the modules that are then being assembled by engineers, then perhaps you actually get scalability. Maybe you have, you know, different engineers working on different things. And, you know, what if we could then take those developers, those intelligent engineers that are assembling these modules and their own experience into, let's call them solutions. And what if we could begin to look at how we automate that process? You know, and spoiler, I'm part of focus group autonomous networks. So this little magic bit here is where autonomous networks is kind of coming in. And then because you automate the process of composition of these different software blocks into different things, then you get diversity in the solutions that are being created, because you're no longer kind of being bound. By automating the process, you can start to explore different things. You can generate different solutions by reusing, you know, this bulk of effort that we see from the modules. So a whole chunk of what I'm very interested in is evolution. And when I say evolution, I don't mean, as people usually say in terms of evolution of the network, I mean like evolutionary computing. So another form of this is more commonly kind of genetic programming. And evolutionary computing is really interesting because it's the same process that you use. You know, there's no training involved. You know, it's just the same process, and you can apply it to different things. And previously, in different spaces, I've talked about how NASA have used it to design antennas. Google have used it to rediscover machine learning algorithms. And it has these two nice properties. And the first property is that it's really good at searching large spaces efficiently. We heard from SR Con that, the state space that you get when you try and do this type of work in this space is enormous. And so we need efficient ways to be able to explore that. The second thing that evolution is very good at is this ability to kind of do multi-optimization problems. So you have these nice Pareto fronts where everything along the front on the curve here is as good as the other one. But if you have a particular preference for, in this case, F1, you can go there without being any less bad with regard to F2 of being overall optimal, right? So evolution as a strategy or as a mechanism or as a technique is a really interesting one to explore. And it fits into this idea of generative things that we've been talking about, because it's an approach that we could use to combine modules to create different designs. Now, one of the, you have to throw ChatGPT in there because, you have to, it's cool, right? But practically, one of the problems when you talk about modularization of things is people say, well, what about the legacy stuff? We have all this code kicking around, we have to build on top of it, can't just make it go away. So one of the things that actually one of my team is looking at is this idea of, well, can we use ChatGPT to ingest code and then start to semantically describe what it's doing? So the idea is you get a block of code like you would see on the left, and then can we use ChatGPT to decompose it into a structured, kind of semantically described set of modules? So we can, simple example here is inputs and aggregation and analysis. But if we can do that, then, and given the fact that it's also code, it means that we could actually start replacing it, right? Because if we have another module that's tagged as, let's say, aggregation or sensory input, given the multimodal example, you could say, well, we can now start swapping these things together to come up with different designs that could be potentially used to achieve or solve the problem. And because we're working with code here, the structure of it being composable and actually being executable code is kind of given for free by the fact you're working within a programming language. A note on intent. Okay, that's kind of cool. That's exciting. We're talking about generative approaches and doing different things. So the natural thing, and we heard it also today from earlier speakers about this idea of, well, how does intent fit within this kind of generative world that we're talking about? So I'm always confused by intent. I don't really know what it means. I've heard about 50 different definitions, and I'm not intelligent enough to figure out which one is the right one or which one makes the most sense. So this is my, really terrible attempt to say what I think in my head when I hear about intent. So there's the human intent, or, the kind of unstructured representation of, I want this, or this is the way it should be, that I can express in my language. And somehow we know that there'll be some kind of transformation into what I would call more of a structured intent. So this might be like a declarative specification. If you're of this community, you could say things like it might be a utility function or a cost function that defines the goal that you want to achieve. And then somehow you have a transformation into a thing, an artifact that can then actually interact with your infrastructure or your network that can actually go and achieve something. So especially for the second arrow and for the structured intent into a thing, this idea of generative, for example, evolutionary based approaches might be one of the solutions we could use to try to realize that, in addition to, NLP to try and give us the structured intent to get us going. And when you start doing that, you look at, well, what is it we want to convey, right? What is the intent we want to tell people? And I think the declarative stuff is nice, but there are many other types. But irrespective of the format that we specify, we have to try and capture what we're trying to convey as the meaning of the intent, right? So usually it's optimality, right? Make it cheaper, make it faster, make it more resilient, make it more robust, right? But especially when you consider evolutionary type things, these are the goals that you're setting down. Evolve me something that will be optimal with regard to profit or regard to time. But the really nice, I guess, scalable property of thinking like this is that optimal is just a number, right? It doesn't need to be focused on the traditional things of faster, better, cheaper. You can start thinking about, well, what's the embodied carbon cost of doing it like this? And because the mechanism is exactly the same, the generative approach that you would use should be able to explore that in exactly the same way as it would be for just straight up cost, right? So now remember back to the multi-objective element, you can set multiple objectives from multiple different domains and give it over to the system to try and explore, well, what is optimal for what I want to see? What are different compositions of these software modules that we could put together to try to realize a design that can fulfill the goal that we've set? And, you know, how long is a piece of string? Interesting people have been doing from Aiden, I'm not entirely sure how to pronounce this. I apologize to the authors. But in this case, they were using an evolutionary approach to say, well, how big should a module be? How can we take our existing code base and restructure the software to give us modules of different sizes so that we could then look for optimality and, you know, those different goals that we would want to see later on. And, you know, my own little throw into the mix in this one, this is a paper we recently submitted, unaccepted. But what we did up in the top left, yes, what you can see there is we built an end-to-end content distribution network system. So this is a real one. It's using Varnish production software. And the purpose of this was to say, okay, what does this look like in a real system with, you know, running criteria as we try and evolve it online, if you like. So the bottom left is the representation of the problem as an evolvable problem in terms of the genome that we're trying to evolve. And on the right-hand side, you can see that all we told it was simply say, you know, increase the hit rate. That's all we said. And the system was able to come around and evolve different configurations of strategies used within the load balancing, as well as configuration of the parameters of the Varnish cache to say, hey, look, you know, we made it better, pretty much is what you take from that. Okay, I'm blistering through as fast as I can. Controller. So focusing on the focus group on autonomous networks. Within that, we have this idea of the controller, right? There are many overlapping descriptions of controller, but this is ours. And the idea here is to say that a controller is effectively composed of modules that does something, right? If you take a closed loop and you kind of unroll it into a straight line, you get a workflow or a pipeline. Equally, if you take a pipeline, you can wrap it around, you could say you get a closed loop. So baked into the approach that we're taking in the focus group in autonomous networks is this idea of modularity and composability that would allow us to explore how we could use something like evolution to compose controllers for the operation of the network. And, you know, this is the wonder that is the focus group on autonomous networks. It's really lovely to see so many people that have participated in person for the first time. I'm really very chuffed about that one. And, you know, you can see the structure that we have where we've been looking at use cases and architecture and different things. And, you know, Vishnu showed this picture at the very beginning. And you can see in here, we have this idea of this kind of exploratory evolution subsystem. And that's really an attempt to try to capture this idea of generative processes within an architecture to realize autonomy as part of a systematic way that consists of also testing and validation, as well as deployment to consider real-time considerations as well as non-real-time considerations. So if you're super interested, please check it out, come say hi, and there's that. Just in terms of an obvious missing part, it's come up a couple of times today. How do we guide this, right? It's fine to say we're going to explore everything, but maybe the heat death of the universe would come first, right? Because how long does it take to converge and do these different things? So this was an attempt from last year's Build-a-thon activity to capture, I guess, a kind of ontology that represents this architecture in terms of the components that exist within it and their relationship to other elements. But I'd say from my perspective, this is one of the things that's missing in terms of how do we capture knowledge, right? Either by human, you know, and domain experts writing these things down, or how do we automatically extract knowledge from the systems to be able to build ontologies? I'm not an ontologist, so I'm just throwing it up as an unknown from my perspective. So maybe this is all as building up as, you know, FGAN comes into its third year and final year. Perhaps this is an interesting opportunity to consider, well, what's the next focus group going to be? And perhaps it's going to be exploring some of these generative aspects and designs by taking some of the use cases, mixing it with elements of digital twins, you know, living digital twins. You know, how do we shape the problems that we want to, you know, how do we capture the problems in terms of the use cases, in terms of the generative aspects to achieve the stability of, you know, not having millions and millions of engineers coming up with our intelligent control. Cool, and that's me. So takeaways are building intelligent solutions doesn't scale. it will work, but it won't scale. So perhaps modularity in generative designs present an interesting opportunity for pre-study standards work. And that's it. Thanks so much.
Thank you, Paul. And, I wonder if you just put together what Jose explained. He was talking about this deep learning based network analytics, and in that he talked about controllers, actionable recommendations, and so on. And then if you go back and put together what Abhishek was talking about in the morning, in terms of generating APIs and so on. And then if you come back to Paul, it's an interesting combination. So yeah, thank you so much. We have, I'm worried that cafeteria will close. Thomas, when does the cafeteria close? Is there still time? Okay, great. That means we have still time a little bit for questions. Any questions from the floor, please? Yeah, Abhishek.
What Paul, what you said, so you have this, let's say you have these building blocks and you have this secret magic sauce which binds them together and forms a cohesive whole. And now imagine these building blocks are disaggregated radio access network. So I mean, as we all know, there is a huge problem of this integration of different parts of RAN from different vendors. Then there is a problem with this brownfield deployment. You can't really deploy because you have existing investments, you can't just remove them and then use ORAN there. So I think, I mean, that seems to be like a perfect match for this kind of solution. So how would you fix the ORAN problem with this?
I would never describe ORAN as requiring fixing. I think, okay, so everything is just a tool, and every tool is good at solving certain problems and not solving certain problems. I think the power of the generative approaches is that it gives you the option or the ability to automatically explore, right? So if there's the capacity in that context, as you say, to let's say, how would this XApp be more appropriate for this context? It gives you the opportunity to explore, well, this composition of an XApp would be really good given how this behaves in different spaces, but it's not guaranteed to find a solution. And if ultimately the platform is not amenable to receiving an XApp and having it deployed on top of it, then you can't use this. You would have to find a different way, but it doesn't have to be XApp. So if there's any form of software control that would be possible, then so long as the modules exist to be compatible with that in terms of acquiring data from the platform and performing an action into the platform, then I see it as compatible.
All right, thank you.
Yes.
Yeah, thank you. Paul was simply fantastic there. And I quite appreciate the way you spoke. This is probably an addition or an observation, because it's a question most persons have been asking, that where do we place? He said something about intent, which is gradually being broadly used now. So he does, where do we place intent? And that is what I want us to probably briefly talk about, intent. But he took time to explain his own aspect of intent. And I am looking at it as something that is centric to different needs, because the definition at one point might not be exactly for the other. But I know quite well that the generics, as in trying to explain intent, is when you probably have very effectively, when you probably have an opportunity to get feedbacks from whatever operator, the human operator, and you probably get in between a knowledge-based manager that could aggregate those intents and straight to the controller, where you probably have an auto controller, and that will send the platform for, specifically for autonomous network, the platform for an ANM orchestrator that could possibly manage and monitor events very well before decision is taken. So what I'm trying to say is how to narrow down the definition of the intent you talked about, so as to know specifically these are the bounds for understanding intent, because gradually intent is getting very wide now. Thank you.
Thank you for the question. I think, as I said, those with better knowledge than I can probably give a more intelligent answer to this question. And please, colleagues, if you have one. I know that ETSI-ZSM have been looking at, descriptions of intent and intent manage and translation for different things. So I think that's an effort to constrain the mechanisms around intent. But I think it hasn't quite captured what is an intent in different contexts and to what level of abstraction that intent is being represented. And I don't have a good answer to that.
Thank you, Paul. Thank you, Professor James. There is a couple of comments online. I will just read them out, and I will request maybe Ahmed and Jose to comment. I think Marco is asking about the physical digital twins, physical environment, representing physical environments. As I understand what he's asking, and between GNNs, because I think he's also referring to Henning's comment in the morning that the physical representation of physical environments are computationally costly, and that is true as well. I believe Marco is also referring to the real-time digital twins that you mentioned, and you also mentioned the multimodal data based the environment ray tracing and so on that you explained, Ahmed, versus the graph neural networks that you explained, Jose. I believe this is the question that he's asking, because I had previous conversations with him before. So what is your take? Do you have comments, Ahmed, first, please?
Is this fine? Okay. Yeah. So just to clarify, real-time digital twin, I didn't mean to rely solely on physics and numerical computations to do like classical, basically build like a 3D map and then run numerical computational methods and ray tracing to do ray tracing, and then go from there to, again, models to, computations to do classical, basically solutions to do, say, beam channel estimation and so on. But you can actually think of this in a also maybe modular way as models, right? So you have a model for building like a task specific 3D map, maybe that's helping the end objective. Similarly for ray tracing, similarly for the end, say, communication metric or quantities that you want to predict, whether it's beam or channel or resource allocation, whatever. And then many of these models could be also replaced or enhanced with AI and different approaches of machine learning or neural networks and so on. So you can even think of like ray tracing as a machine learning model that's maybe model-based machine learning models that will, and knowledge-based machine learning models that will get enhanced over time and calibrated with the environment as it interacts more and more with the environment, to reduce the complexity and computational cost, and also to train the different parameters and so on. So think of it maybe as a parametric-based ray tracing models that many of these parameters will be trained and fine-tuned over time using different machine learning. So I think, I mean, they are not like competing, but maybe they, you can integrate many of them together. All these like concepts. Cool.
Yeah, I agree with that vision, and I would add that probably GNN and in general graph representations are very interesting for implementing such kind of AI-based models for the radio environment. And yeah, also there are some advancements on that area that also deal with geometry. Geometric deep learning can be seen as a natural evolution of GNNs, and particularly in this type of scenarios, I think they can be especially interesting. So I see this more like complementary. For me, the real-time digital twin can integrate inside this kind of models based on GNNs or, for example, geometric deep learning.
Yeah, that's exactly the point. I believe that answers Marco's question. Henning, do you have additional things to add? I know you have done significant work here.
Yeah, I mean, I would see I think Albert has captured very nicely in his talk, right? So once you have a graph-based structure of any kind, you can apply GNN to the problem, right? And then I see the digital twin somewhat broader, right? There anything which helps you, right? So in this, let's say using ML to look into the future and then do the decision making or deploy an ML algorithm, right? To let's say test then your prediction and actions basically. Yeah. So I see them, of course, as related. Yeah. But like I said, for me, this digital twin is a much broader concept where actually many different techniques fit in basically. Yeah. So.
Thank you.
Can I add something? Yeah, so this was also in my list of future research lines but I shortened my presentation. I think it's very interesting also to think about how to maybe make a computationally expensive physics-based model, like so those based in ray tracing, and combine them with deep learning. So how I see it is that this kind of physics-based model capture the fundamental behavior of the radio environment. So we can have like good generalization if we use this kind of models in any area. But at the same time, when we want to apply them to the real world, we need to consider the singularities and the particularities of real world data, meaning that we can have missing data, we can have faulty monitoring records, etc. And I think that deep learning is especially good at this. So if we can combine the fundamental behaviors of more traditional techniques with deep learning, probably is a very good research directions towards creating more efficient real-time digital twins.
Thank you so much. And I think great discussions once again. We have our last session coming up, and that's a very interesting session as well.
Good afternoon, dear colleagues. I know it's difficult actually to speak in the last session. I hope I can keep you awake. I'll try to make it quick and smooth. My name is Fathi Abdeldaim. I'm leading the standardization R&D in United Arab Emirates. Second operator, do. And I'm going to take you in a quick journey, maybe from another perspective than what we hear today. It's really amazing material. So Vishnu, please try to stop me by the 15 minutes. So the agenda for my speech today is a quick brief who we are as a country, as an operator. I will go through the United Arab Emirates AI strategy for 2031, challenges we have for adoption of AI, and AI and 6G, but I will take it from another perspective. Maybe if we have another option, rather than talking about the RF, maybe about Li-Fi. I will speak about our footprint within machine learning for 5G use cases. And I will also discuss what we have been contributing last year to the AN focus group, and then the call for collaboration for the ITU and for the dear colleagues here, and the way forward last. who we are the second operator in United Arab Emirates, speaking after China Mobile with the dimension and the subscriber base. It's a little bit embarrassing. We are hosting like 8 million subscribers. That could be one base station for China Mobile. Anyhow, we are number 2 in the market, 94% market share. We have a wide spectrum of radio access technologies, starting from 2G, 3G, 4G, 5G non-standalone. Since beginning of this year, 5G standalone as well. We are offering IPTV services. We are the official partner of the Dubai Smart Government in a very demanding market, in a very dynamic market. I'm proud to say that from the standardization perspective, we are the forefront for MENA. We are the only GCF full member, the Global Certification Forum, which is the certification arm of the 3GPP. Our network is the reference network for the field trial, 2G, 3G, 4G, and I'm happy to announce since December last year, we are the only worldwide operator holding the status for 5G standalone and non-standalone. Our aim, our focus is customer. We are customer-centric operator, and we have huge ambitions I'm going to cover now. UAE is driving the AI technology in the Middle East. I would say that they try to put this as a part of the DNA of the citizens, of the economy. Maybe it's worthy to mention that the United Arab Emirates is the only country with a dedicated ministry for AI, and there is a minister for AI holding this position. The government has published 2 years ago the strategy for AI in 2031, and of course, the main pillars which is needed for this, 5 pillars: energy, technology, space, transportation, education. The main shared factor for these 5 pillars is AI and machine learning. We as an operator, we are driving this. We are the backbone, and maybe the COVID-19 situation has shown that telecommunication is one of the most important pillars to drive crisis and to drive innovation and next generation network. In a study published last year by the Future Foresight Foundation in UAE regarding the top jobs in 2040, actually the expectation is not that far from what we have now. I mean, they have drones, big data, and robotics. From my opinion, I don't think that we will wait till 2040 to see that actually these are the future pays for any job in the future. Also, shared factor here, it's AI machine learning. As I said, the government is driving this. I will speak about some initiatives. I will speak about some move in the geopolitical situation in the Middle East, which going towards this direction. This slide actually was presented in the beginning of this year for our board as a strategy for the company in 2023 and 2024. And of course, the main targets and objectives for being number 2 in the market, with a huge investment towards 5G standalone, to build a gigabit network. Despite the fact I have actually objection to the word gigabit, because if we see the current development in the market, I think we need to think about a terabit network rather than speaking about gigabit network. I will come to this in a couple of next slides. Next generation operation, and this is fully based on AI machine learning, upscaling the task force of the company, of the country. And what we try now, and we have proposed this to the government, is actually onboarding the academia. We have here a very nice sentence actually from Professor Tom, that actually the academia, they don't have access to the data. And this is exactly the pain point. And this is one of the points actually, and the call for collaboration within the ITU. I will speak more about this. Security, as I mentioned, the geopolitical situation in the Middle East makes security is a higher challenge than maybe elsewhere. And of course, we are a revenue-driven company, so we have to think about revenue streams, new revenue streams, because we have a board, we have a shareholders, they are actually requesting for ROI at the end. Okay. So current use cases based on AI machine learning, we have already two use cases live. The first one is a digital twin data center based. And so actually it gives the operator a simulation environment where they can simulate the operations, and this will impact the carbon footprint. And of course, it gives them the opportunity to build a real-time decision making platform without having the risk of going in a live environment. Of course, customized train models, and this is something we have heard many times today from Jose and from some of the other colleagues here regarding the data and the trained data. And here also I have another comment. Actually, the problem is not the data itself, because we as a service provider, I'm talking from a service provider, we have huge amount of data. The problem is who can control the matureness of this data. And this is something also we have raised to the ITU, and I'm having it today, also a call for collaboration. The problem is there is no data framework which can conclude the matureness. Who can use the data? What can we do with the data based on standard? So what's being done now, it's best effort. And of course, the platform is integrated with our IoT platform. The second one, which is we are driving a digital transformation journey. It's behind us. And the first one we have started is transforming our OSS based on AI. We are using 4 verticals. The first one is artificial intelligence, robotics, machine learning, and of course, the domestic expertise. And this is something I'm going to speak about, the challenges on adoption of AI machine learning, the lack of expertise. And we could see really first positive results in reducing our OPEX cost. We have now, and this is a new terminology being used in operators. Jose, you come from an operator side, and we speak now about time to revenue, not time to market, because it's not a matter of bringing a service live. It's a matter how to bring the service and what kind of monetization concepts you have behind the service. Of course, we could reduce our churn from adopting AI-based OSS system, and higher NPS. And here, the focus of NPS, we have a very demanding market, especially in the United Arab Emirates, and that makes your life really not easy. We have seen it that we are speaking to a very well-educated customer. We have seen it in the social media that some of the users really, they are that techy that they can actually challenge your engineer, and they have their own tools. They do the network speed, they do the check, they do the Wi-Fi check, they can crack your Wi-Fi security, and then they publish this in the social media. And this is a huge impact upon a company image if you are just operating as 2 in the market. Next slide. This is one of the slides that I like to talk about when I'm presenting in front of our board. Of course, speak about the future. Cloudification is one of the major infrastructure points that you need to consider. If you have the infrastructure, 5G, 6G, 5G and 6G and beyond. And for beyond, I will also speak in a couple of minutes. And of course, you need to have the right use case. So in this case, you think that we possess the future. In fact, there is a block it's missing here, AI machine learning. Because AI machine learning, even if you have the connectivity, even if you have the 6G and beyond connectivity, if you don't have that layer, you are not anymore in the future. AI machine learning is not anymore optional. Trends in the Middle East. Every year in October, Dubai is hosting the GITEX. GITEX is actually one of the biggest, if not the biggest, telecommunication exhibition worldwide. Being a standardization lead in the company, actually, I'm following the GITEX, and I'm preparing a report at the end. I'm submitting the report to the CTO, to the CXO, without covering some of the guidelines, some of the forecasts for the coming years. So the past 4 years, the GITEX was only talking about robotics and AI machine learning. Last year, in October, we had the GITEX. 2 weeks before the GITEX, Dubai hosted the first Metaverse Assembly, and it's actually sponsored by His Highness Sheikh Hamdan bin Mohammed, the Crown Prince of Dubai. Many people at that time were thinking, okay, Metaverse, what has this to do with an operator? And that was a big debate, by the way, until Apple announced I'm not an Apple user. I'm not making any advertisement for Apple. I'm an Android user. Until Apple announced this year their Pro Vision, and this is the game changer. So actually, from my perspective as Fathi, I think metaverse is going to be the killer application for the future. This is nice. It could be fancy. It could be a new revenue stream. We will have a problem in the spectrum, and I will speak about this in a while. So what we see in the Middle East, that the governments are driving, the governments are behind AI, machine learning, and now metaverse, and that needs a collective work, maybe guided by the ITU. And I think, thankfully, that the ITU, they have launched a new focus group for metaverse. The GSMA is working on the same. And maybe we need to think about maybe having an unified standard body for metaverse and AI machine learning. The European Parliament, they have started standardizing AI machine learning, especially AI after the ChatGPT. I think maybe we need to have this as an action point to agree on a collective work covering AI machine learning as a guideline. Challenges we have on adopting AI machine learning, as we spoke about today, data, the lack of trained data that we can use. As I mentioned, from an operator perspective, we have data. The problem is the maturity of the data and the responsibility of the data end to end. The second factor here is the lack of trained, skilled people, like data engineers, like machine learning engineers, AI engineers. Lack of plug-in solutions, which is ready to be used. The algorithm testing time and onboarding, it needs to be tackled and covered. There is no unified policies. For example, if we speak about a data framework, there is none of the standard bodies as of now is giving an end-to-end data framework. There is some silos. For example, the Canadian government, they have, but there is no unified standard for data itself. And that's maybe one of the goals we are raising here. We need to work towards having a data framework that covers all entities. And of course, there is no well-defined data platform for AI machine learning, and that's our call maybe for a MENA sandbox or a sandbox. AI and 6G, I think we have covered this many times. Of course, Open RAN is driving this, and we are very sure that it will be a sort of similar structure to the AI machine learning with the ORAN. But in fact, this is not the biggest challenge. The biggest challenge is in the next slide. Professor Harald Haas, he is actually the father of Li-Fi. In 2019, we formed the LCA, Light Association Alliance, which the official standard body for light communication. It covers all the light communication aspects, starting from Wi-Fi, OCC, optical camera communication, FSO, free space optics. And in one of his presentations, actually, he presented the following dilemma, and which actually we are facing as of now. In 2016, there is a study conducted, and they could show that we have a steady exponential growth of data of 60%. My work based on the data we have in our company, based on other data, actually we have 100% exponential growth in data consumption. If we add IoT devices and massive machine type communication, if we add the V2X, I think we reach 100% exponential growth of data. We are using Wi-Fi in 5 gigahertz, 500 megahertz. If we forecast in 20 years from now, where we have 6G as the official network technology, which we will having, simple calculation, 20 years, 60 multiplied by 20 years, so we are talking about 12,000. 500 megahertz for Wi-Fi, we are talking about 6 terahertz. The RF spectrum is only having 0.3. So we have a shortfall is more than 5+ terahertz. So we need a solution. Actually, the solution could come from Li-Fi, especially after now having Apple as an official. Metaverse is going to be a killer application. It's going to be a monetization aspect, if not to the B2B and the B2C in the beginning, but at least for the B2B. How to solve this problem? I think we need to think about an additional technology that it can be a part of the ecosystem. We are not talking about Li-Fi as a substitution for 5G or 6G. We are talking about Li-Fi as and a coexistence to Wi-Fi, and maybe to solve the spectrum crunch problem, which we will have very soon. Simply, light spectrum is 3,000 times more than RF spectrum. It's there, it's free. And the good thing is that the infrastructure is there. If you wish to know, just go outside and look on the ceiling, LEDs. We have published last year one of the papers, white paper under the supervision of Professor Harald Haas about terabit. And that's why I said we need to think about terabit, not gigabit networks. And it's mainly using the laser beam as point-to-point communication. We could reach with phosphor-coated laser beam for an eye safety level and a terabit connectivity. And this is something actually, I think 2 or 3 weeks ago, at NAFTEC in India, they could demonstrate live the first mountaintop 5G speed connectivity based on laser actually for one of the villages in the mountains of Pakistan. So we need to have a look again, and maybe this is something, again, something for the ITU. We need to think about maybe collaborating with the Light Association Alliance, because this is the way forward, as we need to have this at a paradigm shift. Use cases for AI, as of now in our company, we have this use case with customer journey based in AI. I will not go through the details. It's simply based on the data, based on the predictive analysis. We could use AI to utilize the customer behavior, and at the end to save the customer roaming charges. The other one is the metaverse digital twin, which is a live use case as of now. And instead of sending our engineers to the data center, actually they can use metaverse to tackle, to troubleshoot the full end-to-end data center connectivity issues. This is one of the use cases. We are proud, and thanks again to Vishnu, our participation last year. It was one of our colleagues inside the company, and he proposed building a global standard and guidelines for fixed networks. And it will be under the umbrella of the ITU. This use case has been accepted, and it will be published in the ITU journal. It will gather different stakeholders from the telecom operators, the civil and defense, the water and gas authorities, municipalities, and road and authorities, with the aim of building a unified committee for this scope. Okay, call for collaboration. This is actually something we submitted last year to the ITU CXO meeting, which we hosted in Dubai last year. And I hope really with this year, we will welcome Dr. Bilal again. We have submitted 3 proposals. They are all accepted. The first one is to drive a metadata global framework under the umbrella of the ITU. And this is, again, one of the requests we're still having for the ITU. The second one is creating a MENA sandbox. And this is something, I'm sorry, I'm over the time, creating a MENA sandbox where we can onboard the academia. We build a scheme to offer all participants the medium, the data, the trained data, where we can utilize the MENA sandbox for the participation. The third one, it was for a request for the ITU to tackle immersive technologies such as metaverse. And as we see here, with the announcement of Apple, I think it's going to be not an option anymore. So the proposal for the MENA sandbox is to gather the academia, the operators in the MENA region, government entities, startups, and especially for the startups, I'm pointing again here at Jose from Telefonica Germany, from Telefonica Spain. Telefonica Germany has created a very nice model, which is outsourcing the whole innovation part in BI to Wayra Germany. And actually we are looking at this model, and our aim is maybe to create a similar concept in the Middle East region, where we give the startups an opportunity, funding opportunity. For example, there is Dubai Future Foundation. They are actually scouting for use cases for talents, where if you need the technology, they will give you access to technology. If you need the fund, they will give you the fund. And that should be under the umbrella of a standard body, ITU, GSMA, ITSI, and the Unified MENA Sandbox. It could be hosted by DO or Etisalat, TDRA, which is the regulatory in the region, or maybe as a national service, gathering all the 3 entities. And of course, the main aspects for this to create an AI machine learning framework, standardize the use cases, and to agree on certification and acceptance criteria for the AI use cases, and of course the transformation, end-to-end transformation. I'm sorry, I need to jog with you. Can we move to the next slide, please? What we are expecting, what we are looking at 2024, we need to study the use cases for machine learning over 6G. Again, I will link this again here to Wi-Fi. We need to think about the spectrum issue. We have been talking all the time from use case perspective, from standard perspective, but from the technology and the spectrum perspective, which is an essential case, we need to think about this. We need to get creating the MENA sandbox. It's the call for everybody here is open. We hope of your support. We need to get AI up and running to work. We need to generate data. And as I said, we have the data, but we need to agree on the concept, how to use the data. And of course, our target is to create a reference model hub for the ITU, offering all participants this opportunity. Last from my side, the MENA region is getting a new wind. Speak about AI machine learning. And of course, the most important thing from my speech today is we need to think about Wi-Fi as a paradigm shift for the next 6G and terabit network. Thank you very much. I'm sorry, I'm over the time. Thank you. Thank you. I'm sorry for the time. Sorry, Vishnu.
Thank you very much, Pati. Thank you that there is a very emphatic message there. Can we move on? Maybe Frank, yeah.
Thank you. And yeah, I'm a bit nervous because, first of all, thank you a lot, because to me, it's a bit of a special being here today talking as a speaker, because as a student, I had the opportunity to follow ITU activities for quite a long time, since 2018. We were discussing that before. And all the things I learned, I think that are today somehow reflected in this presentation. So basically what I did is applying what I learned here and during my PhD and so on, and my career, and apply it to Wi-Fi, which is my main domain. I'm kind of an intruder here because Wi-Fi is something that it is not being discussed so much here, but okay, let's see how it goes. So basically the agenda, I like simple things, so it will be 2 points. First point is kind of first introduction to what is wireless unlicensed, what is Wi-Fi, and then kind of confluence on Wi-Fi and AI/ML, going from particular challenges, solutions, what's going on in standardization. It's kind of an overview. So yeah. So we can proceed. So, okay, I think it is very clear to all of us about the value of Wi-Fi. I mean, it's been here for quite a long time. We use it a lot. And this is translated into the impressive numbers that you can see here regarding the adoption, how much Wi-Fi is used, what is the value, economical value of Wi-Fi, and so on. So basically, the question is that what is wireless unlicensed? No? So wireless unlicensed, and it's simply a set of technologies that operate in the unlicensed spectrum or license exempt spectrum, meaning that it uses free spectrum somehow. This includes technologies obviously like Wi-Fi, Bluetooth, but also cellular solutions, no, like LAA and New Radio U, no. The good part of using the licensed spectrum is obviously that it is free and that it is pretty convenient in terms of deployment flexibility, you know. So it means that anyone can go everywhere and deploy a network. And this is quite cool, I would say, no? The drawbacks of this, of using the license, is that on the contrary, you don't have control over the frequency resources. So you cannot guarantee certain performance. I mean, Wi-Fi works super well, especially when it is isolated. And in fact, it provides very high throughput and very low latency, even lower than in cellular, but in optimal conditions. No, when you have crowded environments, then you cannot anymore guarantee reliability. No, and this is kind of the main drawback, I would say, of wireless unlicensed and Wi-Fi. No, but still there is great opportunity there. Okay, this is a bit of the Wi-Fi historic evolution. So basically, Wi-Fi traditionally it was conceived or widely used for domestic use cases, but now it's kind of expanding, and it has been expanding over the years to many other domains like industry, healthcare, IoT, many domains. No, and this has been possible, I would say, thanks to the evolution of the amendment, the evolution of the Wi-Fi standard. And the Wi-Fi standard has incorporated many features with each version, like multi-user MIMO in Wi-Fi 5, OFDMA in Wi-Fi 6, or now we have multi-link operation in Wi-Fi 7. And the message here is that, okay, so Wi-Fi is expanding to new domains, new use cases, and it is doing so by not only improving throughput, but also by improving other performance metrics, no, like efficiency, latency, and now reliability, which is also very important, as we'll see now. This is a bit the picture of how Wi-Fi standardization is at the very moment. So basically, we are about to finish a standardization cycle in Wi-Fi. So the next or the newest version of Wi-Fi will be released by the beginning of the next year in 2024, and it is Wi-Fi 7 or .11be, and it will include new features like wider channel bandwidth, higher modulation and coding scheme orders, and also this multi-link operation, which is something new in Wi-Fi. This obviously doesn't stop here because Wi-Fi 8 is still has just begun now. So the 11BN has been defined to start its activities this year, and this time in 11BN Wi-Fi 8 there will be actually a complete paradigm shift, because for the first time, instead of targeting extremely high throughput, which is the name of Wi-Fi 7, it will target ultra high reliability. And this is a very important milestone in Wi-Fi because Wi-Fi has always been unreliable, as I said at the beginning. So, okay, so now we will have some determinism in Wi-Fi. We will see, we don't know yet because standardization has just started for Wi-Fi 8. But we will see to which extent reliability and determinism is provided in Wi-Fi, in the wireless, in the licensed spectrum. So yeah, this is about the second part of the presentation on the confluence on Wi-Fi and AI/ML. So the first thing that I wanted to ask is, or I wanted to, address is what can be expected from AI/ML and Wi-Fi. No, so basically here I divided kind of 3 adoption phases. We have early adoption of AI/ML and Wi-Fi, which is nowadays, I would say, where we have kind of AI/ML for assisting the operation of Wi-Fi, for kind of driving a better user experience, but from a management point of view, from the top. And here we have solutions like dynamic channel allocation, deployment planning, and so on, things like that. Then we may expect midterm adoption, whereby AI/ML can actually drive some of the novel features in Wi-Fi, which is increasing in complexity. One example is multi-access point coordination, which it will be the most important feature in Wi-Fi 8. So basically, in Wi-Fi 8, access points will be able to cooperate, collaborate in order to optimize performance. So this cooperation is complex task and gives opportunity to AI ML to interact there, right? And finally, we may have in the long term, we may have this. I mean, we have heard a lot about AI ML native operation, no? So we can have the same in Wi-Fi, and this can start from the definition of AI ML functionalities in the standard itself, no? For instance, for driving the channel access or things that nowadays are not possible. Okay, so why do we need dedicated efforts in Wi-Fi for the adoption of AI ML? So basically, Wi-Fi is very particular. First of all, because it defines the MAC and the physical layer operations only. And unlike for 3GPP networks, where you have kind of big overview of the network and you have more control on all the network, here the set of ML functionalities will be more limited. So the approach is different. And also the fact that it is so local, you are defining the MAC and the physical layer only, then it limits the range of tools that you can use for AI ML. And one example is digital twinning, no? So digital twinning, it makes sense in 3GPP networks, but in Wi-Fi, it can be harder to be achieved, I think. Another particularity of Wi-Fi is about this channel access, because Wi-Fi is using the licensed spectrum, and for that, typically we use listen before talk mechanisms, and there is this uncertainty always. So this should be the integration of AI ML here should be kind of addressed from a different perspective, than if, in cellular you have this scheduled transmission. Everything is very kind of deterministic. In Wi-Fi you don't have this, no? So that's the point here. And finally, there is the curse of the backward legacy compatibility, whereby any amendment on Wi-Fi, so any new generation of Wi-Fi needs to be compatible with the older generations, no? So in this regard, AI ML solutions will need to be aware of what is there, in order to be fair and friendly with these older generations that are in fact not using AI ML, no? And as for the opportunities, basically Wi-Fi is everywhere. So we have billions of devices with Wi-Fi. So this is something that can be leveraged. And of course, the evolution of Wi-Fi is bringing a lot of opportunities in terms of new functionalities that may need the intervention of AI ML, no? Yeah. Okay. So what's there in terms of standardization on AI ML for Wi-Fi? So basically there is a little, but there is something. The solutions that we have nowadays on AI ML for Wi-Fi are mostly proprietary. So basically manufacturers build their own AI ML solutions, and typically they do that by leveraging some kind of solutions, standardized solutions, architectures, tools that like this one, like the operator managed Wi-Fi architecture from the Wireless Broadband Alliance. And these solutions are not defined from the Wi-Fi standard itself, but they operate on top of it, no? So typically they are for operators or for types of networks where you have kind of a controller and you have control over the network, no? So these solutions, basically, they provide the means to kind of perform some AI ML, because they provide the means for gathering data from Wi-Fi devices. They provide the means for configuring and optimizing Wi-Fi devices and so on. But the problem is that, first of all, these solutions are proprietary, so there are interoperability issues there. Another issue is that these type of solutions are not conceived for AI ML, so it is not kind of 100% compliant with AI/ML, and it does not allow to unleash the full potential of AI/ML. And yeah, that's pretty everything. And here it is an example of the type of things that you can configure or type of information that you can gather by using these solutions. Examples are channel allocation, onboarding client devices, setting passwords. So it is very limited what you can do, no? Okay, the good news for Wi-Fi is that IEEE has started a new activity, which is the Task Interest Group on AI/ML for Wi-Fi. And this is obviously the first step towards this long path of adoption of AI/ML in Wi-Fi, no? So basically, this group was established last year, and they are progressing on AI/ML use cases and their technically feasibility for Wi-Fi. And this is very similar to what the focus group on ML 5G did here. And it is a very important activity, as you will see next. No, basically, they are defining these use cases. They have, at the moment, 4 use cases. One is CSI feedback compression for beamforming. Then there is AI/ML-based roaming enhancements. There is also deep reinforcement learning-based channel access, which is kind of very, innovative thing. And very interestingly, they are also addressing AI/ML model sharing, which is kind of universal thing, not only for Wi-Fi. And here, I think there is a lot of space for collaboration with other SDOs and organizations, right? And yeah, okay. So this is basically a bit my view on how to practically bring AI/ML to Wi-Fi. And for that, I used the famous architectural framework from the ITU, this 3.1. Okay, can you go to the previous one? It was, yeah, this one. So basically, this is the ITUT AI/ML architecture for communications. And this was born as one of the activities in the focus group on ML 5G in pre-standardization. And this took place between 2018 and 2020. So basically, they defined a framework whereby you could define and instantiate, let's say, ML operations in communication systems. And for that, they defined this nice architecture, which includes a management subsystem, which is meant for instantiating and orchestrating the ML operation. Then there is this multi-level ML pipeline where there are several nodes in charge of doing things like data collection, data reprocessing, model training, model inference, model output distribution, and so on. And finally, there is the closed loop subsystem, or the ML sandbox, which is, I would say, much more than a digital twin. But I mean, this would be a separate talk, but it is also a component there in this architecture. And this architecture is very suitable for Wi-Fi in particular, because it is very flexible in terms of the deployment options. And in Wi-Fi, you may have very diverse type of deployments, going from fully decentralized deployments where no one is controlling anything, so it's full anarchy. And you can also have more controlled deployments, like in enterprise networks, in industry, where you have control on what's going on. No? So this again calls for different types of ML solutions, and of course, different types of deploying each ML component at different parts of the network. Yeah. And this is basically from a paper that we did a few years ago, where we took this architecture and we use it for kind of depicting or kind of solving AI/ML use cases in Wi-Fi. And here I wanted to put the example of the AI/ML-based Wi-Fi roaming, which is one of the use cases that the task interest group, the IEEE task interest group, is studying at the moment. So this is basically a proposal of where to place the pieces of the architecture to fulfill this particular case, no? And I mean, I don't think we should go through the details. I mean, there is no much time, no? And of course, I wanted to bring the ITU AI challenge into the stage because it is, to me, a very nice activity that it is being done here. So for standardization, it is not only generating documents that can be used by the study groups or whatever, but it is also all the related activities, no, that are around them. No, one is the organization of workshops like this, or all the workshops that were co-located with the focus group meetings, which are very, very nice. And another activity is this ITU AI challenge, no? And the ITU AI challenge, to me, it's a great opportunity to bring together a lot of people, a lot of good people, in fact. And before I heard that non-communications people, you know, is not that good for the purpose, but I think that they bring very, you know, fresh and unbiased vision to communications problems. No? So we can give them problems in communications, and they may think out of the box and solve them like in a original manner, because typically the people that we have communication background, we tend to design solutions, AI/ML solutions, like, but with the mindset of the communications perspective. No? So the ITU challenge is a great opportunity of bringing also these people from other fields, and this is great, basically. Yep. So, okay, to conclude, basically Wi-Fi Alliance and Wi-Fi are very important parts of the telecommunications ecosystem, and they will be very important as well in 6G, as the numbers were illustrating that. The adoption of AI/ML in Wi-Fi calls for special and delicate manners of doing that. I mean, it's not fair to use kind of the same standards for 3GPP to Wi-Fi in terms of AI/ML, I mean. And the good thing is that, as I said, pre-standardization in Wi-Fi, AI/ML for Wi-Fi has begun, but still more efforts are needed, of course. That's obvious. And for that, I wanted to highlight the importance of the ITU activities, ITUT activities in pre-standardization, which is what I know personally, and which has helped me to understand a bit more about AI/ML for communications. So basically, in focus groups, there is big opportunity to bring people together, because typically focus groups are open, so anyone can participate. And in my opinion, this is good for this early stage of standardization, where you need to collect ideas and collect perspectives to see what is important, right? And of course, the ITU challenge, as I said, is also a great opportunity to gather academia, industry, ML experts, and also to identify which are the most important problems or the more challenging problems in communications. And it can also be used to provide input to standard bodies, so that to identify what is needed there. I think that's everything. Thank you.
Thanks a lot, Frank. Actually, Frank has seen everything. He has while doing his PhD, he has worked with us, right? So I know the points that he's having is actually from his experience. So yeah, thanks a lot, Frank. Can I call Karim, please?
Hello, hi. Thanks, Vishnu, for the invitation. Thomas, it's really, I'm really happy to join back the activities after like 3 years of disconnection. So it really feels great to be back. My name is Karim Rabia. I'm a senior architect at Red Hat. My whole career is very like telco-centric. The last 18 years, I exchanged seats between telco vendors like Nokia, Huawei, mobile operators like Orange and STC, system integrators like Tech Mahindra and NEC. And for the last, I'd say, 5 years, I led and still leading the transformation projects and the exercises in the region in EMEA. So I tailored like a storyboard. I have like 10 slides that actually position the artificial intelligence and the cloud native within the umbrella of digital transformation, which what most of the telcos are doing now or undergoing. Because I'm working on the transformation, you'll find that I'm highlighting some challenges and some barriers that actually stops or makes an obstacles for the technology adoption. And I will end my slides with some recommendation from my side on how we can move forward and how the SDOs can help. So please allow me to start. I'm very used to do sessions while I'm standing, so it's very hard for me to do it. So, yeah. Okay. So let's just start with like a primary slide that shows actually what are the motivations of the telcos to undergo the digital transformation. And I'm happy that I came after Mr. Farhi because he talked about the revenue, right? At the end, telcos looking for monetization, new monetization opportunities and looking for revenues, right? And you see that there's a pure decline of revenues in the classic services, in the voice services, in the SMS, in these kind of things. So it became mandatory to start to look for a new set of services, digital services that will be like an evolution to the legacy services. There's a current high quality of expectation at all the users because now they are dealing with hyperscalers, with applications. So they are expecting the same from the mobile operator. They don't expect that to purchase service, he must go to a certain store or to call the call center. He must have it like through a marketplace or an app. So that's the digital experience that he's expecting. Second thing that now there's a battle of anything or everything as a service. So operators are not just competing with operators, competing with OTTs, with hyperscalers. So they don't just want to, offer voice services. They want to transfer all the existing domains, classic domains like RAN, core, transport, whatever, into something that we call a service exposing domains. And using the intent-based orchestration, we'll talk about the intent. Then we can start to offer like new modern services out of these domains, like network slicing, for example. Second and last thing I'll talk about, it's actually the tough enterprise market competition. I was talking with one of the colleagues today that the service of a mobile operator is very local. So you can just provide service to your customer locally in the border of the country. While hyperscalers, for example, can offer the same service across the globe. So also operators want to go to that stage. If you just scan all these like requirements or challenges, you will find that cloud is an enabler, is a basic catalyst for such move. And that's why, for example, I'm not good with this. That's why if you like interpret the ongoing activities at any operator, most probably you will find a lot of scattered initiatives at many departments, at many teams. Like DevOps at one team is looking for new digital channels. One team is looking for deploying cloudification under different names, private cloud, IT cloud, telco cloud, whatever. You'll find some team talking about a solution for AI. Radio team has AI capabilities. So you'll find a lot of scattered initiatives at many domains. While in reality, there is a big umbrella, which is the digital transformation, that should actually include all these initiatives, because all these initiatives should work together to deliver the value to the telco operator, which is actually going to be a DSP, getting a new monetization opportunity and getting new revenue streams. What you see on the left, these are like the classic domains that you will find at any operator or any enterprise, like resources like the cloud infrastructure domain, service like the OSS part, for example, and then the customer domain, and then the domain that where you sell your product. So a lot of initiatives are actually cross-domain initiatives. And one of them at the AI. AI should be, yeah, exactly. So AI should be a cross-domain capability. Unlike the current case, which we have in the most telco operators are scattered things in many departments. So my slides are focusing on two pillars, which is the cloud and the AI. Yeah, I'm going to show exactly the evolution of the two paths, and then I will end up with some recommendations. So starting from 2012, with the rise of NFV, network functions virtualization, and mainly from 2015, the deployment of private clouds has been there started to rise at the mobile operators. The basic service that cloud used to provide was infrastructure as a service. So we were just providing some sort of a virtualization layer where application owner or telco teams can just start to onboard their telco functions, and these are classically the radio and the core and the network routers. And with that infrastructure as a service, there were some talks about controllers like the SDN, like the OpenStack, and some attempts from HCNFV to provide some sort of orchestration layer like the NFVO. And also there were some operational tools like the FMPM, but it lacked a lot of things like RCA, like closed loop control. This was not there in the cloud. What we are observing, what we observed is that the cloud started to evolve to start to provide an advanced service on top of infrastructure as a service. Starting from, I would say, 4 years, and especially with the rise of 5G, most of the mobile operators starting to deploy the CaaS layer or the container as a service, to deploy something like Kubernetes solutions to start to host the telco application that were modernized to be container-based or microservices. And as you see here in the slide, that's where you start to onboard the bot or the containers either on bare metal or in a virtualized layer. But the most interesting thing, and that will be the touch point with the AI here, is that cloud started to provide also a PaaS, platform as a service, not just a container as a service or just a virtualization layer, but starting to provide something like load balancing as a service, data analytics, RCA. So here we can detect an intersection between what cloud is offering and actually what the vendor solutions they're offering. And I will give a concrete example on that. I put here data analytics. We all know, I think, the NWDAF, right? The network data analytics function of the 5G. The most interesting thing that 6 months back, there was a white paper from AWS, and they were listing the flavors of the NWDAF that AWS is providing. One of them was PaaS, like a capability from AWS itself, inviting their customers to use it as a software as a service, for example. The other thing that is telling you, and we are onboarding vendor X and vendor Y solutions for NWDAF. So now it's an option for the customer, either to go with the cloud capabilities and build on top of it, or to onboard external capabilities. So that's a new trend in the cloud. Okay. No, just okay. For the AI, we started, I'm trying just to interpret the journey. We started to have, I would say the first wave was to have like a functionality or a capability in a certain VNF or a certain function that using AI, that's using AI. And I'm giving you an example that, for example, these are like virtual machines or microservices. So one at a time, there was like many features related to paging, right? Smart paging. Because in paging, you just send a broadcasted message to all users on the cell level or on tracking area level, and whoever the user who gets his ID, he said, yes, I'm here. So for example, some vendors introduced the feature of smart paging that is using AI with some predictive patterns. He can just select the cell that the user is assumed to be there. So that was the first step where telcos met like the AI capability. It was embedded in the VNFs or in the network functions. And then the second step was to having some sort of a platform as a service or a capability from a certain function exposed to the other network. I brought here an old example of this Acomos or Acunos adapter in the RIC. but this project was archived. But the idea of having an X app, for example, in the RIC that is supporting RIC to take decisions, that be considered the same case. The case as I mentioned about AWS providing analytics as a function, that also applies, or that also follows the same methodology. The third pattern where I personally worked on, because I was mainly working on the orchestration stack like 5 years back, to extend the capabilities of the existing orchestrators in the network to add some sort of a policy engine or some sort of an ML-based engine that helps the orchestrator, for example, for the closed loop control, instead of having the automation scripted, I mean, or the logic scripted using by a policy engine. And there is an example, for example, of the ONAP, the component, and ONAP is based on microservices, the component of the policy engine that is actually representing that case. And all the commercial orchestrators in the market from all the vendors, they include a sense of a policy engine that's actually working based on ML. What we want to achieve, and then next steps, that, as I will say, I will also discuss in the next slide. So telcos, they like reference architecture. We like reference architecture. We like a document, standard document that tells us who is integrating with what. This is actually what we used to do, right? 2G, 3G, 4G, 5G, and I think 6G will not be an exception. So we want to have a standard reference architecture where operators can follow as an initial step just to draw the architecture. Because for operators, if you can't give them a visualized architecture on how the solution would be, it will be very hard to adopt it. Very, very hard. Last thing, or the next step, and you were all talking about the AI native, and in the first session we had a definition about the AI native. So what I'm saying here, that plus the architecture, the functions itself must be natively designed and architectured to be AI native. For example, using the AI techniques for the lifecycle management for any kind of service logic that is natively, I mean, would be natively used by the network function. That's why I used two things: by design and by architecture. So architecture is following the AI, allowing AI capabilities to be exposed and consumed, and by design that the microservices itself are designed to consume, I would say, the AI service from the network. And the last point, and it is very important, and I will witness that in the 5G. I give you one example about what happened in 5G. We spent like 3 years talking about orchestration of the radio domain. We spent like years talking about orchestration of the core domain, but no one really believed that this could be true. Once the orchestration framework was brought in 3GPP SA5 in the 5G specifications, all the operators said, yes, we need this one. So it's very important to push the logic of the architecture in the ways when the technology is starting. If you succeed to do that, most probably these solutions or this technology will be adopted. And this happened in the 5G. Before the 5G rise, I was working in one of the orchestration vendors. We had many nice use cases about core orchestration, but no one believed that they needed. But once 3GPP mentioned that, they all asked for it. My last slide. And again, I'm really heavily involved in the transformation engagement. So I work with the operators to transform the operator, like from CSP to a DSP, under different names, under the name of digital transformation, center of excellence, DevOps, hopefully MLOps, in like what we heard. So my recommendation that, okay, I follow a principle in my work called 80-20, that 20 is the technology. Technology is important, but if you don't have the right culture and the right organization, most probably the technology will fail. That's why when you're talking about being AI native, or even being cloud native, then we as an SDO, we should provide some sort of blueprint that actually explain to the operators how to adopt this technology, how this technology will change their enterprise architecture. Do they still like have the classic design and operation teams where they have their classic network teams, or you need also to do some sort of a cross-functional teams, horizontal team, virtual teams, and what will be the operational model? how to procure the AI-based solution. Believe it or not, this is one of the obstacles I witnessed with telco operators. They don't know how to procure an AI-based solution, because procuring a box is easy. You issue an RFQ, requirement, fully compliant, you get the scope, and then deliverables are very straightforward, put in the contract, and that's it. So we need to work on transformation blueprint, not just technology, how this solution, how they should adapt to welcome this technology. Second thing, the standard architecture. I heard really great things today. I learned a lot. And the idea of having like interfaces on demand, that was really, for me, it was really not a surprise, but a concept that I didn't think about it before. But in general, telcos, they love the architecture. In 6G, we have to enforce I mean, I witnessed the write-up of the documents from the ITU, and we all really appreciate the effort done on the machine learning architecture, specifying the interlocks and issue definitions. So this should be pushed somehow to the standard of 6G. Third thing, the brownfield success stories. Not all the operators, and it happened when we started the cloud journey. Our reference was AT&T and NTT Docomo, but usually the comment is, we are not AT&T and we are not NTT Docomo. We don't have developers. So you have to always promote or advocate success stories. For example, you all talked here about nice machine learning solution. But if all operators now are participating, then we have to issue reports on success on a brownfield, not like not an extreme case, and not even a greenfield, because nowadays there are new types of operators greenfield, like starting on an OpEx based, for example, partnering with a hyperscaler. No, we need a classical CSP who is actually adopting machine learning based solutions and help them to achieve his targets, and then we issue that report. Number 4, and that actually, unfortunately, that killed the NFV. What killed the NFV, or what actually was an obstacle in the NFV adoption and the spread of telco cloud, was the technology fragmentation. What's technology fragmentation? That instead of dealing with one entity as telcos used to do, like 8 years back, 10 years back, they found a lot of entities issuing a lot of publications, and then and then multiple open source groups complementing the SDOs with multiple projects. And that raises something very dangerous, which is the uncertainty. If the operator is uncertain about technology, this will open the door for single vendor stacks to get in. So I really call for some sort of collaboration of standardized confinement and having some sort of a guide to mobile operators, what to follow. Last thing that I mean, in the old days in 3G and 4G, we used just to issue standards, but now it's not enough. You have to complement the standards with POCs and pilots. So that's why, for example, entities like AT&FV started first 4 years just issuing standards, and then there was no adoption, and then they had to go for POCs, for demos, for Plugfest, for whatever. So we have to complement standardization with realization, and that this is doable and this is happening. That was my last slide. Thanks a lot. I think I made it right. Okay, thank you.
Thank you. Thank you so much, Karim. A very, very practical points. I think each of those points we can spend a lot of time, but unfortunately we have to wrap up today. Can I call upon Professor James and Fidel to please do the last presentation? I can assure you one thing. This is a very interesting presentation. I know it is the last, but sorry. Yeah, sure. Thank you. Yeah. So yeah, this is. I know this is the last presentation, but it's a very interesting presentation. We have had an amazing journey with Professor James and Fidel last 5 years or so. So you should listen to it.
Yes, thank you very much. Greetings to everyone. And equally, I bring to you greetings from my university, the Federal University of Technology, Mina, and at the same time, the Veritas University, Abuja, all in Nigeria. I have the pleasure of being here today, not just having to barge in, but with the cooperation of some very, very key important persons I must not fail to recognize. Madam Karoki Tatiana is somebody she's not here. Kuroki, sorry, but Tatiana, I really need to appreciate her for the wonderful encouragement. Way back when we started, she actually encouraged that the academia is a key to development of this course. And I can't say thank you enough to Dr. Vishnu, who has been an engine room to the course of the progress we've made. So not taking much of our time. The time is fast spent, and I need to work within the specified time. I will be speaking with my co-author here in the person of Dr. Fidelix Honor, and here we're here to give you this talk on leapfrogging to the next generation, a developing nation's perspective. Quickly, this is a brief overview of what we have. Next slide. Yes, we all know we've heard so much about ML, AI in communication networks. You know what artificial intelligence and machine learning approaches have established themselves in the field of communication network. Communication network can be clustered into AI ML techniques for network monitoring. AI ML techniques help in network management, operation, automation, and also address the design application in the techniques to improve the ways we address networking today. Next slide. Quickly, talking about the application, applying AI ML to reduce costs or faults in network is actually key, because for we to leapfrog the developing nation's perspective. Yeah, you've been talking, good number of authors have spoken, and they've not actually made emphasis on the environment where some of these things are being done. We need to appreciate the environment. The domain actually differs with regards whatever technology you are evolving. So it's a key issue we need to look at so we can address it effectively. Here we have study use cases for application in 6G, create models for from around the world, fine-tune with local data, monitor with human feedback. Here, when you go back. When you are in a developing region, leapfrog to technology to reduce the cost of faults in the network. Next slide. Yeah, here we have some vertical industries, industry verticals that actually are a proponent of enjoying what this means, because we heard so much about the 6G, and that is where we're going, whether we like it or not. The encumbrances, the constraints that will be associated with getting there is what we are all here to discuss and possibly solve moving forward. So collaborate to study the local relevant use cases. Now, how to reduce cost of innovation. Here we have the digital twin. You've heard so much about digital twin today. A good number of authors have actually done justice to that course. And for a digital twin to network and generative AI, digital twin and network. All of us can see what ChatGPT is doing today, and issues of virtual reality and augmented reality gradually creeping in, and things are happening, and all together makes up the kind of the network we look into the future. So now you say when you don't have you can see what we have there, the dollar sign for innovation budget, then generate data and innovation will probably meet the gap. Next slide. So there's something I want us to look at very well, network service orchestration. I love this aspect of the entire design very well because there's so much to actually bring on it. I was interested in what Paul was saying the other time when he was talking about intent, because it's a very important point to bring out. But when we look at the concept of network service of orchestration, you begin to see what this thing is all about. When you have, when decisions are to be made, insights are to be realized, then you probably need a knowledge-based manager that will aggregate whatever knowledge you receive from outside and inside and generate a knowledge base for an automated controller to eventually pass on to an autonomous network orchestrator that will do the management, that will carry out management, monitoring, and other functions. So it's a thing to actually embrace. Next slide. So how to reduce cost of automation? Now, with myself here, my humble self here, some time ago, it was my brainchild. I came up with the idea of developing a research group among young school students, which we call WINESS. That's WINESS means Wireless Networking and Embedded System Research Group. We had youngsters who are undergraduates in my university within the age bracket of 15, 16, 17, 18. As young as they could, they were then. Tasks were given to them at various intervals, and on weekly basis, we're having meetings, and these meetings gradually developed them, and they got mature to attending some of the problem statements from the use cases provided in by ITU. And we had a platform that's a build-a-thon competition where they came, showcase themselves. Some of them have actually won bronze at some instances, gotten to their finalists, and we're still making remarkable progress. I can tell you, and I can assure you now that some of those two students are hot and bright for the market today. Is with these initiative. So what we have here, you have the analysis of zero-touch network and service management requires document was done. So all of that we actually took into cognizance. Now we have the cloud you have there, knowledge base, resource, simulation resources, AI and ML models and data, all within the 5G framework. Next slide. Yes, I said most of us for the past couple of hours, we've been talking about some of the discoveries, projections, and what is on ground, but we don't talk about the environment. Some of these things we do are usually environment centric. The progress we made could be affected by the environment. So we have challenges which ordinarily we tend to see how we can surmount. A while ago, I was telling Paul that the reason why I greatly appreciate you is that you give us standard when we see what you do, standards to work on, because we always follow him and see the much he's doing. We said, no, you're not going to give us this gap. So he motivates us to move. So seeing some of the things they do, I said, no. These are some of the challenges we have. Maybe they don't have it over there. So we try to see how we can close the gap. Like the issue of energy, epileptic power supply is really a challenge to some extent though. It's been gradually being worked upon. Internet connectivity too is not complete. And to some extent, we still have some challenges. Now, low percentage penetration in terms of AI, ML awareness. Yes, this is equally an issue there. but still coming up and still being advertised. And lack of proper mentorship. Yes, some person we need more experts to mentor some of these youngsters. Then, of course, though I know this is a general problem, but it could be more in some other areas, funding challenges. Now, we have a blueprint for ITU academia collaboration with the research team. Yeah, ITU, FG, ML, 5G student project, all of these were our roadmaps. So where we are today, there are more than 3 contributions from the Yness team actually have been involved then way back. Then ITU News Magazine for ML in 5G. That's article highlighting the research projects in Nigeria. Actually, I have the pleasure of telling you that, letting you know that some of the media houses have actually taken time to recognize some of the work we do, and they've hosted various interviews among these youngsters, and it has further encouraged the youngsters to declare interest, and more are coming when they see remarkable feedback from these media houses. And ITU RG13 Africa's 7th workshop, we participated there and contributions were made, and more recognition. The ITU RG13 Africa 8 workshop, an in-depth study of existing standards related to autonomous network. Then ITU FG, that focus group on autonomous network, Build-a-thon. We've actually participated, and I think impact was made and recognitions were equally felt. In 2021, first position, network resource allocation for emergency management based on closed loop. Here we try to see how we can come up with a network resource allocation based on intent for autonomous network in a closed loop system. And in 2022, 3rd position, baseline representation of AN controllers. All of that were done. Then the same again for the 3rd position, development of a smart weather station. All of these were realized with the research group, which the students have actually been participating in. Next slide. Yeah, here we have some of this is just a similar kind of scenario of what we have in my institution, where we have the students always coming together to collaborate and discuss, have group discussions. And in one of it, they came up with a project here where we had a research topic in Nigeria, advancing education and speech recognition. Here we were able to come up with an AI classroom speech recognition scheme that will easily interpret some of these things in local languages. So making sure that the barrier is actually melted. So the important key takeaways are actually what you have here, and a couple of recognitions have been made. This one of these online interview granted us, and it's actually there on YouTube till date. So what we need in now leapfrogging to next generation. This is a key deliverable. So what is expected? Mentoring, creating open knowledge base, AI for developing nations, reference LLM hubs. I was interested in LLM hubs. And that's why I took that question when the other speaker was talking about it. Go ahead. So maybe the next 1 or 1.5 minutes or 2 minutes, not to take our time, we want, I'll call on engineer Dr. Fidelis Honor, who is equally a co-author and a consistent participator in the course of this program. So you have the floor, sir.
Thank you very much. Thank you very much, Prof. James. And I really want to thank, is it all right? Yeah, okay. I really want to thank the Vishnu and all the people that had made it possible, Basikolo and all of them. It's quite a good thing. And because it seems like all the things being discussed here are really discussing the developing nations, because we really need this kind of knowledge and skill. So when we are talking of leapfrogging to the next gen, it is the ability for crisis management of the ensuing disruptive tendencies or risks in the process of leapfrogging. And being able to manage it is key to success. And the concept of leapfrogging to next gen, it is not only the attempt for successful leapfrogging that is key. Not all the leapfrogging attempts are successful. So there is a need to embark on risk management. The choice may not be popular. That is the choice of the technology or the process that you may use to leapfrog. It may not be a popular one. It may also lack the economy of scale. It may not be easily achieved, and it may not have the return on investment that might be necessary to sustain such leapfrogging. So these are part of the issues that ensue when you are trying to leapfrog in developing nations. Leapfrogging as a concept to the next gen refers to the concept of bypassing the traditional stages of development and embracing advanced technologies directly. Machine learning in the family of artificial intelligence has the potential to drive leapfrogging in the developing nations by leveraging data-driven decision-making, automation, and optimization. I know that the developing nation will also like to embrace autonomous networks and autonomous IoT and different things that come with machine learning. It does not mean bypassing relevant essential processes like integrity tests. If you want to leapfrog and you want to embrace certain technologies, there's need for integrity tests and there's need for interoperability as well as interconnectivity. So when we are talking of leapfrogging, it does not mean bypassing this or bypassing human capital development or bypassing proper fundraising, raising process or research development, but it is bypassing obsolete technologies and routines and deploying most appropriate technologies that would address the issues. But there are risks that are associated with this. The existing technologies are not always adapted to the local trends. Then the needed technology include mobile phone applications, sensors, satellites, drones, and so forth. And we all know that these are all high-tech systems that require high-tech management. So if you want to bypass, does the nation or the people have this capacity for the high-tech management? So these technologies are smart and intelligent and programmable and could be disrupted. You know, like hacking or other things that can corrupt the system. What we are also saying is that for such processes that cannot be skipped, like we have talked of human capital development, we've talked of R&D, fundraising. For such processes that cannot be skipped, we require that it should be fast-tracked, that fast-track procedures should be developed and employed. Like in human capital development, it could be crashed. The training could be, intensive, and then within a short period, the needed expertise could be developed. And then in research and development, just like we could borrow from ITU system, if a topic is being discussed or researched on, it could be broken into very smaller pieces where smaller working parties could discuss them and raise them. These are non-existent in developing nations. So if these are supposed to be there, these are supposed to have been covered before the leapfrogging, but it could also be crashed. And then there's also a problem of government buy-in. Sometimes there is a political issue, the political willpower to further such steps that could help in leapfrogging, and then give the necessary backing, give the necessary regulatory enablements, and then also the funding. So the ability of the system in learning the new techniques and adapting to it is also very key. And these are kind of risks that are associated with it. Some of the challenges are like inadequate infrastructure and other development resources like data, ICT tools, etc. Poor human capital development, uncoordinated and inadequate policies of government agencies, coupled with the absence of legal and regulatory frameworks. These are kind of things that can, challenges that they meet, because in certain areas, in certain climes, the respective government agencies tend to hold their tough and would not allow penetration from, like tough protection, they would not allow penetration from other agencies. But like we have seen, because of the massive convergence and the kind of penetration of machine learning and artificial intelligence, no one person, no one system can go on without the cooperation of other associated systems. So, but you will see these people holding fast to their toughs. So we also know of inadequate and weak institutional frameworks, like certain regulatory bodies are supposed to enjoy some measure of independence, some measure of authority, but you find that some of them are not having such things. And these are preventing seamless synergy between existing ICT implementing institutions. So government policies sometimes do not create the enabling environment, like I have even mentioned before. And then there are problems of inadequate investment. Like if you want to leapfrog, what it means is that you have to put in a lot of energy, a lot of money, so that it can bypass the present situation and be able to manage the disruptive nature that might ensue. Then funding, these are all known. So in my little conclusion, I would like to say that constraints that developing economies face are investment opportunities, having the right regulatory environment in crucial areas, and for enabling that would enable leapfrogging. Innovation must scale, and pilots schemes must scale through to trigger the leapfrogging. Public investments should prioritize scale acquisition and low return on investment. Low return on investment. R&D is key for adapting technology to local contexts. I want to thank you for the time, the extended time that was given to me to make this presentation. Thank you very much.
Thank you, Fidel, and thank you, Professor James. That is well understood. I think at least from a technical perspective, we should be able to extend the collaboration with what we have been having with Professor James. It has been quite amazing. The achievements what he showed are quite amazing. We may not have much time for discussion. Bilal is waiting. So please let me call upon Bilal to conclude with the lessons and the gems that we have from today's session.
You did well.
Thank you very much, Vishnu, and thanks to all the speakers and all of the listeners for your endurance today. It's an amazing day. We've had many interesting talks. I have learned a lot myself, not having been following closely this work since the 5G machine learning focus group and the publication of the Y3172 that has been cited many times today as a reference document for the work on machine learning in ITU and beyond. Many new interesting areas that have I'll just point out what was recurring as I was listening from, I think we started at 7:30 today with the breakfast session. We heard a lot about the native AI. We heard a lot about open source, about data, access to data, the large language models, the move from model development to model deployment with the MLOps, for example, to bridge. A very interesting concept of not defining the interface, but actually using the semantics from Abhishek's presentation to have intelligent production and consumption of data structures. Quite innovative. Discussions around the 6G RAN. But throughout this first session, there was always a recurring theme of needing a group or a platform for this discussion and collaboration to take place. Then in the second session, we heard a lot about the digital network twin, the graph neural networks, the graph machine learning. Then we heard also about the native network intelligence from Nokia and the work that's happening in 5G, in 3GPP and ETSI, and the importance to collaborate and not duplicate some of the efforts and see where there are areas of standardization or pre-standardization that needs to happen. We heard about autonomy versus cognition. Also a very interesting presentation by Professor Tom Luo on the SRCon and the optimization of networks and the use of AI to optimize networks. I hope that could be also contributed to ITU because it's quite innovative and interesting as an area. DeepSig and the presentation on the performance evaluation and view with using AI machine learning, and also the need for pre-standards work to accelerate 6G machine learning and the proof of concept. Then we had some interesting Q&A. Unfortunately, I had to go to another AI for Good focus group just across the hall to talk about creating a new initiative on the AI for Health Global Initiative, which we will be launching with WHO and WIPO tomorrow. So I missed the presentation from Shilling, but I had the opportunity to hear some of her thoughts earlier today, and it's really the need for, again, AI native data access, but also holistic and collaborative view among the SDOs on AI machine learning in the 6G space. The need, again, for data harmonization, data access, APIs, collaboration with ETSI, 3GPP, TM Forum also on the APIs. By the way, we already have a very strong collaboration with TM Forum in Study Group 20 on in terms of IoT, but we certainly could expand that to APIs in machine learning. And again, a lot of mentions in context of Open RAN with the open source discussions. Then after I came back, I saw the presentation on Deep Verse and 6G and a call to ITU to support the data sets and multimodal sensing, compute resources, access. Telefonica, Jose also mentioned forging networks of tomorrow on terms of the deep learning and mobile, and listed some of the open challenges of explainability, usability, autonomy and MLOps and energy efficiency. Then Paul from University of Glasgow talked about the intent, which was repeated a few times in other presentations. Interesting concept, but also that we network engineers want scale. So we need another way of addressing this by using machine learning and using the engineers to develop those models and annotate in the network design. I think we have an offer from Do to use the MENA AI machine learning sandbox. So if we go forward with a group that will not just look at the pre-standard specifications on paper, but also look at the open source and have a sandbox where this could be complemented. And was very interesting, the presentation, second one from Nokia with Francesc, on how actually the previous focus group was a learning ground as you're developing your PhD. So that's a very interesting story that I think why 3172 was quite impactful. And then Karim kind of tied it up with the Red Hat perspective and your experience around the operator networks and how the telcos are transforming themselves, having the digital transformation. And the need for guidelines on helping them procure and deploy AI and machine learning. And the closing was really very pleased to hear from our colleagues in Nigeria about how the journey with the Study Group 13 and the African group, regional African group under Study Group 13, as well as the focus group work has been helping in designing a leapfrogging strategy in developing countries, and the challenges that you face from power, connectivity, awareness of AI, machine learning, mentorship, and funding. So overall, I think we had a 360-degree view on AI and machine learning and 6G. There are many key points that I kind of touched upon and that could really constitute the terms of reference of a group that could continue this effort and maybe focus on 6G machine learning and the use of native AI. Not as we have done in the 5G, it was kind of an add-on, but now it's more of a as a native perspective. So that is probably the, to structure that, there has to be a contribution to one of our study groups. Probably Study Group 13 is the most logical place to continue this effort. It is the study group that published 3172. That is now being widely used reference across the industry, but certainly in a collaborative way with our other partners, 3GPP, ETSI, ORAN, and so on and so forth, to really design the next blueprint for machine learning in 6G, and how we could not only work on the specifications and pre-standard work, but also on the open source, open code, and the sandbox. So hopefully I've done fairness to all of your efforts today, and I'll stop here and turn it back over to Vishnu. Thank you.
Thank you so much, Bilal. I think that is Bilal just now put out a very nice word cloud of what we did for the day. Thank you so much, Bilal, and thank you for your guidance. We will we will make sure that we follow up and, you know, do as per your guidance. Thank you so much.